Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. Let's begin with something simple and quiet. Something vast but reassuringly slow. Volcanoes. They're Earth's patient way of letting go, of releasing heat that's been building for longer than any human timescale can comfortably hold. Think of them as the planet's slow-release valves, channels through which deep warmth travels upward, reshaping land grain by grain, flow by flow, across spans of time so long they make a human lifetime feel like a single breath. And here's the thing, you don't need to remember any of this. The facts can drift past you like warm air cooling in a quiet room. Let them settle where they will. A volcano, at its most basic, is simply an opening. It's a place where material from deep inside Earth can reach the surface. That's all, no drama required. Just geology doing what geology does, moving, shifting, releasing. When we talk about what's happening beneath our feet, we use a particular word for the melted rock that hasn't yet seen daylight. Magma. It sits, there in chambers and pockets, warm and patient, waiting for the conditions that might let it rise. And when that same material finally does emerge, when it flows out onto the surface where air and sky can touch it, we call it lava. Same substance, different location, different name. It's a small distinction, but it helps us talk about where things are in their journey from deep to shallow, from hidden to visible. Now, magma isn't just melted rock. It often contains dissolved gases, water vapor, carbon dioxide, sulfur compounds and others, held in solution by the enormous pressure of the rock above. Deep underground, that pressure is so great that gases stay dissolved, invisible, part of the liquid mixture. But as magma rises toward the surface, pressure decreases. Think of opening a bottle of carbonated water. The release of pressure lets carbon dioxide come out of solution, forming bubbles. The same principle applies here, though on a much grander scale and over much longer periods. As magma ascends through fractures and conduits in the crust, those dissolved gases begin to form bubbles, expanding as pressure continues to drop. This process matters quite a bit, because gas content and behaviour influence how a volcano will eventually express itself at the surface, but we'll return to that later when we're ready. Volcanic activity is one of the ways Earth releases its internal heat. Our planet is warm inside, not metaphorically, but literally, measurably warm, and that heat comes from two main sources. Some of it is original heat, left over from Earth's formation 4.5 billion years ago, when countless collisions of smaller bodies released energy that melted and shaped the early planet. That primordial warmth is still radiating outward, slowly, steadily. The other source is radioactive decay, elements like uranium, thorium and potassium scattered throughout Earth's interior, break down over geological time, and that decay releases heat, continuously. Together, these processes keep the inside of our planet far warmer than the cold of space would otherwise allow, and volcanoes are one outlet through which that warmth finds its way to the surface. Volcanoes don't appear randomly across Earth's surface. They tend to form in specific geological settings, places where the conditions are just right for magma to form and rise. This isn't a matter of chance or cosmic whim. It's the result of plate tectonics, the slow dance of Earth's outer shell. We'll explore those settings in detail soon enough, but for now, just hold the idea that volcanoes have preferred locations, zones where the planet's internal machinery makes their existence not just possible but likely, even inevitable. When scientists talk about volcanoes, they often describe them as active, dormant, or extinct. These categories are based on recent behaviour, though recent in geological terms can span thousands of years. An active volcano is one that has erupted, in recorded history or shows clear signs of ongoing unrest. Gas emissions, seismic activity, ground deformation. A dormant volcano hasn't erupted recently but still has the potential to do so. It's sleeping, not dead. An extinct volcano is one that scientists believe is unlikely to erupt again, often because the geological conditions that created it have shifted or ceased. Of course, these distinctions aren't always sharp. Sometimes a volcano thought dormant surprises everyone. Earth keeps its secrets well, and our observations, however careful, cover only the thinnest slice of geological time. Let that foundation settle for a moment. we've established the basics: what a volcano is, what magma and lava are, why Earth is warm inside, why volcanoes form where they do rather than scattered randomly. Now we can move gently into the question of location, into the specific settings where volcanoes prefer to grow. Many volcanoes form along tectonic plate boundaries. Earth's outer shell, the lithosphere, is divided into several large plates and many smaller ones, all floating on the softer, slowly flowing rock of the mantle beneath. These plates move, not quickly by human standards, typically just a few centimetres per year, about the rate your fingernails grow, but over millions of years that motion reshapes continents, opens and closes ocean basins, builds mountains and, yes, creates volcanoes. Where plates interact, dramatic things can happen, albeit slowly. Convergent boundaries are places where two plates move toward each other. The specifics of what happens next depend on what kind of crust is involved. When an oceanic plate meets a continental plate, the denser oceanic plate typically sinks beneath the lighter continental plate in a process called subduction. Picture one massive slab of rock sliding beneath another, descending back into the mantle. As that oceanic plate descends, it carries with it water, locked in minerals, trapped in sediments, and that water becomes crucial. At depth, heat and pressure release the water, which then rises into the wedge of mantle above the subducting plate. Water lowers the melting point of rock. It allows the mantle to melt more easily than it would if dry, generating magma that can rise toward the surface. This is why chains of volcanoes so often form parallel to subduction zones. Think of the Cascade Range in the Pacific Northwest, or the volcanic arc of Japan, or the Andes along the western edge of South America. They're all expressions of this process, long lines of potential and actual volcanic vents marching along the edge where one plate dives beneath another. The subduction process itself is worth lingering on, because it's one of the most important geological processes shaping our planet's surface. As the oceanic plate bends and descends into the mantle, it generates earthquakes, lots of them at varying depths. Shallow earthquakes occur where the plates first meet and begin to grind past each other. Deeper earthquakes happen as the slab continues its descent, sometimes reaching depths of several hundred kilometres before the slab becomes so warm and weak that it can no longer fracture in the brittle way that produces earthquakes. The descending slab also drags down sediments that have accumulated on the ocean floor, layers of mud, sand, organic material, all compressed and carried into the depths. Some of this sediment gets scraped off and piled up at the edge of the overriding plate, forming what's called an accretionary wedge. But some of it continues down with the slab, and eventually those sediments, along with the altered oceanic crust itself, begin to release fluids as they heat up. These fluids don't just contain water, they carry dissolved elements, sodium, potassium, silica, trace metals, and they migrate upward through the mantle wedge above the slab. The introduction of these fluids causes partial melting of the mantle rock. Not complete melting, the entire mantle doesn't turn to liquid, but enough that pockets and zones of magma begin to form. This magma is different from the magma that forms at mid-ocean ridges. It's been influenced by the fluids from the slab, enriched in certain elements, more evolved chemically. As this magma rises, it may stall in chambers within the crust, where it can sit for thousands of years, slowly crystallizing, changing composition as minerals settle out or as fresh magma is added from below. Eventually, some of this magma reaches the surface, erupting to build the volcanoes we see in subduction zone settings. Divergent boundaries, by contrast, are places where plates pull apart. As the plates separate, the pressure on the mantle beneath decreases. Lower pressure makes it easier for rock to melt, even without adding water, so magma can form and rise to fill the gap. This process creates new crust as the magma cools and solidifies. Much of this happens beneath the ocean, hidden from casual view. Mid-ocean ridges are the largest volcanic systems on Earth by length. Tens of thousands of kilometres of underwater mountain ranges where new oceanic crust is continuously being born. The rock there is mostly basalt, dark and fine-grained, formed from magma that cools relatively quickly in contact with cold seawater. Most people will never see these ridges directly, yet they represent the planet's most voluminous volcanic activity, a continuous, slow process of creation happening in the deep and the dark. The process at mid-ocean ridges is remarkably consistent, yet it varies in detail from place to place. Some ridges spread quickly, pulling apart at rates of 10 centimetres per year or more. Others spread slowly, just a centimetre or two per year. Fast-spreading ridges tend to have smooth, broad topography and steady magma supply. Slow-spreading ridges are more rugged, with deeper rift valleys and more episodic volcanic activity. But in all cases, the fundamental process is the same. Plates pull apart, mantle rises to fill the gap, pressure drops, melting occurs, magma ascends, and new crust forms. It's a factory for oceanic crust, operating continuously, building the floors of all the world's ocean basins. Not all volcanoes fit neatly at plate boundaries, though. Some form above what are called hotspots, persistent upwellings of unusually hot mantle material rising from deep within Earth, possibly from the boundary between the mantle and the core, though scientists continue to debate the precise mechanisms and depths involved. A hotspot stays relatively stationary while the tectonic plate above it moves. Magma generated by the hotspot punches through the plate, creating a volcano. As the plate continues its slow drift, that volcano eventually moves away from the heat source and becomes inactive, while a new volcano begins to form over the hotspot. Over millions of years, this process can create a chain of islands or seamounts, each one a snapshot of where the plate was at a particular moment in geological time. The Hawaiian Islands are the classic example, a string of volcanic islands tracing the movement of the Pacific plate over a deep mantle plume, with the Big Island currently sitting above the hotspot and still growing, while the older islands to the northwest are slowly eroding and sinking, their volcanic fires long extinguished. The Hawaiian chain extends far beyond the islands you might visit on vacation. If you trace the line of seamounts to the northwest, you find the Emperor Seamounts, underwater mountains that continue the chain for thousands of kilometres across the Pacific floor. These seamounts are the ancient remnants of the same hotspot activity, dating back tens of millions of years. The chain even has a bend in it, the Hawaiian Emperor Bend, where the direction of the seamount chain changes abruptly. This bend records a change in the direction of Pacific plate motion that occurred roughly 50 million years ago. The hotspot stayed in place, but the plate changed course, and the volcanic trail it left behind preserves that history. Hotspots aren't unique to Hawaii. Yellowstone sits above a hotspot beneath the North American plate, and the track of that hotspot can be traced southwest across Idaho in a line of progressively older volcanic fields. Iceland sits atop a hotspot that coincides with the Mid-Atlantic Ridge, which is why Iceland exists at all. It's a place where both divergent plate boundary volcanism and hotspot volcanism work together, building the island faster than erosion can tear it down. The Galapagos Islands, Reunion Island in the Indian Ocean, the Azores, all are hotspot volcanoes, each one marking a plume of heat rising from deep in the mantle. Now that we have a sense of where volcanoes form, plate boundaries, both convergent and divergent, and hotspots scattered across the globe, we can relax into considering what shapes they take. Volcano shape isn't arbitrary. It depends on the properties of the lava involved and the style of eruption, both of which are ultimately controlled by magma composition and gas content. Shield volcanoes are broad, gently sloping structures that can stretch for many kilometres. Their slopes are so gradual that if you are standing on one, you might not immediately realise you are on a volcano at all. It could feel more like a long, gentle hill. Shield volcanoes form from repeated eruptions of low-viscosity lava, typically basaltic lava, which flows easily and spreads out in thin, far-reaching sheets before cooling. Each eruption adds another layer, and over time, often over hundreds of thousands or even millions of years, the accumulation of these flows builds a broad, dome-like mountain. The Hawaiian volcanoes are shields, and Mauna Loa, one of the most famous, is also one of the largest mountains on Earth by volume, though much of it is hidden beneath the ocean if you measure from its base on the seafloor to its summit. Mauna Loa rises more than 9 kilometres, taller than Mount Everest, though most of that height is underwater. The construction of a shield volcano is a patient process. Each lava flow might be only a metre or two thick, spreading out over several square kilometres before solidifying. Over time, hundreds or thousands of such flows stack up, each one contributing a thin layer to the edifice. The volcano grows slowly, imperceptibly from a human perspective, but steadily. Some shield volcanoes have summit calderas, large depressions at the top. formed when the summit collapses into a partially emptied magma chamber. The caldera can then become the site of future eruptions, with lava filling and refilling the depression over time. Stratovolcanoes, also called composite volcanoes, are steeper and more classically cone-shaped. They're built from many layers, strata, hence the name. These layers can include both lava flows and deposits of volcanic ash and other fragmented material. Stratovolcanoes tend to form where the magma is more viscous, often richer in silica, which doesn't flow as easily as basaltic lava. The result is steeper slopes, and a greater likelihood that eruptions will involve both flowing lava and explosive ejection of ash and rock. Many of the world's most visually striking volcanoes, Mount Fuji, Mount Rainier, Mount Vesuvius, are stratovolcanoes. They're symmetrical cones the result of countless eruptions layering material over geological time. The internal structure of a stratovolcano is complex. If you could slice one open and look at a cross-section, you'd see layers of lava flows interbedded with layers of ash, scoria, and other pyroclastic material. Some layers might be thin, representing small eruptions. Others might be thick, marking larger events. The volcano might have been built over hundreds of thousands of years, with long quiet periods between active phases. During those quiet times, erosion works to carve gullies and valleys into the flanks, only for the next eruption to fill them in again with fresh material. The competition between construction and erosion shapes the volcano's final form. Stratovolcanoes can also develop complex internal plumbing systems. Magma doesn't always rise straight up through a single central conduit. Sometimes it takes advantage of weaknesses in the rock, rising through networks of dikes and sills, sheet-like intrusions of magma that cut through or spread between existing rock layers. Some magma gets trapped in these intrusions and cools underground, never reaching the surface. Other magma finds pathways to flank vents, secondary openings partway up the volcano's slope. Over time, a stratovolcano can develop a whole system of vents, chambers, and conduits, making its behavior complex and sometimes difficult to predict. Cinder cones are smaller, simpler structures, often forming relatively quickly compared with the long construction timelines of shields and stratovolcanoes. A cinder cone builds when blobs of lava are ejected into the air during an eruption. As these fragments fly through the air, they cool and solidify before landing around the vent, piling up into a steep-sided cone of loose, fragmented rock called cinders or scoria. Cinder cones are often just a few hundred meters high and can form in a matter of months or years. They're sometimes found on the flanks of larger volcanoes, small satellite vents that opened during a particular eruptive episode. The eruptions that build cinder cones are called strombolian eruptions, named after Stromboli, a volcano in Italy that exhibits this style of activity almost continuously. The eruptions aren't usually dangerous at a distance. They're more like vigorous fountaining, with globs of molten rock arcing through the air and landing nearby. Up close, of course, being pelted with molten rock is hazardous, but from a few hundred meters away you can watch the show relatively safely. The fragments cool quickly in flight, forming a frothy, vesicle-rich rock that's full of gas bubbles. When these fragments land, they pile up loosely, building the cone. Because the material is unconsolidated, just piled up rather than welded together, cinder cones erode relatively quickly once activity stops. Rain and wind can tear them down in a few thousand years, which is fast by geological standards. Calderas are a different kind of feature altogether, not a mountain, but a depression. A caldera forms when a magma chamber beneath a volcano empties, either through a large eruption or through the magma draining away laterally. Without the support of the magma, the ground above collapses, creating a large, often circular or oval depression. Some calderas are many kilometers across. The collapse itself can be gradual or sudden, and the resulting landscape is often dramatic, a wide, relatively flat floor surrounded by steep walls. Over time, calderas can fill with water, forming lakes, or they can become the site of renewed volcanic activity if magma returns to the region. Crater Lake in Oregon occupies a caldera formed when Mount Mazama collapsed roughly 7,700 years ago. The caldera is not the result of an explosion blowing the top off the mountain, but rather the collapse following the evacuation of the magma chamber. It's a subtle but important distinction. Some calderas are associated with truly enormous eruptions. The Yellowstone caldera, for instance, formed during a massive eruption roughly 640,000 years ago that ejected more than 1,000 cubic kilometers of material. That's a volume difficult to grasp. Imagine a cube 10 kilometers on each side filled with ash and rock fragments. The eruption blanketed much of North America with ash, and the collapse created a caldera that's roughly 55 by 72 kilometers. Since then, smaller eruptions have partially filled the caldera with lava flows, and the ground continues to rise and fall as magma moves beneath the surface, though the likelihood of another super eruption in any human-relevant time frame is extremely low. Many volcanoes have summit craters, circular or irregular depressions at the top, where volcanic vents release gases, lava, or both. These craters mark the point of most recent activity, though not all eruptions happen at the summit. Flank eruptions, where magma finds a pathway to the surface partway down the volcano's slope, are also common. The summit crater is often where you'll see fumaroles, vents releasing steam and volcanic gases, a reminder that even when a volcano isn't actively erupting, the heat beneath is still present, still working its slow way toward the surface. Some craters contain small lakes, fed by rain or snowmelt, and the water can be acidic from dissolved volcanic gases. Other craters are dry, dusty places, slowly filling with windblown debris between eruptions. With the shapes of volcanoes sketched out, we can ease into the personality of lava itself, how it behaves, how it moves, what determines whether it flows like a slow river or barely creeps along before freezing in place. The key property here is viscosity, which describes how easily a fluid flows. Honey has high viscosity, it pours slowly. Water has low viscosity, it pours quickly. Lava's viscosity depends on several factors, most notably temperature and composition. Hotter magma usually flows more easily than cooler magma. Heat keeps the atoms moving, prevents them from locking together into a solid structure. As lava cools, it stiffens, becomes more resistant to flow, until eventually it stops moving altogether and solidifies into rock. Composition matters too. Magma with more silica, silicon and oxygen, the building blocks of many minerals, tends to be more viscous. Silica forms long chains and networks of molecules that tangle together, making the liquid thicker, stickier, less willing to flow. Basaltic. Magma, relatively low in silica, flows easily when hot, spreading out in broad, thin sheets. Rhyolitic magma, rich in silica, is thick and sluggish, more likely to pile up near the vent than to flow far from its source. The temperature of erupting lava varies depending on composition. Basaltic lava can erupt at temperatures around 1200 degrees Celsius. That's hot enough to make the lava glow bright orange or yellow, hot enough that you can feel the radiant heat from meters away. Rhyolitic lava, by contrast, might erupt at only 800 to 1000 degrees Celsius, still incredibly hot by everyday standards, but cooler than basalt, and that lower temperature contributes to its higher viscosity. The cooler lava is more sluggish, more prone to forming domes and short, thick flows rather than the long, fluid flows typical of basalt. When low-viscosity lava flows and cools, it can form smooth, ropey textures on its surface, patterns that look almost like frozen waves or coiled rope. This is called pahoho, a Hawaiian word that has been adopted into geological vocabulary worldwide. Pahoho forms when the surface of the flow cools just enough to form a flexible skin, which then wrinkles and folds as the still liquid lava beneath continues to move. The result is a surface that's smooth and undulating, surprisingly beautiful in its quiet patterns. You can walk on cooled pahoho relatively easily. The surface is uneven, but it's not sharp and it's mostly solid. In some places, the ropey folds are so well preserved that they look fresh even thousands of years after the eruption. Other lava, even basaltic lava, cools into rough, jagged textures called ie, another Hawaiian term. Ie forms when the lava flow is slightly cooler or moving more slowly, so the surface breaks into sharp, clinkery fragments as the flow advances. Walking on Iea is difficult. The surface is uneven, unstable, full of sharp edges that can cut through boot leather if you're not careful. The fragments are angular and brittle, piled loosely on top of each other, and they shift underfoot. Both Pahoho and Ae can come from the same eruption, the same lava source. The difference lies in cooling rate and flow conditions. A lava flow might start as Pahoho near the vent where it's hottest and flowing most freely, then transition to Ae as it cools and slows farther downstream. Lava flows cool from the outside first. The surface in contact with air loses heat more quickly than the interior, forming a solid crust while the interior remains molten. This crust acts as insulation, slowing the rate at which the interior cools. Beneath that crust, lava can continue moving for hours, days, even weeks, quietly flowing inside a self-made tube or channel. Some of these lava tubes remain intact after the eruption ends, creating natural tunnels that can stretch for kilometers. You can walk through some of them, long dark passages with smooth walls where molten rock, once flowed, now cool and silent. The floor might be flat and smooth where the last of the lava drained away, or it might be littered with collapsed debris from the ceiling. Lava tubes can be surprisingly large. Some are big enough to drive a truck through, though most are more modest, requiring you to stoop or crawl in places. The formation of a lava tube begins with a channel, a depression or pathway where lava preferentially flows. As lava continues to move through this channel, the edges and top crust over, forming a roof. The lava inside remains insulated, hot, and mobile. As long as lava continues to be supplied from the vent, it flows through the tube, sometimes for weeks or months. When the eruption finally stops, the lava drains out of the tube, leaving behind an empty tunnel. Some tubes have skylights, places where the roof has collapsed, opening a window into the tube. Others remain completely intact, their presence only revealed by subtle depressions or lineations on the surface. Some lava flows develop natural channels, pathways carved or built up over time as repeated surges of lava follow the same route down the volcano's slope. These channels act like slow rivers of rock, directing the flow and allowing lava to travel farther than it otherwise might. The edges of the channel cool and solidify, forming levees that contain the flow, while the centre remains liquid and mobile. It's a strangely orderly process, this flowing of stone, governed by the same principles of fluid dynamics that shape water flowing in a stream. The main difference is timescale and temperature. Lava flows at meters per hour or per day, not meters per second, and it's hundreds of degrees hotter than boiling water. When lava cools completely, it becomes igneous rock. Igneous, from the Latin for fire, though the process is more about cooling than burning. The specific type of igneous rock depends on composition and cooling rate. Fast cooling produces fine-grained rock or even volcanic glass like obsidian if cooling is extremely rapid. Obsidian forms when lava cools so quickly that crystals don't have time to grow. The atoms freeze in place in a disordered, glassy structure. The result is a rock that's smooth, glassy, and can be incredibly sharp when fractured. Ancient peoples used obsidian to make cutting tools, arrowheads, and blades because a freshly broken edge can be sharper than steel. Slow cooling, which usually happens when magma solidifies underground rather than at the surface, allows crystals time to grow, producing coarse-grained rock like granite. The rock records the conditions of its formation, holding information about temperature, pressure, composition, cooling history. A quiet archive of geological processes written in mineral grains and textures. Now we shift from glowing rock to the fine, dusty side of volcanoes, ash and what it becomes over time. Volcanic ash is made of tiny fragments of rock, minerals and volcanic glass, shattered and ejected during explosive eruptions. Despite the name, it's not soft or fluffy like the ash left by burning wood. Volcanic ash is hard, abrasive, made of sharp-edged particles that can damage engines, clog filters, scratch surfaces. The particles range in size from fine dust, almost too small to see, to coarser grains like sand. When fresh, ash can be grey, black, brown, reddish, depending on the minerals involved and the degree of oxidation. The formation of volcanic ash is a violent process. During an explosive eruption, magma is torn apart by rapidly expanding gases. The fragmentation is so thorough that individual mineral grains are separated, glass is shattered into tiny shards, and rock is pulverized into dust. All of this material is hurled into the air, carried upward by the force of the eruption. The finest particles can be lifted tens of kilometers into the atmosphere, while larger fragments fall back to Earth more quickly. The ash cloud, if large enough, can block out the sun, turning day to twilight and covering the landscape in a grey mantle. Ash can be carried far from its source by wind. How far depends on particle size and the altitude the ash reaches. Fine ash, ejected high into the atmosphere by a powerful eruption, can drift for hundreds or even thousands of kilometers before settling. Larger particles fall closer to the source, often within hours or days. The pattern of ash deposition creates layers, distinct horizons in the geological record that can be traced across wide areas. These layers are useful to scientists. They act as time markers, allowing correlation of deposits and events across different locations. If you find the same ash layer in two widely separated areas, you know that those two locations were both affected by the same eruption, and you can use that to establish a relative timeline. Some ash falls into the ocean, where it settles to the seafloor and becomes part of the sediment record. Deep-sea cores drilled from research vessels sometimes contain multiple ash layers, each one recording a past eruption. By analysing the chemistry of the ash and comparing it to known volcanoes, scientists can sometimes identify which volcano produced which layer, building up a history of eruptions going back millions of years. Over time, volcanic ash weathers. Rain and chemical reactions break it down, releasing minerals into the soil. This is why many volcanic regions have fertile soils. The ash contains elements like potassium, phosphorus, calcium, magnesium, nutrients that plants need. As the ash weathers, these nutrients become available, replenishing the soil in ways that constant cropping or erosion might otherwise deplete. Many of the world's most productive agricultural regions are on volcanic soils. The slopes of volcanoes in Indonesia, Central America, Italy, the Pacific Northwest. It's a quiet exchange. The mountain gives ash, time and water turn ash to soil, and plants grow thick and green where once there was only rock and heat. The weathering of volcanic ash proceeds through several stages. Initially, the fresh ash is glassy and reactive, vulnerable to chemical attack by slightly acidic rainwater. The glass dissolves slowly, releasing ions into solution. These ions can precipitate as secondary minerals, clays, zeolites, iron oxides, which gradually replace the glass. Over thousands of years, the ash layer transforms from a loose deposit of sharp particles into a consolidated layer of clay-rich soil. The transformation is slow, but it's also thorough. Eventually, you might not recognize the soil as having been ash unless you know what to look for. Volcanic soils, once stable, can support dense plant growth. Forests reclaim the slopes, grasses cover the lowlands, crops flourish in the fields. The landscape settles into a long calm period, and the memory of fire fades, though the potential remains. Old ash layers, buried and compressed, can become part of the rock record. Geologists read these layers like pages in a book, reconstructing eruption histories, understanding the frequency and scale of past events, building a picture of how a particular volcano behaves over time, spans far longer than human observation can cover. In some places, volcanic ash has been buried and compressed to the point that it's become rock, a process called lithification. The resulting rock, called tuff, is often soft and easy to carve, which is why some ancient cultures used it for building material or carved dwellings directly into tough cliffs. The tuff from the eruption that created the Yellowstone caldera, for instance, can be found across much of the western United States, a layer of volcanic rock preserving the record of that enormous event. Volcanic deposits create new landforms too. Ash and lava can fill valleys, bury old surfaces, build plains where once there were hills. Over time, erosion reshapes these deposits, carving canyons, exposing colourful layers, creating badlands or plateaus. Even after the eruptions stop, the landscape continues to change, but the pace is slow, measured in centuries and millennia rather than days or years. In deep time, volcanic material becomes part of Earth's slow recycling, the endless process of creation and destruction, burial and exhumation, melting and solidifying that has shaped the planet's surface for billions of years. Now we glide outward to a quieter truth, one that surprises many people when they first encounter it. Most of Earth's volcanic activity happens where few people ever see it, deep beneath the ocean. The seafloor is volcanically active, and in fact, a large portion of all volcanic activity on our planet occurs underwater, hidden from view, unnoticed except by the scientists who study it. Mid-ocean ridges are the largest volcanic features on Earth by length. They form a continuous system of underwater mountain ranges stretching more than 60,000 kilometers through the world's ocean basins. At these ridges, tectonic plates pull apart, and magma rises from the mantle to fill the gap. As the magma cools, it solidifies into new oceanic crust. which then spreads away from the ridge as more magma rises behind it. This process, called seafloor spreading, has been creating new ocean floor for hundreds of millions of years. The ridges themselves are not smooth or uniform. They're rugged, fractured, cut by transform faults and rift valleys, dotted with volcanic cones and fissures. But they're also remote, deep, difficult to study directly. So much of what we know comes from sonar mapping, submersible dives, and seafloor drilling. The discovery of mid-ocean ridges and seafloor spreading revolutionized geology in the mid-20th century. Before then, scientists didn't understand how continents could move or how ocean basins formed. The mapping of the seafloor, particularly the discovery that it was youngest at the ridges and progressively older, moving away from them, provided the key evidence for plate tectonics. It showed that the seafloor wasn't static but was being continuously created and destroyed, and that the ocean basins were relatively young features geologically speaking. The oldest seafloor is only about 200 million years old, ancient by human standards but young compared to continental rocks that can be billions of years old. When lava erupts underwater, it behaves differently than it does on land. The surrounding water is cold, near freezing in the deep ocean, and it cools the lava very rapidly. This rapid cooling can produce distinctive forms, particularly pillow lava. Pillow lava forms when the surface of a lava flow chills almost instantly upon contact with water, creating a glassy rind. The pressure of the still molten lava inside breaks through the rind, forming a new lobe that also chills rapidly, and the process repeats. The result is a pile of rounded, pillow-like shapes stacked and tumbled together, each one a snapshot of a moment when lava met water and froze. Pillow lavas are common along mid-ocean ridges and wherever underwater eruptions occur. Each pillow is typically a few tens of centimetres to a metre across, with a smooth, glassy outer skin and a more crystalline interior. If you cut one open, you can see radial cooling cracks and sometimes concentric layers that record the cooling history. Pillow lavas are so distinctive that geologists use them as an indicator of underwater eruption. When you find ancient pillow lavas now exposed on land, you know that those rocks formed beneath the sea and were later uplifted. Seamounts are underwater volcanic mountains. They rise from the ocean floor, sometimes reaching heights of several kilometres, though they don't break the surface. There are tens of thousands of seamounts scattered across the ocean basins, most of them extinct volcanoes, remnants of past activity. Some seamounts grow high enough to become islands. When a volcano builds from the seafloor and finally emerges above the waves, it becomes an island, a volcanic island, built entirely from erupted material. The Hawaiian Islands, Iceland, the Galapagos, the Azores, all are volcanic islands, mountains of lava and ash that happen to reach above sea level. Volcanic islands build slowly, through repeated eruptions over long periods of time. Each eruption adds material, raising the summit a little higher, expanding the island's footprint. Between eruptions, erosion works to tear the island down. Waves undercut the coasts, rain carves gullies, landslides strip away loose material. The balance between construction and destruction determines whether an island grows or shrinks. Young, active volcanic islands like the Big Island of Hawaii are still growing, their volcanoes adding new land faster than erosion can remove it. Older islands, no longer supplied with new lava, gradually erode away, sinking slowly as the seafloor beneath them cools and subsides. Eventually, millions of years after their volcanic fires go out, they may disappear beneath the waves entirely, becoming seamounts once more, completing a long geological cycle. The process of island subsidence is gradual but relentless. As new oceanic crust forms at a mid-ocean ridge, it's hot and buoyant, riding high. But as it moves away from the ridge, it cools, contracts, and becomes denser, causing the seafloor to sink. A volcanic island sitting on that seafloor sinks along with it. Over millions of years, an island can subside by hundreds or even thousands of meters. Some islands that once stood high above the waves are now flat-topped seamounts called guyots, their summits planed off by wave erosion when they were at sea level, then carried beneath the surface as the seafloor sank. Coral reefs can grow around volcanic islands, forming fringing reefs in shallow water near shore. As the island subsides, the reef continues to grow upward, keeping pace with the sinking land, and eventually the island can disappear entirely, leaving behind a ring of coral, an atoll. Charles Darwin proposed this mechanism for atoll formation in the 19th century, long before anyone had direct evidence for seafloor subsidence, and it turned out to be essentially correct. Drilling through atolls has confirmed that beneath the coral lies volcanic rock, the remnant of the island that once stood there. Hydrothermal vents often occur in volcanically active regions on the seafloor. These vents form where seawater seeps down through fractures in the crust, encounters hot rock or magma, becomes heated, and then rises back up, emerging as a jet of superheated, mineral-rich water. The temperature of the water can exceed 300 degrees Celsius, hot enough to melt lead, yet it doesn't boil because the pressure at depth is so great. When this hot water meets the cold ocean, dissolved minerals precipitate out, forming chimneys and mounds around the vent. Some of these structures, called black smokers, emit clouds of dark, mineral-laden water that look like smoke rising from a chimney. Others, white smokers, emit lighter-coloured fluids rich in different minerals. These vents support unique ecosystems, communities of bacteria, tube worms, clams, crabs, and other organisms that thrive in the heat and chemical richness, independent of sunlight, deriving energy from the chemicals in the vent fluids rather than from photosynthesis. It's a reminder that life finds a way, even in places that seem utterly inhospitable. The discovery of these vent communities in the late 1970s was a revelation. Before then, scientists assumed that all ecosystems ultimately depended on sunlight, that photosynthesis by plants or algae was the foundation of all food chains. But the vent communities proved otherwise. The bacteria at the base of these ecosystems use chemical energy from hydrogen sulfide and other compounds in the vent fluids, a process called chemosynthesis. The tube, worms, which can grow to lengths of more than a metre, have no digestive system. They host symbiotic bacteria in their tissues and rely entirely on the bacteria for nutrition. It's an alien world, in a sense, operating on completely different principles from the sunlit surface ecosystems we're familiar with. From the deep ocean, where volcanoes work in darkness and cold, we move into the quiet science of noticing them. How scientists monitor volcanoes, listening for changes, watching for signs of unrest, trying to understand what the volcano might do next. This work is patient, methodical, built on careful observation and the recognition of patterns over time. Seismometers are one of the primary tools for monitoring volcanoes. These sensitive instruments detect and record vibrations in the ground, including the small earthquakes that often accompany volcanic activity. When magma moves underground, it fractures rock, creating seismic signals. When fluids or gases flow through cracks and conduits, they can generate a kind of continuous tremor. By placing seismometers around a volcano and recording the earthquakes they detect, scientists can begin to understand where magma is moving, how fast it's rising, whether the activity is increasing or decreasing. Not every earthquake means an eruption is imminent. Volcanoes experience earthquakes all the time, and most of them lead nowhere. But changes in the pattern, frequency, or depth of earthquakes can be significant. It's about context, about seeing shifts in the baseline. Modern seismometers are remarkably sensitive. They can detect ground motions smaller than the width of an atom, vibrations that would be completely imperceptible to a person standing next to the instrument. This sensitivity allows them to pick up the faint signals of magma moving several kilometers beneath the surface, or the subtle tremor associated with gas escaping through fractures. By analysing the seismic waves, their frequency, amplitude, and arrival times at different stations, scientists can locate the source of the activity and sometimes infer what kind of process is producing it. Scientists also measure ground deformation, tiny swelling or sinking of the volcano's surface. When magma accumulates in a chamber beneath a volcano, it takes up space, and that can cause the ground above to bulge upward, sometimes by just a few centimeters, sometimes by meters, depending on the volume of magma and the depth of the chamber. When magma drains away or an eruption relieves pressure, the ground can subside. These movements are often too small and too slow to notice without instruments, but they're measurable. GPS stations placed around a volcano can detect changes in position with millimeter precision, tracking the slow inflation and deflation of the volcanic edifice. Satellite radar can map ground movement across wide areas, using a technique called interferometry that compares radar images taken at different times. The result is a detailed picture of how the surface is deforming, which in turn tells scientists something about what's happening below. Interferometric synthetic aperture radar, or INSAR, has become an invaluable tool for volcano monitoring. A satellite passes over a volcano repeatedly, sending down radar pulses and recording the reflections. By comparing the phase of the radar waves in images taken weeks or months apart, scientists can detect ground movements of just a few millimeters. The technique works even in remote areas, even through clouds, and it can cover entire volcanic regions in a single image. The data appears as colourful interference patterns called interferograms, where each colour cycle represents a certain amount of ground movement. Interpreting these patterns requires care, but they provide a synoptic view that would be impossible to achieve with ground-based instruments alone. Volcanoes release gases, water vapour, carbon dioxide, sulfur dioxide, hydrogen sulfide, and others, and the composition and quantity of these gases can provide clues about magma depth and movement. As magma rises, pressure decreases, and gases come out of solution, rising ahead of the magma itself. An increase in sulfur dioxide emissions, for instance, might suggest that fresh magma is approaching the surface. Scientists collect gas samples directly from fumaroles and measure gas concentrations in the air downwind from the volcano. Some monitoring stations use spectrometers to measure gases remotely, even from aircraft or satellites, tracking how emissions change over time. Gas monitoring isn't a perfect predictor. Gases can migrate through complex fracture networks, and the relationship between gas release and eruption isn't always straightforward, but it's another piece of the puzzle, another line of evidence. Different gases provide different information. Water vapour is the most abundant volcanic gas, but it's also ubiquitous in the atmosphere, so it's hard to use as a monitoring tool. Carbon dioxide is less abundant in air, and it can escape from deeper in the volcanic system than other gases, so changes in CO2 emissions can sometimes signal deep magma movement before other indicators appear. Sulfur dioxide is particularly useful because it's relatively rare in the atmosphere, and it's released in large quantities when magma degasses. Satellite instruments can measure sulfur dioxide plumes from space, tracking how much gas a volcano is releasing even if there's no access to the summit. Thermal sensors detect warming near vents and fissures. Increased heat flow can indicate rising magma or increased circulation of hot fluids. Infrared cameras, either ground-based or mounted on aircraft and satellites, can map temperature variations across a volcano's surface. A new hotspot, or a gradual warming of a crater floor, might signal changing conditions below. Thermal monitoring is especially useful for volcanoes that are difficult to access on foot, or for tracking changes over large areas. Many regions with active volcanoes have dedicated volcano observatories, institutions where scientists work full-time to monitor and study the local volcanoes. These observatories maintain networks of instruments, collect and analyze data, assess hazards, and provide information to emergency managers and the public. The work is long-term, often spanning decades. Volcanic unrest can last for months or years without leading to an eruption, and understanding what's normal for a particular volcano requires years of baseline data. Monitoring is about pattern recognition, about detecting the subtle shifts that might indicate an approaching eruption, and about being patient enough to watch and wait even when nothing dramatic is happening. The Hawaiian Volcano Observatory, established in 1912, is one of the oldest continuously operating volcano observatories in the world. For more than a century, scientists there have been monitoring Kilauea and Mauna Loa, building up an unparalleled record of volcanic activity. That long baseline allows them to understand the nuances of how these volcanoes behave, to recognize the early signs of an eruption, and to provide timely warnings. Other observatories around the world, in Japan, Italy, Indonesia, the Philippines, Alaska, and elsewhere, perform similar work, each one tailored to the specific volcanoes in their region. With that calm, attentive framework of monitoring in place, we can gently explore eruption styles, the range of behaviours a volcano might display when it does become active. There's no need to focus on fear or destruction here, just the physical processes, the ways in which magma, gas, and rock interact to produce different kinds of eruptions. Some eruptions are slow lava effusions rather than explosive events. Lava simply flows out of a vent or fissure, spreading across the ground, cooling as it goes. These effusive eruptions are common with low-viscosity basaltic magma and can continue for weeks, months, even years. The lava doesn't shoot into the air, it oozes, creeps, advances at a pace you could walk away from. It might destroy structures in its path by burying them, but it rarely poses a direct threat to human life because it moves slowly enough for people to evacuate. The 2018 eruption of Kilauea in Hawaii was largely effusive. Lava erupted from fissures in the Lower East Rift Zone, sending flows downslope toward the ocean. The flows were spectacular. Rivers of molten rock glowing orange in the darkness, advancing across roads and through forests, entering the sea in great clouds of steam. But they moved slowly, typically just hundreds of meters per day, giving people time to leave. The eruption lasted for months, eventually covering more than 30 square kilometers with new lava and destroying hundreds of homes. Yet the loss of life was minimal because the advance of the lava was predictable and slow. Eruption style depends partly on viscosity and gas content. High viscosity magma doesn't flow easily, and if it contains a lot of dissolved gas, pressure can build until the magma fragments explosively, shattering into ash and rock. This is how explosive eruptions happen. The gas expands rapidly as pressure drops, tearing the magma apart and propelling fragments into the air. The violence of the explosion depends on how much gas is present, how viscous the magma is, and how quickly the pressure is released. Some explosive eruptions are relatively modest, sending ash and rock a few hundred meters into the air. Others are far more powerful, creating eruption columns that reach tens of kilometers into the stratosphere. Water interacting with hot magma can create steam-driven eruptions, also called phreatic eruptions. If groundwater or surface water comes into contact with magma or very hot rock, it can flash to steam almost instantaneously. The rapid expansion of water turning to steam is incredibly energetic, and it can fragment rock and eject material even if no fresh magma is involved. These eruptions tend to be sudden and difficult to predict because they depend on water availability and subsurface conditions that can change quickly. Phreatic eruptions are often the first sign of renewed volcanic activity. As magma rises beneath a volcano, it heats the surrounding rock and any groundwater present. The heated water can boil and flash to steam, causing small explosions that eject old rock from the vent. These explosions can create craters and eject debris, but they don't involve fresh magma. If magma continues to rise and eventually reaches the surface, the eruption can transition from phreatic to magmatic, with molten rock joining the ash and steam. A volcanic plume is a rising column of ash, gas, and sometimes larger rock fragments ejected during an eruption. The plume rises because it's hot and less dense than the surrounding air. As it rises, it cools, and eventually it reaches a height where it's no longer buoyant. At that point, the plume spreads laterally, forming a mushroom-shaped cloud. Plumes vary widely in size and duration. Some are modest, rising just a few kilometers and lasting minutes or hours. Others are enormous, sustained for hours or days, reaching well into the stratosphere. The height a plume reaches affects how far ash can travel. Higher plumes inject ash into upper-level winds that can carry it around the globe. The 1991 eruption of Mount Pinatubo in the Philippines produced one of the largest volcanic plumes of the 20th century. The eruption column reached more than 35 kilometers into the atmosphere, well into the stratosphere. The ash and aerosols spread around the world, reflecting sunlight and causing measurable global cooling for several years. The eruption itself was powerful, but because scientists had successfully predicted it and evacuated tens of thousands of people from the area, the loss of life was relatively limited. It was a triumph for volcano monitoring and hazard communication. Volcanic lightning can occur within an eruption plume. As ash particles collide with each other during the explosive ejection, they can build up electrical charge through friction. When the charge difference becomes large enough, it discharges as lightning. The result is dramatic. Bright flashes and arcs of electricity within the dark ash cloud, lighting it from within. It's a phenomenon that photographers love, but it's just physics, the same process that creates lightning in a thunderstorm, playing out in the chaotic environment of an eruption column. The lightning can occur within the plume, between the plume and the ground, or even between different parts of the plume as charge separates. The ash particles act like the ice crystals in a thunderstorm, colliding and transferring charge until the electrical potential is large enough to overcome the resistance of the air. The discharges can be frequent during vigorous eruptions, creating almost continuous lightning within the ash cloud. Lava domes form when thick, viscous lava piles up near a vent rather than flowing away. The lava is too stiff to spread, so it mounds up, growing slowly as more lava is extruded from below. Domes can grow for months or years, adding material little by little. The outer surface cools and solidifies, but the interior remains hot and somewhat mobile. As the dome grows, the solid carapace can fracture and shed blocks of rock, or the dome can partially collapse, sending avalanches of hot rock and ash down the volcano's slopes. Despite the potential for sudden collapses, dome growth itself is usually a slow process, one that can be monitored and studied over time. The dome growing at Mount St. Helens after the 2004 eruption provides a good example. The dome grew slowly and episodically, with periods of active growth separated by pauses. At times, fresh lava would push up through the centre of the dome, tilting and fracturing the older, cooler rock. At other times, the dome would simply sit there, steaming and cooling. Scientists were able to monitor the growth closely, measuring the deformation, tracking the seismicity, and assessing the hazards. The growth continued for several years, eventually building a dome hundreds of meters high within the crater left by the catastrophic 1980 eruption. Even energetic eruptions follow consistent physical rules. The explosions, the ash clouds, the flows of lava, all of these are expressions of thermodynamics, fluid dynamics, material properties. There's no mystery here, no supernatural force, just heat, pressure, chemistry, and the behavior of matter under extreme conditions. Understanding these rules allows scientists to make sense of what they observe, to compare different eruptions, to develop models that can, in some cases, help predict future behavior. Now we zoom out to the planetary scale, considering how volcanoes fit into Earth's long, steady cycles, how they're part of the larger system that keeps our planet geologically active, that recycles crust and mantle, that shapes landscapes and influences climate over deep time. Volcanism is intimately linked to plate tectonics, the slow movement of Earth's lithospheric plates. Plate motion is driven by mantle convection, the gradual flow of warm, slowly deforming rock in the mantle. Hot material rises, cooler material sinks, and this circulation, operating over millions of years, drags the plates along. At convergent boundaries, where plates collide, one plate descends into the mantle in subduction zones. This process recycles oceanic crust back into the mantle, taking with it sediments, water, and altered minerals. Eventually, much of that material will be melted and brought back to the surface through volcanic eruptions, completing a cycle that can take hundreds of millions of years. The recycling is not perfect or complete. Some material gets carried deep into the mantle, and may remain there for a very long time before being incorporated into rising plumes or mantle currents. Other material is returned to the surface relatively quickly. The system is complex with multiple pathways and timescales, but the overall result is that material circulates between the surface and the deep interior, mixing and being transformed along the way. Volcanoes are one surface expression of this deep recycling. They bring material from the mantle to the crust, releasing heat, building new land, contributing gases to the atmosphere. Over Earth's history, volcanism has played a significant role in shaping the atmosphere. Early in Earth's history, volcanic outgassing likely contributed much of the water vapour, carbon dioxide, nitrogen, and other gases that formed the early atmosphere. Over time, these gases helped create conditions suitable for liquid water and eventually for life. Even today, volcanoes release gases that become part of the atmospheric mix, though in much smaller quantities compared to the planet's early days. The early Earth was a very different place. The atmosphere was likely dominated by carbon dioxide and water vapour, with little or no free oxygen. Volcanic outgassing was intense, as the young planet was much more geologically active than it is today. Over billions of years, the carbon dioxide was gradually sequestered in rocks through weathering and precipitation of carbonate minerals, and oxygen levels rose as photosynthetic organisms evolved and spread. The atmosphere we have now, rich in nitrogen and oxygen, with only trace amounts of carbon dioxide, is the result of billions of years of geological and biological processes working together. Volcanic rocks create new crust when they cool and solidify. At mid-ocean ridges, basaltic lava forms the ocean floor, adding new crust at a rate of a few centimetres per year along each side of the ridge. On land, volcanic eruptions can build islands, thicken continental crust, create plateaus. The Deccan traps in India, the Siberian traps in Russia, the Columbia River basalts in the Pacific Northwest. These are examples of flood basalts, enormous outpourings of lava that covered vast areas, in some cases millions of square kilometres, with layer upon layer of solidified lava. These events occurred over geologically brief periods, typically a few million years, and they represent some of the largest volcanic events in Earth's history. The Siberian Traps eruption, which occurred roughly 250 million years ago, coincided with the Permian-Triassic mass extinction, the most severe extinction event in Earth's history. More than 90% of marine species and 70% of terrestrial vertebrate species went extinct. The exact causal mechanisms are still debated, but it's likely that the massive release of volcanic gases, carbon dioxide, sulfur dioxide and others, triggered severe climate changes and ocean acidification. The eruption lasted for perhaps 1 million years or more, releasing enough lava to cover an area the size of Europe with layers of basalt kilometres thick. It's a reminder that volcanic eruptions, while usually local or regional phenomena, can sometimes have global consequences. Some volcanic aerosols, tiny particles and droplets, can reach high into the atmosphere and reflect sunlight, temporarily cooling Earth's surface. When a volcano injects large amounts of sulfur dioxide into the stratosphere, the gas reacts with water vapour to form sulfate aerosol particles. These particles are reflective and can remain aloft for months, or even a few years before settling out. During that time, they scatter incoming sunlight, reducing the amount of solar radiation that reaches the surface. The effect is measurable. Large eruptions in the past have caused temporary global cooling of a degree or more. But the particles eventually settle, the air clears, and temperatures return to their previous levels. It's a temporary perturbation, not a permanent change, though it can have significant short-term effects on weather and climate. The 1815 eruption of Mount Tambora in Indonesia was one of the most powerful eruptions in recorded history. It injected massive amounts of sulfur dioxide into the stratosphere, and the resulting aerosol clouds circled the globe. The year 1816 became known as the Year Without a Summer in parts of Europe and North America. Temperatures dropped, crops failed, and there were widespread food shortages. The cooling lasted for several years before the aerosol settled out and normal conditions returned. It's a sobering example of how a single volcanic eruption, however distant, can affect people on the other side of the world. Over geological time, Earth's surface changes gradually through countless small steps. Mountains rise and erode, continents drift, ocean basins open and close. Volcanoes are part of this ongoing transformation, adding material here, releasing heat, there, reshaping the land in episodes separated by long intervals of quiet. Earth stays dynamically active, constantly adjusting, constantly in motion, without any need to hurry. The pace is set by the slow convection of the mantle, by the steady decay of radioactive elements, by processes that operate on timescales so long they make human history seem vanishingly brief. And now we return to the bedside scale, to the quiet room, to the stillness of the night. We've travelled from the deep mantle to the ocean floor, from lava tubes to eruption plumes, from monitoring instruments to planetary cycles. Now we bring it all back to something simple and immediate. The ground beneath you, the warmth deep below, the patient work of a planet that never truly sleeps but never rushes either. Most nights the ground beneath you feels completely still. You lie in bed and there's no sense of motion, no vibration, no sign of the immense forces at work far below, and yet beneath the crust, heat moves slowly through solid rock. It doesn't race or surge. It diffuses, spreading outward at a pace determined by the thermal properties of the rock. This is conduction, the slow transfer of heat from warmer regions to cooler ones, atom by atom, grain by grain. It's so gradual that you could watch for a lifetime and never see a change, yet over millions of years it reshapes the planet. Mantle convection is the long-term flow of warm material deep inside Earth. The rock in the mantle is solid, not liquid, but at the temperatures and pressures found there, over geological time, it behaves like a very slow fluid. Warmer rock rises, cooler rock sinks, and the circulation continues, driven by the heat coming from the core and from radioactive decay in the mantle itself. This convection is what drives plate tectonics, what causes the slow drift of continents, what brings magma to the surface at mid-ocean ridges and subduction zones. It's the engine beneath everything we've been. discussing, and it operates on a timescale so vast that it's almost impossible to truly comprehend. The mantle convects at a rate of perhaps a few centimetres per year, similar to the rate plates move, because the two are linked. Over millions of years, that slow circulation has mixed the mantle, redistributed heat, controlled the planet's thermal evolution. Volcanoes are one way Earth releases heat without constant surface disturbance. Instead of the entire surface being molten, instead of heat escaping everywhere at once, it's concentrated at specific points, plate boundaries, hotspots, rifts. This allows much of the surface to remain cool, solid, stable, while heat is efficiently vented through these relatively narrow channels. It's an elegant system, a balance between the need to lose heat and the need to maintain a solid surface capable of supporting complex geology, oceans, atmospheres, life. Many volcanic landscapes, after the eruptions end, become peaceful places. Forests grow back. Rivers return to their old courses or carve new ones through the fresh rock. Animals recolonize. The evidence of past violence, the ash, the lava flows, becomes substrate for new ecosystems. Lava becomes rock, hard and dark, providing raw material for soil formation. Rock weathers under the patient assault of water, air and living organisms, breaking down into minerals and particles. Those particles mix with organic matter, leaves, roots, fungi, bacteria, and become soil. Soil supports plants, plants support animals, and the landscape transforms from barren volcanic wasteland to thriving ecosystem. The timescale varies. Sometimes it takes decades, sometimes centuries, but the pattern repeats across volcanic regions worldwide. Life is resilient, opportunistic, good at finding footholds in the most unlikely places. Geological time is vast, vaster than most people ever pause to consider. 1,000,000 years is a comprehensible number, but it's incomprehensible as a duration. It's long enough for mountains to rise and erode away, for species to evolve and go extinct, for continents to drift thousands of kilometres. And Earth's history encompasses not 1,000,000 years, but 4.5 billion. 4,500 million years, a span so long that the entire history of human civilization, all of recorded history, all of the rise of agriculture and cities and technology, is a blink at the very end. Against that backdrop, most geological change feels gentle and gradual. There are sudden events, to be sure, earthquakes, volcanic eruptions, asteroid impacts, but even these are brief punctuations in a much longer, slower narrative. The dominant mode is patience. Tonight, you can borrow that patience. You can let your thoughts cool and settle like lava solidifying into stone. There's no need to hold on to anything, no need to worry or plan or remember. The facts about volcanoes, the mechanisms of eruption, the slow dance of plates they've passed through your awareness, and whether you recall them tomorrow or not doesn't matter. They're part of the planet's story, not yours to carry. You can set them down and let them rest. Earth continues its quiet heat cycle. Deep below, radioactive elements decay, releasing warmth. The core remains molten, convecting slowly, generating the magnetic field that shields the planet from solar radiation. The mantle circulates, rising here, sinking there, moving plates, building mountains, creating volcanoes. The surface receives sunlight, radiates heat back to space, weathers and erodes, shifts and changes. It's a system in dynamic balance, not static but stable, capable of sustaining itself over billions of years. And you, right now, in this moment, are resting on the surface of that system, safe, supported, part of the same planet that builds volcanoes and recycles crust, and releases heat through vents and fissures scattered across the globe. The planet is doing its long work, the work of geology, the work of deep time. It doesn't need your help or your attention. It will continue regardless, patient and inexorable. And you're allowed to do the simplest work of all, the work of resting, of breathing, of letting your body and mind settle into the quiet that the night offers. The ground beneath you is still, the air around you is calm. The distant fires of Earth's interior are banked and slow, working their way upward grain by grain, century by century, asking nothing of you. You can close your eyes and let the weight of your body sink into the bed, trusting that the surface will hold you, that the crust beneath is solid, that the cycles of heat and rock and time will carry on without you needing to tend them. Sleep is its own kind of geology. A slow process, a settling, a release of the day's accumulated tension. Like lava cooling into stone, your thoughts can slow and solidify, your awareness can dim and fade, until you drift into the dark and quiet space where rest lives. The planet turns, the mantle convects, the heat rises, the crust holds, and you, safe in the stillness of the night, can let go and sleep. The next story is about to begin. Please relax and enjoy. Rain is liquid water falling from clouds to the ground. It's one of the most familiar things in nature, and yet when you pause to think about it, even this simple phenomenon is full of quiet complexity. Rain is part of the water cycle, that constant movement of water around Earth, from ocean to sky, from sky to land, and back again in loops that have been running for billions of years. Every raindrop you see has been somewhere else before. It has cycled through rivers, oceans, soil, plants, clouds, and now it falls again, repeating an ancient pattern that connects everything on the planet in a web of moisture and motion. Rain begins with water vapor, which is invisible. You can't see it in the air around you, even though it's there, mixed in with nitrogen and oxygen and all the other gases that make up our atmosphere. Water vapor is just water in its gaseous form, molecules moving freely, bouncing around, unattached to one another. It forms when liquid water evaporates, when the sun warms the ocean, or when moisture lifts from a lake, or when a wet street dries after a storm. The energy from heat allows water molecules to break free from the liquid and drift into the air as vapor. This vapor is light, it rises, it spreads, and it waits. The waiting is important in its way. Water vapor can linger in the atmosphere for days or even weeks, traveling with the wind, mixing with other air masses, moving across continents and oceans. During this time, the vapor is just one component of the air, invisible and unremarkable to anyone breathing it. But it carries with it the potential for rain, stored energy in the form of latent heat, moisture that will eventually return to the surface in one form or another. The atmosphere holds an enormous amount of water at any given moment. If all of it condensed and fell at once, it would cover the Earth's surface with about an inch of water. But it doesn't fall all at once. It falls gradually in specific places when conditions are right. The next step happens when air cools enough. Water vapor becomes droplets when air reaches a temperature where it can no longer hold all that invisible moisture. This temperature is called the dew point. Cooling to the dew point allows condensation to happen. Condensation is the opposite of evaporation. It's when water vapor turns back into liquid. But here's something interesting. Condensation doesn't usually happen all by itself, even when the air is cool enough. The vapor needs a little help. It needs something to gather on, something to give it a starting point. That's where condensation nuclei come in. Condensation usually needs tiny particles called condensation nuclei, and these particles are everywhere. They can be dust, sea salt, smoke, or pollen. They can be microscopic fragments of soil kicked up by wind, or tiny crystals of salt left behind when ocean spray evaporates, or particles released by factories and cars, or even bits of organic material from trees and plants. These nuclei are so small you'd never notice them, but they're floating all around you, thousands and thousands of them in every breath of air. When water vapor encounters one of these particles and the air is cool enough, the vapor begins to stick to it. A droplet starts to form, molecule by molecule, building up around the nucleus like a tiny shell of liquid. The process of a droplet forming on a nucleus is surprisingly delicate. The nucleus provides a surface, a place where water molecules can gather more easily than they could in empty air. Without the nucleus, water molecules would have to spontaneously cluster together, which requires much more cooling. Air would have to be supersaturated, cooled well below the dew point before droplets would form. But with nuclei present, condensation can happen right at the dew point, or even slightly before. The nucleus acts like a seed, a foundation on which the droplet can grow. Different types of nuclei work with different levels of efficiency. Sea salt particles are particularly good at attracting water, because salt is hygroscopic. It absorbs moisture readily. Some particles are less effective, but even a speck of dust can work if the air is cool and moist enough. Cloud droplets start extremely small. We're talking about droplets that are only 10 or 20 micrometers across, far smaller than the period at the end of this sentence. They're so light that they can float in the air, held aloft by even the gentlest upward motion in the atmosphere. A cloud is really just a collection of billions of these droplets, all suspended together, drifting and shifting. From the ground, a cloud looks solid, but if you could walk through one, you'd just feel a cool mist. Each droplet is separate, floating in space, too small and too light to fall. When you see a cloud, you're seeing the collective effect of countless tiny droplets scattering sunlight. Each droplet acts like a tiny lens or mirror, bouncing light in different directions. White clouds are white because they scatter all wavelengths of visible light roughly equally. Darker clouds appear dark because they're thick enough that light can't penetrate all the way through them. The base of the cloud is in shadow. But whether a cloud is white, grey or nearly black, the droplets inside it are all transparent. The colour is an optical effect, a result of light interacting with vast numbers of droplets. But many droplets must grow before they can fall as rain. The challenge is that these tiny cloud droplets are in a kind of equilibrium. They're small enough that they don't fall, but they're also not growing much just by sitting there. For rain to happen, droplets need to get much bigger, hundreds of times bigger. They need to become heavy enough that gravity can pull them down through the air, even against the upward currents and the drag of the atmosphere. Rain happens when droplets become heavy enough to overcome rising air and drag, and there are a few different ways this growth can happen depending on the type of cloud and the conditions inside it. One common way droplets grow is by colliding and merging. This is called collision coalescence. Imagine millions of tiny droplets all drifting around inside a cloud. Some are moving up, carried by rising air. Some are starting to fall because they're slightly bigger. As they move, they bump into each other. When two droplets collide, they can merge into one larger droplet. That larger droplet is now a bit heavier, so it falls a little faster, and as it falls, it collides with even more droplets on the way down. Each collision adds more water, and the droplet grows. In warm clouds where the temperature is above freezing all the way through, this process can make raindrops efficiently. The droplets don't need to freeze. They just keep colliding and growing until they're big enough to fall all the way to the ground. The efficiency of collision coalescence depends on several factors. Droplet size is important. If all the droplets are exactly the same size, they'll all fall at the same speed, and they won't collide as often. But in real clouds, there's always a range of droplet sizes, and this creates different fall speeds, which creates more collisions. The strength of the updraft matters too. Strong updrafts keep droplets suspended longer, giving them more time to collide and grow before they fall out of the cloud. The concentration of droplets also plays a role. More droplets mean more potential collisions. In maritime clouds over the ocean, where condensation nuclei are less abundant and droplets tend to be larger on average, collision coalescence can produce rain quite quickly. In continental clouds over land, where there are more nuclei and droplets tend to be smaller, the process can take longer. In colder clouds, ice can help form precipitation too. When temperatures inside a cloud drop below freezing, ice crystals can start to form. These crystals are different from liquid droplets. They have a different structure, and they interact with water vapour in a special way. Ice crystals can grow by collecting water vapour directly from the air around them. Water vapour molecules can stick to the surface of an ice crystal and freeze onto it, adding layer after layer. This is called vapour deposition, and it can make ice crystals grow much faster than liquid droplets can grow by condensation alone. The reason ice crystals grow so efficiently has to do with a subtle difference in saturation. At the same temperature below freezing, the saturation vapour pressure over ice is slightly lower than the saturation vapour pressure over liquid water. This means that in a cloud containing both ice crystals and supercooled water droplets that are still liquid even though they're below freezing, the air can be saturated with respect to the water droplets but supersaturated with respect to the ice crystals. In this situation, water vapour will preferentially deposit onto the ice crystals and the crystals will grow rapidly. Meanwhile, the supercooled droplets might actually evaporate slightly to maintain equilibrium. This process, called the Bergeron process or the ice crystal process, is very important for precipitation formation in clouds that extend up into freezing temperatures. Ice crystals can also collide with droplets and other crystals. When an ice crystal bumps into a supercooled droplet, a droplet that's still liquid even though it's colder than freezing, the droplet can freeze onto the crystal instantly. This process, called riming, can make the crystal heavier and more complex in shape. Rimed crystals can look like small pellets of ice, completely coated in frozen droplets. Crystals can also collide with each other and stick together, forming larger clumps of ice called aggregates. Snowflakes are often aggregates, clusters of many individual ice crystals that have joined together during their fall. All of these processes help ice particles grow inside cold clouds, and when they get heavy enough, they start to fall. When ice falls into warmer air, it can melt into raindrops. As an ice crystal or snowflake falls from the cold upper parts of a cloud into the warmer air below, it begins to melt. The ice turns back into liquid water, and what reaches the ground is rain, not snow. This is actually how a lot of rain forms, even in the summer. The precipitation starts as ice high up in the cloud, then melts on the way down. So even on a warm day, the rain that falls on you may have been frozen just a few minutes earlier, thousands of feet above your head. The melting level, or freezing level, is an important boundary in the atmosphere. It's the altitude where the temperature is 0 degrees Celsius. Above this level, precipitation is likely to be frozen. Below it, precipitation is likely to be liquid. In winter, the freezing level can be quite low, sometimes even at ground level, which is when you get snow instead of rain. In summer, the freezing level is much higher, often several kilometers up, so precipitation melts long before it reaches the surface. Weather forecasters pay close attention to the height of the freezing level because it determines what type of precipitation will fall. Rain can fall from clouds that look dark or clouds that look gentle and grey. The colour of a cloud doesn't always tell you whether it's raining. A thick, dark cloud is often dark because it's very deep and blocks a lot of sunlight, and deep clouds often produce rain because there's more space for droplets to grow. But even a thin grey cloud can produce drizzle if the conditions are right. The darkness is about thickness and light, not always about rain itself. Rain often begins high above you and finishes its fall near the ground. The journey of a raindrop from cloud to earth can take minutes, depending on how high the cloud is and how big the drop is. During that fall, the drop is moving through different layers of air, each with its own temperature, humidity and wind. The drop might shrink a bit if it's falling through dry air and some of it evaporates. It might grow a bit if it's falling through a humid layer and collecting more moisture. It's a dynamic process, and every raindrop's journey is slightly different. A raindrop falling from a typical cumulus cloud might travel 2 or 3 kilometers before hitting the ground. If it's a small drop, falling at perhaps 2 meters per second, that journey could take 15 or 20 minutes. A larger drop, falling at 7 or 8 meters per second, might make the trip in just a few minutes. During that time, the drop is subject to all sorts of influences. It might pass through a layer where the temperature changes, affecting its evaporation rate. It might encounter wind shear, where the wind speed or direction changes with altitude, causing the drop to drift sideways. It might even collide with other drops on the way down, growing slightly larger. By the time it reaches you, it has travelled through a complex, ever-changing environment. Not every cloud makes rain, even if it looks thick. Some clouds just don't have the right conditions. Maybe the air isn't lifting strongly enough to keep the process going. Maybe the droplets never grow large enough. Maybe the cloud dissipates before precipitation can develop. Clouds are constantly forming and dissolving, and only some of them produce rain. That's why you can see a sky full of clouds on some days, and still not feel a single drop. There are fair weather cumulus clouds, for instance, puffy white clouds that form on sunny afternoons. They look substantial, and they might contain millions of droplets, but they rarely produce rain. The updrafts inside them aren't strong enough or long-lasting enough to allow droplets to grow to raindrop size. The clouds might only last for half an hour before they evaporate away. They're part of the atmosphere's constant churning, visible signs of convection, but they don't lead to precipitation. Only when conditions are more vigorous, when there's more moisture, more instability, stronger lifting, do clouds develop into rain producers. Raindrops are not shaped like teardrops as they fall. This is one of those common misconceptions that shows up in drawings and cartoons. But it's not how raindrops actually look. Small raindrops are often close to spherical. Surface tension, the force that pulls water molecules together, tries to make the drop into a sphere, the shape with the smallest surface area for a given volume. For very small drops, this works well, and they fall through the air as little round beads. Surface tension is a fascinating property of water. It arises because water molecules are attracted to each other through hydrogen bonding. At the surface of a water drop, molecules are pulled inward by the molecules beneath them, creating a kind of skin that tries to minimize the surface area. This is why water forms droplets in the first place rather than just spreading out into a shapeless blob. The surface tension is strong enough to hold small drops in a spherical shape even as they're falling and encountering air resistance. Larger raindrops can flatten slightly on the bottom. As a raindrop falls, it's pushing through the air and the air pushes back. Air resistance pushes on the falling drop's underside, and this pressure can deform the drop. Instead of a perfect sphere, a larger raindrop might look more like a small hamburger bun, rounded on top, flatter on the bottom. The faster it falls, and the bigger it is, the more pronounced this flattening becomes. Very large drops can break apart into smaller drops. If a raindrop gets too big, the forces acting on it, gravity pulling it down, air resistance pushing up and flattening it, can become strong enough to tear it apart. The drop becomes unstable, and it splits into two or more smaller drops. This breakup helps keep raindrops within a certain size range. You don't see raindrops the size of baseballs because they would break apart long before they reach the ground. Most raindrops that hit the ground are somewhere between 0.5 millimeter and about 5 millimeters across. Anything much bigger than that doesn't survive the fall intact. The breakup process is surprisingly complex. A large drop doesn't just split cleanly in half. Often it develops an indentation on the bottom as air pressure pushes up. The indentation grows deeper, eventually forming a bag-like shape with a rim of thicker water around the edge. The bag can burst, creating several smaller drops from the thin membrane, while the rim breaks up into a ring of slightly larger drops. High-speed photography has captured this process in detail, revealing just how intricate something as simple as a raindrop breaking apart can be. The speed a drop falls depends on its size. A tiny drizzle drop might fall at less than a meter per second, slow enough that it almost seems to float down. A large raindrop might fall at around 9 meters per second, which is faster, but still not terribly fast. It's much slower than, say, a ball thrown by a person. The drop reaches a terminal velocity, a speed where the upward force of air resistance exactly balances the downward force of gravity, and then it falls at that constant speed the rest of the way down. Terminal velocity increases with drop size because larger drops are heavier relative to their surface area. A small drop has a lot of surface area for its weight, so air resistance slows it down more. A large drop has less surface area relative to its weight, so it can fall faster before air resistance balances gravity. But even the fastest raindrops aren't moving all that quickly compared to other things falling from the sky. A raindrop at 9 meters per second is travelling about 32 kilometers per hour, about the speed of a leisurely bicycle ride. Wind can tilt a raindrop's path so rain looks slanted. On a calm day, rain falls more or less straight down, but when there's wind, the drops get pushed sideways as they fall, and you see rain coming at an angle. Strong winds can make rain seem almost horizontal. The drops are still falling downward due to gravity, but they're also being carried sideways by the moving air, and the combination of those two motions makes the slanted streaks you see during a storm. The angle of the rain tells you something about the wind speed. If the rain is falling straight down, there's little or no wind at the level where the drops are falling. If the rain is at a 45-degree angle, the horizontal wind speed is roughly the same as the terminal velocity of the drops. If the rain seems nearly horizontal, the wind is much stronger than the fall speed. Sailors and pilots pay attention to these cues, reading the rain to understand what the wind is doing at different altitudes. The pattern of rainfall can change minute by minute as cloud layers shift. Clouds are not static objects. They're constantly evolving, growing in some places, shrinking in others, moving with the wind, responding to changes in the atmosphere around them. As they shift, the rain they produce shifts too. You might feel a heavy burst of rain for a few minutes, then it lightens to a drizzle, then it stops, then it starts again. These changes reflect what's happening in the clouds above you. Changes in updrafts, changes in the supply of moisture, changes in temperature. Rain is a conversation between the sky and the surface, and it's always changing. Sometimes these changes are organized into patterns. A line of thunderstorms, for instance, might move through an area over the course of an hour, producing bursts of heavy rain separated by lulls. Each storm cell in the line has its own internal structure, its own updraft, its own downdraft, its own region of heavy precipitation, and as the line moves, you experience each cell in sequence. First the leading edge with gusty winds and the first heavy drops, then the core with the heaviest rain, then the trailing edge as the cell moves away and the rain lightens, then a gap a period of light rain or no rain before the next cell arrives and the pattern repeats. Drizzle is made of very small droplets. Drizzle is its own category of precipitation, different from rain. The droplets in drizzle are tiny, usually less than 0.5 millimeter in diameter. They fall slowly and they don't make much sound. Drizzle often has a soft, almost weightless quality. It can make everything damp without ever feeling like a real rain shower. It's the kind of precipitation that barely makes a splash when it hits the ground. Drizzle often falls from low-layered clouds. These clouds, called stratus clouds, are the flat grey blankets that sometimes cover the whole sky. They're not very tall, and they don't have strong vertical motion inside. They're stable and calm, and the precipitation they produce is equally calm. Drizzle from a stratus cloud can last for hours, just a steady, light mist that seems to hover in the air. Stratus clouds often form when a layer of moist air cools just enough to reach the dew point. This can happen overnight, when the ground cools by radiating heat to space, and the air near the surface cools in response. It can happen when warm, moist air moves over a cooler surface, like when air from over the ocean moves over cooler coastal land. The cooling is gentle and widespread, and the resulting cloud is gentle and widespread too. The droplets in a stratus cloud are small and don't grow very large because there isn't enough vertical motion to promote collision coalescence or ice processes. What falls is drizzle, not rain. Showers are rain that starts and stops more suddenly. A shower is different in character from steady rain. Showers tend to be briefer and more intense. They come on quickly, rain for a while, and then stop. The rain might be heavy during a shower, then nothing, then heavy again. Showers are less predictable in their timing and location. Showers often come from clouds with stronger vertical motion. These clouds, called cumulus or cumulonimbus clouds, have strong updrafts inside them. Warm air is rising quickly, carrying moisture upward, and the clouds can grow tall in a short amount of time. Inside these clouds, droplets grow rapidly through collision and coalescence, and ice processes can be very active in the upper levels. The result is bursts of rain that can be quite heavy, but which don't last as long as the steady rain from a large weather system. A cumulonimbus cloud, the towering cloud associated with thunderstorms, can produce very heavy showers. These clouds can extend from near the surface all the way up to the tropopause, the boundary between the troposphere and the stratosphere, which is typically around 10 or 12 kilometers high in the mid-latitudes. The updrafts inside a cumulonimbus can be extremely strong, sometimes exceeding 20 or 30 meters per second. These updrafts can suspend large raindrops and even hailstones, allowing them to grow to impressive sizes before they finally fall. When they do fall, the result is a deluge, a shower that can drop centimeters of rain in just a few minutes. Steady rain can last longer when large cloud systems pass through. Think of a cold front moving across a region, or a low-pressure system spinning slowly overhead. These systems are big. They can cover several states, or even a large portion of a continent. They contain vast layers of clouds, and as the system moves, the clouds move with it. Rain can fall for hours or even days as the system passes, because there's just so much cloud and so much moisture involved. This is the kind of rain that settles in and doesn't seem to want to leave. The clouds associated with these systems are often stratiform, layered clouds that extend horizontally for hundreds of kilometers. Within these layers, there's gentle, widespread lifting of air, enough to sustain condensation and precipitation over a large area. The rain from stratiform clouds is typically light to moderate rather than heavy, but it makes up for that by lasting so long. A winter storm system can bring steady rain for 24 hours or more, accumulating significant totals even though the rate at any given moment isn't extreme. Some rain is light enough to feel like a mist. This is rain that you notice more by the dampness it leaves than by the sound it makes. It might be hard to see individual drops, but after a few minutes outside, your clothes are wet. The drops are small, the rate is low, and the whole experience is gentle. It's the kind of rain that feels almost meditative, quiet, and soft. Some rain is heavy enough to sound like a steady curtain. At the other end of the spectrum, heavy rain can be loud. It drums on roofs, hisses on pavement, and makes it hard to see across the street. The drops are larger, they're falling faster, and there are more of them per second. This kind of rain can fill gutters and create puddles in minutes. It has weight and presence, a kind of insistence that light rain doesn't have. Heavy rain can produce rainfall rates of several centimeters per hour. In extreme cases, such as with tropical thunderstorms or organized lines of severe storms, rates can exceed 10 centimeters per hour for brief periods. This is an enormous amount of water falling from the sky in a short time. The ground can't absorb it fast enough, so it runs off, filling streams and rivers, sometimes causing flash flooding. Heavy rain is dramatic and sometimes dangerous, a reminder that the atmosphere can move vast amounts of water very quickly when conditions align. Rain can fall in narrow bands or wide sheets. The distribution of rain is rarely uniform. Sometimes a band of heavy rain is only a few kilometers wide, and if you're on one side of it, you get drenched, while just a few kilometers away it's barely raining at all. Other times, rain falls over a huge area with little variation. The structure of the clouds and the dynamics of the storm system determine how rain is organized in space. Rain bands are a common feature of many storm systems. In a hurricane, for instance, spiral rain bands wrap around the center of the storm, each one producing heavy rain and gusty winds. Between the rain bands, conditions are much calmer. If a rain band passes over you, you experience a period of intense rain, and then it moves on, and you're in a relatively dry area until the next band arrives. Even in smaller systems, rain can organize into bands aligned with features like fronts or lines of convergence, where winds from different directions meet and force air upward. Rain can be local, affecting one neighborhood and not another. On a summer afternoon, a small thunderstorm might develop over one part of a city and dump rain there while the rest of the city stays dry. You can sometimes see this from a distance, a column of rain falling from a single cloud, with clear skies all around it. It's a reminder that weather happens on many scales, from continent-wide patterns down to individual clouds a few kilometers across. The localized nature of some rain can be surprising and even frustrating. You might check the weather forecast and see that rain is expected, but the rain falls on the other side of town and you don't get any. Or the opposite, the forecast says it will stay dry, but a small cell develops right overhead and drenches you. Forecasting the exact location of these small-scale features is difficult because they depend on local variations in heating, moisture, and wind that aren't always well represented in weather models. Rain intensity is often measured as rainfall rate over time. Meteorologists talk about how much rain falls in an hour or how many millimeters or inches accumulate in a day. A light rain might be just a millimeter or two per hour. A moderate rain might be 5 or 10 millimeters per hour. A heavy downpour could be 20 or 30 millimeters per hour or more. These numbers help quantify something that can otherwise be hard to describe. How much water is actually falling from the sky? Rain gauges are the instruments used to measure rainfall. The simplest rain gauge is just a cylinder with straight sides, open at the top. Rain falls in, and you measure the depth of water that collects. More sophisticated gauges can record rainfall automatically, logging the amount that falls in each hour or even each minute. Some gauges tip a small bucket each time a certain amount of rain has fallen, and the number of tips is counted electronically. Others weigh the collected rain continuously. All of these measurements help meteorologists track storms, verify forecasts, and build up long-term records of rainfall patterns. Rain can cool the air as it falls. One of the side effects of rain is cooling, and this happens through a process that's easy to overlook. Cooling happens because some droplets evaporate, which uses heat. Even as rain is falling, some of the drops are evaporating, especially if the air they're falling through is dry. Evaporation is a phase change from liquid to vapor, and phase changes involve latent heat, energy hidden in the change of state. When water evaporates, it absorbs heat from the surrounding air. That heat is used to break the bonds between water molecules and turn liquid into vapor. As a result, the air gets cooler. This evaporative cooling can be significant, especially in dry climates. When rain falls into dry air, a lot of the rain can evaporate before it even reaches the ground, and the air below the cloud cools dramatically. That cool air is denser than the warm air around it, so it sinks, creating a downdraft. This is one reason thunderstorms can produce strong gusts of wind. The rain cools. The cool air rushes downward, and when it hits the ground, it spreads out in all directions, creating gusty winds. These downdrafts are sometimes called downbursts if they're particularly strong. A downburst can produce winds as strong as a tornado, though they're spread over a wider area and don't have the rotating structure of a tornado. Downbursts are especially common in arid regions where the air is very dry and evaporative cooling is very efficient. A thunderstorm over a desert can produce a tremendous downdraft even if very little rain actually reaches the ground, just because so much evaporation is happening during the fall. Rain can make a warm day feel softer and calmer. There's a psychological component to this certainly, but there's also a physical one. The cooling from evaporation, the increase in humidity, the change in light as clouds block the sun, all of these things combine to make the air feel different. A hot, dry afternoon can be transformed into a cool, damp one in just a few minutes of rain. The relief that rain brings on a hot day is something many people find deeply satisfying. There's a freshness to the air, a sense of things being washed clean. Temperatures drop, sometimes by several degrees in just a few minutes. The oppressive heat lifts. The air feels easier to breathe. This is one reason rain is so often welcomed after a dry spell. It's not just about the water for plants and reservoirs, it's about the immediate comfort it brings. After rain, the ground can release smells that many people notice. This smell is one of the most recognizable and pleasant aspects of rain. It has a fresh, earthy quality, and it's especially strong after the first rain following a dry spell. The rain smell is often linked to oils from plants and compounds in soil. One compound in particular, called geosmin, is produced by certain soil bacteria and released into the air when rain disturbs the soil. Geosmin has a very distinctive odour, even in tiny concentrations, and it's a big part of that after-rain smell. Plants also release oils during dry periods, and when rain hits the ground, it can vaporise some of these oils and carry them into the air. The smell of rain has a name, petrichor. The term was coined by two Australian researchers in the 1960s, derived from Greek words meaning stone and the fluid that flows in the veins of the gods. It's a poetic name for a common experience, and it captures something of the almost magical quality that smell has for many people. Petrichor is released when rain hits dry soil, and it's at its strongest after a long dry period when oils and compounds have built up. The smell can be detected at very low concentrations. Humans are remarkably sensitive to geosmin, able to detect it at levels of just a few parts per trillion. Rain can also clean dust and pollen from the air temporarily. Raindrops falling through the air collide with particles, dust, pollen, soot and other aerosols, and carry them down to the ground. After a rain, the air often looks clearer because those particles have been washed out. The effect is temporary because new particles are always being added to the air, but for a while, the atmosphere is a bit cleaner. This cleansing effect is particularly noticeable in cities, where there's a lot of particulate pollution from vehicles, industry and construction. After a good rain, visibility can improve dramatically. The sky looks brighter, the air feels fresher, and distant objects are easier to see. The rain has literally washed the pollution out of the air, carrying it down to the ground where it can be swept into storm drains or absorbed into the soil. The air can feel fresher after rain because temperatures and particles shift. There's a combination of factors at work. The air is cooler, it's more humid, it's cleaner, and there are new smells from the ground. All of these changes together create that fresh, clean feeling that people associate with the end of a rainstorm. Light rain can create a steady, soothing soundscape. Rain sounds are one of the reasons people find rain relaxing. There's something about the consistency of the sound, the way it fills the space with a soft, continuous noise, that many find calming. It's not loud enough to be jarring, but it's not silent either. It's a kind of white noise, a background sound that can mask other, more distracting noises and help the mind settle. The soothing quality of rain sounds has been studied by psychologists and acousticians. White noise and similar sounds can help with sleep and concentration because they provide a consistent auditory environment. Your brain doesn't have to keep alert for sudden noises or changes because the sound is steady and predictable. This allows other mental processes to relax. Rain sounds also tend to have a pleasant spectral quality. They're broadband, meaning they include a wide range of frequencies but without any harsh peaks or jarring elements. Rain sounds change depending on what it lands on. The surface makes a big difference. Rain on leaves sounds different from rain on metal, which sounds different from rain on water. Each surface has its own acoustic properties, how hard it is, how much it absorbs or reflects sound, whether it's smooth or textured. These properties shape the sound the rain makes when it hits. Leaves soften impacts and create a gentle patter. When rain falls on a tree or a bush, the leaves catch the drops and absorb some of the impact. The sound is soft, almost muffled, with a light tapping quality. It's organic and irregular because leaves are flexible and move with each drop. The overall effect is gentle and natural, a layered sound as drops hit leaf after leaf. A forest in the rain produces a complex layered soundscape. Raindrops hit leaves at different heights. Some fall on the canopy high above, others on understory shrubs, still others on ground-level plants. Each level contributes its own sound, and together they create a rich acoustic tapestry. There's movement too, branches swaying, leaves fluttering, and this adds variation to the sound. Walking through a forest during rain is a multisensory experience, the sound enveloping you from all directions. Roofs can create sharper taps and steady drumming. Rain on a roof is often louder and more distinct, especially if the roof is made of metal. Each drop makes a clear, sharp sound, and when many drops are falling, it becomes a drumming rhythm. Roofs are hard and reflective, so the sound bounces around and can be quite noticeable inside the building. It's one of the classic rain sounds, the one people often associate with being indoors during a storm. Tin roofs are particularly resonant. A metal roof amplifies the sound of rain, turning even a light shower into a noticeable drumming. In some parts of the world, this sound is such a familiar part of rainy season that it's deeply embedded in the cultural experience of weather. People remember the sound of rain on the roof from childhood, associate it with coziness and safety, find comfort in it. Pavement can create a crisp, wide hiss. Rain on a street or a sidewalk has a different character. The surface is hard, so there's some sharpness to the sound, but it's also distributed over a large flat area, so it blends into a kind of hiss. It's a broad, diffuse sound rather than a series of individual taps. You hear it when you're walking in the rain or standing near a wet road. The hiss of rain on pavement is punctuated by the sounds of cars passing through puddles, water splashing against curbs, drops hitting umbrellas and coats. In a city during rain, the soundscape is complex and layered. Rain on all sorts of surfaces, wind rustling leaves and whistling around buildings, distant thunder, the hum of traffic. It's a busy, active sound environment, very different from the quiet simplicity of rain on a forest or a field. Grass can absorb sound and make rain feel quieter. Grass and soil are softer than pavement or roofs, and they absorb more of the sound energy when rain hits them. The rain still makes noise, but it's quieter, more subtle. You might hear the rain more in the air around you than on the ground itself. Rain on water can create overlapping rings and soft splashes. When rain falls on a pond or a puddle, each drop makes a small splash and sends out ripples. The sound is a mixture of the impact and the subsequent splashing and rippling. It's a layered sound, with each drop adding to a complex, constantly changing pattern. There's something hypnotic about rain on water, both visually and acoustically. If you watch rain falling on a lake or a quiet pool, you see countless rings expanding outward, overlapping, interfering with each other in intricate patterns. Each drop creates its own small disturbance, and these disturbances interact, creating a continuously shifting pattern of waves and ripples. The visual and auditory experience together can be mesmerizing, a display of simple physics playing out in countless simultaneous events. The size of drops changes the sound. Bigger drops make deeper taps. A heavy rain with large drops sounds different from a light drizzle with tiny drops. The large drops have more mass and more energy when they hit, so they make a louder, lower-pitched sound. Small drops are quieter and higher-pitched. The size distribution of the drops shapes the overall sound of the rain. Wind changes the sound by changing the angle and speed of impacts. Wind doesn't just move the rain sideways, it also affects how hard the rain hits surfaces. When wind is strong, drops can hit at steeper angles and with more force, creating louder, sharper sounds. The wind can also create variation in the sound as gusts come and go, making the rain louder and quieter in waves. Distance changes the sound. Rain far away can be a soft whisper. When you hear rain in the distance, it's quieter and less distinct. The sound has travelled through the air and some of it has been absorbed or scattered. What you hear is a kind of gentle murmur, a hint of rain rather than the full sound. It can be very soothing, this distant rain sound, because it's so soft and non-intrusive. A steady rainfall can become a natural lullaby because it is repetitive and non-demanding. The sound doesn't change much. It doesn't startle you. It doesn't require your attention. It's just there, constant and calm. and that constancy can help the mind let go of other thoughts and drift. Rain sounds are often used for sleep and relaxation for this very reason. They're predictable, they're soft, and they're easy to stop actively listening to, which allows them to fade into the background of awareness. Sometimes rain evaporates before it reaches the ground. This is called virga. Virga is a phenomenon that's easy to see once you know what to look for. Virga is common when air near the ground is dry. Imagine rain falling from a cloud into a layer of very dry air. As the drops fall, they evaporate, turning back into vapor before they can reach the surface. You can sometimes see virga as wispy streaks below a cloud. The streaks are the rain, still visible as it falls but fading away as it evaporates. From a distance, it looks like the rain is disappearing into nothing. Virga is particularly common in arid and semi-arid regions, where the surface air is often very dry. You might see a storm cloud with clear signs of precipitation, a dark base, streaks extending downward, but feel no rain at ground level. All of the rain has evaporated in mid-air. For someone hoping for rain to water crops or fill reservoirs, virga can be frustrating. The moisture is there, falling from the sky, but it never reaches the ground where it's needed. Evaporation during virga can cool the air below a cloud. Just as with rain that reaches the ground, evaporating rain absorbs heat from the air. This cools the air in the layer where the evaporation is happening. Cooler air can sink, changing wind patterns near the ground. The sinking air can create downdrafts and gusty winds, even if no rain is actually reaching the surface. This is one way rain can affect the weather even when it doesn't fall all the way to the ground. Dry air can turn rain into a brief moment rather than a long event. In arid regions, virga is very common. Clouds can produce rain, and that rain can fall halfway to the ground or more, but the air is so dry that the rain never makes it. You see the clouds, you see the streaks of precipitation, but you feel nothing. It's a reminder that the atmosphere is layered, and conditions can be very different at different heights. This is one reason you can see rain in the distance and feel none where you are. Even if a cloud is overhead and rain is falling from it, if the air at your level is dry enough, the rain won't reach you. Or maybe the rain is falling a few kilometers away, and the wind isn't carrying it in your direction. Rainfall distribution is rarely perfectly even. Some places get rain, others don't, even when they're close together. The atmosphere is always layering and mixing, quietly shaping what reaches the ground. Air is constantly moving, rising, sinking, mixing horizontally and vertically. These motions create layers with different temperatures, humidities, and wind speeds. Rain has to pass through all of these layers on its way down, and each layer can change the rain in some way. The atmosphere is not a simple, uniform medium. It's a complex, dynamic fluid, and rain is shaped by that complexity. Rain usually begins with air lifting upward. This is the fundamental starting point for most precipitation. For rain to happen, you need moisture in the air, you need that air to cool, and cooling usually happens when air rises. As air rises, it expands because the pressure decreases with altitude. Expansion cools the air, and cooling brings the air closer to its dew point. When the air reaches the dew point, condensation begins, clouds form, and if the process continues, precipitation can develop. Air can lift when the ground warms it. This is called convection. On a sunny day, the ground absorbs sunlight and heats up. The air in contact with the ground warms up too. Warm air is less dense than cool air, so it starts to rise. As it rises, it cools, and if it's carrying enough moisture, it can reach the dew point and form clouds. This is how many afternoon thunderstorms develop, especially in warm, humid climates. The sun heats the ground, the air rises, clouds grow, and rain falls. Convective processes are particularly important in the tropics, where strong sunlight and abundant moisture create ideal conditions for afternoon storms. Almost every day, cumulus clouds begin to form in the late morning as the sun warms the surface. By early afternoon, some of these clouds have grown into towering cumulonimbus, producing heavy rain showers and thunderstorms. The pattern is so regular that people can almost set their watches by it. Clear mornings, building clouds at midday, storms in the afternoon, clearing in the evening. Air can lift when it's pushed up a mountain. This is called orographic lifting. When wind blows toward a mountain range, the air has to go up and over the mountains. As it rises, it cools, and cooling can lead to condensation and clouds. The upwind side of mountains often gets a lot of rain because of this effect. while the downwind side can be much drier. The air has lost much of its moisture on the way up, so by the time it descends on the other side it's relatively dry. Orographic precipitation can produce very high rainfall totals. Some of the wettest places on Earth are on the windward slopes of mountains, where moist air is constantly being forced upward. Mount Waialeal in Hawaii, for instance, receives more than 10 meters of rain per year on average because it's in the path of the trade winds, which carry moist air from the ocean and force it up the mountain slopes. The downwind sides of islands and mountain ranges, by contrast, can be surprisingly dry. Even though they're just a few kilometers away from the wet slopes, air can lift where warm and cold air meet along fronts. A front is a boundary between air masses with different temperatures. When warm air and cold air meet, the warm air is forced to rise over the cold air, because warm air is lighter. This lifting can produce extensive cloud systems and precipitation. Cold fronts, where cold air is advancing and pushing under warm air, can produce lines of showers and thunderstorms. Warm fronts, where warm air is advancing and rising over retreating cold air, can produce broad areas of steady rain. Frontal systems are a major source of precipitation in the mid-latitudes, where warm tropical air and cold polar air frequently collide. The boundary between these air masses is the polar front, and it's along this front that many of the storms affecting North America, Europe, and Asia develop. As the front moves, it brings changing weather. First the approach of clouds, then rain, then clearing as the front passes and different air moves in. Lifting cools air, which encourages condensation. This is the key mechanism. Without lifting, air wouldn't cool enough to reach the dew point, and without reaching the dew point, condensation wouldn't happen. No condensation means no clouds, and no clouds means no rain. Lifting is the engine that drives the whole process. Clouds grow where condensation is happening repeatedly. Once condensation starts, a cloud begins to form, and if the conditions are right, the cloud keeps growing. More air keeps rising, more moisture keeps condensing, and the cloud expands. In some cases, clouds can grow very tall very quickly, especially in unstable atmospheres where rising air accelerates as it goes up. Instability in the atmosphere occurs when temperature decreases rapidly with height. In a stable atmosphere, rising air cools at a rate similar to the surrounding air, so there's no tendency for the air to keep rising. But in an unstable atmosphere, rising air stays warmer than its surroundings even as it cools, and this makes it buoyant. It continues to accelerate upward, driving vigorous convection and rapid cloud growth. This is the environment that produces the most intense thunderstorms. Larger cloud systems can organize rain over wide areas. When weather systems develop, they can create clouds that extend for hundreds of kilometers. These systems can produce rain over entire regions, and the rain can last for many hours or even days. The organization of the clouds is tied to the structure of the weather system, where air is rising, where it's sinking, where the moisture is concentrated. Small clouds can produce quick, gentle showers. On the other hand, a single cumulus cloud might only be a kilometer or two across, and it might only last for half an hour, but during that time it can produce a brief shower. The shower might be light, and it might only affect a small area, but it's still rain, produced by the same basic processes of lifting, cooling, condensation, and droplet growth. The same cloud can shift from drizzle to steadier rain as conditions change. Clouds are not static. Their internal structure is constantly evolving. Updrafts can strengthen or weaken. The supply of moisture can increase or decrease. The temperature profile can change. All of these changes affect the precipitation. A cloud that's producing drizzle might start producing heavier rain if the updrafts strengthen and droplets have more time to grow. Rain is often the visible end of invisible processes, lifting, cooling, condensing, and growing droplets. What you see when you look at rain is the final product. You don't see the air rising, you don't see the cooling, you don't see the condensation nuclei, and you don't see the collision coalescence or ice processes happening inside the cloud. But all of those invisible processes are what make rain possible. The rain you feel is the culmination of a long chain of atmospheric events. Rain moves fresh water from the sky back to land and ocean. This is one of the most important roles rain plays on Earth. The water cycle is constantly moving water between the surface and the atmosphere. Evaporation lifts water from the ocean and the land into the air. Condensation and precipitation bring it back down. Without rain, the water that evaporates would just accumulate in the atmosphere and the land would dry out. Rain is the return trip. the way water gets back to where it's needed. Rain helps refill rivers, lakes and reservoirs. When rain falls on land, some of it soaks into the ground, some of it evaporates, and some of it flows over the surface and into streams and rivers. This surface runoff is what keeps rivers flowing, it's what fills reservoirs behind dams, it's what maintains lake levels. Without rain, rivers would run dry, lakes would shrink, and reservoirs would empty. Rain is the source of fresh surface water. The Amazon River, the largest river in the world by volume, is fed almost entirely by rain falling on its vast drainage basin. Millions of square kilometres of rainforest receive abundant precipitation, and all of that water eventually flows into the river system. The river carries more than 15% of all the fresh water that flows into the world's oceans, a staggering amount that speaks to the immense rainfall over the Amazon basin. Rain supports plant growth by bringing water to soil. Plants need water to survive. They absorb it through their roots, and they use it for photosynthesis, for transporting nutrients, for maintaining cell structure. Rain delivers water to the soil where roots can access it. In places with regular rainfall, vegetation is lush and diverse. In places with little rain, vegetation is sparse and specially adapted to survive on very little water. The amount and pattern of rainfall shapes entire ecosystems. Rain carries minerals through ecosystems in gentle cycles. As rain falls through the air, it can pick up small amounts of dissolved gases and particles. When it hits the ground, it can dissolve minerals from rocks and soil. As the water moves through the landscape, soaking into the ground, flowing into streams, seeping into aquifers, it carries these dissolved substances with it. This is one way nutrients are distributed through ecosystems. It's a slow process, but it's been going on for so long that it's shaped the chemistry of soils, rivers and oceans. Rainfall patterns influence where forests, grasslands and deserts form. Climate is driven by many factors, but rainfall is one of the most important. A place that gets abundant rain year-round might have a rainforest. A place that gets moderate rain might have forests or grasslands, depending on temperature and seasonality. A place that gets very little rain becomes a desert. These are broad generalizations, but they hold true around the world. Rainfall is a defining feature of climate, and climate determines what kinds of ecosystems can exist. Rain releases heat in the atmosphere when vapor condenses into droplets. This is the other side of latent heat. When water evaporates, it absorbs heat from the surroundings, cooling them. When water condenses, it releases that heat back into the air, warming it. This release of latent heat is a huge source of energy in the atmosphere. It's one of the main engines of weather. Thunderstorms, hurricanes, and other storm systems are powered in large part by the heat, released when water vapor condenses. That released heat can help drive winds and circulation. The warming from condensation makes air more buoyant, which strengthens updrafts, which brings in more moist air from the surroundings, which leads to more condensation and more warming. This feedback can intensify storms and create powerful winds. On a larger scale, the release of latent heat in the tropics is one of the main drivers of global atmospheric circulation. It helps create the trade winds, the jet streams, and the large-scale patterns of rising and sinking air that shape weather around the world. Rain is one way the atmosphere redistributes energy. The sun heats the earth unevenly, more at the equator, less at the poles. The atmosphere and ocean work together to move heat from warm regions to cooler regions, evening out the temperature differences. Rain is part of this redistribution. Water evaporates in warm places, carrying energy up into the atmosphere as latent heat. The water vapor moves with the wind. When it condenses and rains out in a different location, that heat is released, warming that part of the atmosphere. Through this mechanism, rain helps transport energy across the planet. Even light rain is part of Earth's constant balancing act. The Earth system is always trying to reach equilibrium, balancing energy in and energy out, balancing moisture between surface and sky, balancing temperature between different regions. Rain, even a gentle drizzle, is part of this balancing process. It might seem small and local, but it's connected to the global system. The water you experience as rain has often travelled through many places before. The water molecule that lands on your hand might have evaporated from the Pacific Ocean weeks ago, been carried across continents by the wind, condensed into a cloud over your city, and now it's falling. But its journey doesn't end there. It will soak into the soil, or run into a river, or evaporate again in a few hours, and then the cycle continues. Water molecules are constantly being recycled through the Earth system, and rain is just one stage in their endless journey. Your breath contains water vapor. Every time you exhale, you're releasing a small amount of water vapor into the air. It's a tiny amount, but it's there. If you breathe onto a cold window, you can see it condense into a thin fog. This is the same process that happens in clouds, just on a much smaller scale. Your breath is part of the water cycle, even if it's a minuscule part. A warm shower can raise humidity in a room by adding vapor to the air. When you run hot water, some of it evaporates and mixes with the air in the bathroom. The humidity goes up. You can feel it. The air feels thicker, warmer, more moist. After you turn off the water, the humidity gradually drops as the vapor condenses on cold surfaces or mixes with drier air from the rest of the building. But for a while, you've created a little humid microclimate in your bathroom. Cooler air holds less water vapor than warmer air. This is a fundamental property of air and water vapor. Warm air can hold a lot of moisture before it becomes saturated. Cool air can't hold as much. If you take a parcel of warm, moist air and cool it down, eventually it will reach. The dew point and the vapor will start condensing. This is why condensation happens at night when temperatures drop, and it's why clouds form when air rises and cools. That's why condensation can form on cold windows. On a cold night, the window glass is much colder than the air inside the room. When warm, moist indoor air comes into contact with the cold glass, it cools down quickly. If it cools below the dew point, the water vapor condenses right onto the glass, forming a layer of tiny droplets. This is the same process that forms dew on grass or frost on a car windshield. Rain reminds us that the air is full of invisible moisture. You can't see water vapor, but it's always there, mixed in with the other gases in the atmosphere. Rain is proof of that invisible moisture. It's the vapor made visible, transformed from gas to liquid, falling to the ground. Every raindrop is a reminder that the atmosphere is not just nitrogen and oxygen, it's also water, constantly shifting between phases. The water cycle never stops, even while you sleep. Right now, somewhere on Earth, water is evaporating from the ocean. Somewhere else, clouds are forming. Somewhere else, rain is falling. The cycle runs continuously, day and night, summer and winter, year after year. It doesn't pause. It's one of the most constant, reliable processes on the planet, a rhythm that has been running for as long as Earth has had an atmosphere and oceans. Some of the water in rain once evaporated from oceans far away. The atmosphere is well mixed over time and distance. Water that evaporates in one place can be carried thousands of kilometers by the wind before it falls as rain somewhere else. The rain that falls on a landlocked region might have evaporated from the ocean weeks ago and been carried inland by weather systems. The journey of water through the atmosphere can be long and complex. Some of it once evaporated from plants through a process called transpiration. Plants take up water from the soil through their roots, and they release some of it through tiny pores in their leaves called stomata. This process is called transpiration, and it's a significant source of water vapor in the atmosphere, especially in forested regions. A large tree can transpire hundreds of liters of water in a single day. That water enters the atmosphere and can eventually become part of a cloud and fall as rain. Tonight, you can let thoughts fall like rain. Quiet, steady, and then gone. Rain is a good metaphor for letting go. Thoughts come, they fall, they touch the surface of your mind, and then they flow away. You don't have to hold on to them. You don't have to examine each one. You can just let them pass like raindrops falling through the air, each one separate, each one temporary, each one part of a larger pattern that you don't have to understand or control. And as you rest, Earth continues its oldest rhythm, water rising, gathering, and returning softly home. This rhythm has been running for billions of years. It was running before there were forests, before there were animals, before there were people. It will keep running long after we're gone. It's one of the most fundamental patterns of the planet. Water moving from surface to sky and back again, in an endless loop, a quiet exchange that sustains everything. Rain falls. It has always fallen, it will always fall. It's simple and it's complex. It's ordinary and it's profound. It's something you can watch from a window or feel on your skin. It's something you can hear and smell and measure. And it's also something you can just let be. Just another part of the world, doing what it has always done, soft and steady, cycle after cycle. drop after drop returning home. Just one more small fact, and then we drift. The next story is about to begin. Please relax and enjoy. A cloud is made of tiny water droplets, tiny ice crystals, or both. When you look up at the sky and see those white or grey shapes drifting across the blue, you're actually looking at billions upon billions of these minuscule particles suspended in the air. Each droplet is so small that you couldn't see it with your naked eye if it were alone. It's only when countless millions of them gather together that they become visible as the soft, puffy forms we call clouds. The ice crystals, similarly, are delicate structures that form in the colder regions of the atmosphere, each one a tiny piece of frozen water floating effortlessly in space. Together, these droplets and crystals create the gentle shapes that move across the sky, sometimes slowly, sometimes a bit faster, but always with a kind of peaceful rhythm that makes them pleasant to watch. What's particularly interesting is that clouds are not made of water vapour. This might seem confusing at first because we often think of clouds as some form of evaporated water hanging in the air, but vapour itself is actually invisible. When water evaporates from a puddle, a lake, or the ocean, it becomes water vapour. Individual molecules of water dispersed in the air spread so far apart that light passes through them without any scattering or reflection. You can't see water vapour any more than you can see the oxygen or nitrogen in the air around you. It's only when this vapour changes form, when it transitions from those separated molecules into tiny liquid droplets or ice crystals, that it becomes visible. So the cloud you see is water that has moved past the vapour stage into something new, something that interacts with light in a way that makes it appear white or grey against the sky. Clouds form when moist air cools enough for water to condense. The air around us always contains some amount of water vapour, even on days that feel dry. This vapour is mixed throughout the atmosphere, carried along by winds and air currents, invisible and weightless. But air has a particular property. When it cools down, it can't hold as much water vapour as it could when it was warm. Think of it like a sponge that becomes less absorbent as it gets colder. As the temperature drops, the air reaches a point where it simply can't keep all that water in vapour form anymore. The vapour molecules begin to slow down, to come closer together, and eventually they transform into liquid droplets. This transformation happens at a specific temperature for any given amount of moisture in the air, and it's the reason why cooling is so essential to cloud formation. Condensation happens when air reaches its dew point. The dew point is the temperature at which air becomes saturated with water vapour, the point where it can't hold any more moisture without some of it condensing into liquid form. Every parcel of air has its own dew point, depending on how much water vapour it contains. If the air is very moist, the dew point will be close to the current temperature, and it won't take much cooling to reach it. If the air is dry, the dew point will be much lower, and the air will need to cool quite a bit before condensation begins. You can observe this principle on a cool morning when dew forms on grass or spiderwebs. The ground has radiated heat during the night and cooled down, and the air immediately touching that cool ground has also cooled until it reached its dew point. The result is those tiny droplets of water clinging to surfaces, appearing seemingly out of nowhere as the invisible vapour becomes visible liquid. Most clouds need tiny particles to condense onto. In perfectly pure air, water vapour would have a harder time condensing into droplets, even when the temperature dropped below the dew point. The vapour molecules would bounce around, occasionally clustering together, but those clusters would tend to break apart before they could grow into stable droplets. What makes condensation easier and more reliable is the presence of tiny particles floating in the air, solid surfaces that give the water molecules something to gather around. When vapour molecules encounter one of these particles, they can stick to its surface, and once a few molecules have attached, it becomes easier for more to join them. The particle acts as a nucleus, a seed around which a droplet can grow. Without these particles, clouds would form much less readily, and the sky might look quite different. Those particles are called condensation nuclei. They're everywhere in the atmosphere, even in air that seems perfectly clean and clear. Some of them are natural, and some come from human activities, but all of them serve the same purpose, providing a foundation for water droplets to form. These nuclei are incredibly small, often measured in micrometers or even smaller fractions, making them invisible to the eye but absolutely crucial to the process of cloud formation. They drift through the air carried by winds, rising and falling with air currents, waiting patiently for the right conditions, the right temperature, the right amount of moisture, to fulfill their role in creating a cloud. Condensation nuclei can be dust, sea salt, smoke, or pollen. The sources are wonderfully varied. Dust particles lifted from deserts or dry soil can travel thousands of miles on the wind, eventually becoming part of a cloud forming over an ocean or a forest. When ocean waves crash and break, they send tiny droplets of seawater into the air, and when those droplets evaporate, they leave behind microscopic crystals of salt that float upward and become perfect condensation nuclei. Smoke from wildfires or industrial processes contributes particles as well, tiny bits of carbon and other materials that drift through the atmosphere. Even pollen grains released by plants during their reproductive cycles can serve as nuclei, though they're generally larger and heavier than the ideal size. Each of these particles has travelled its own path through the air before contributing to a cloud, and each brings with it a tiny fragment of the place it came from. A desert, an ocean, a forest, a city. Each droplet in a cloud is extremely small. If you could somehow pluck a single droplet from a cumulus cloud and examine it, you'd find it measures about 10 to 20 micrometers in diameter. To put that in perspective, a human hair is roughly 70 micrometers across, so a cloud droplet is several times smaller than the width of a single hair. It would take millions of these droplets clustered together to form something the size of a raindrop. This extreme smallness is part of what allows clouds to float. Something so tiny doesn't fall through the air the way a raindrop does. Instead, it drifts, buffeted by air currents, rising and falling with the movement of the atmosphere, sometimes staying suspended for hours before it either evaporates back into vapor or grows large enough to fall. A cloud can look solid, but it's mostly air. When you see a towering cumulus cloud, it might appear dense and substantial, like a floating mountain of cotton or a mass of whipped cream. But if you could fly through it, you'd find that it's surprisingly insubstantial. The droplets and ice crystals are spread throughout a large volume of air, with lots of space between them. In fact, if you could somehow gather all the water droplets from a typical cloud and compress them together, they'd form a surprisingly small amount of liquid. Perhaps just enough to fill a bathtub or a small swimming pool, depending on the cloud's size. The rest is simply air, with those tiny droplets scattered through it like dust motes in a sunbeam, each one too small to see individually but together creating something visible and beautiful. Clouds are part of the water cycle moving water through the atmosphere. Water is always in motion on Earth, constantly changing form and location in a process that has continued for billions of years. The ocean evaporates water into the air. That water rises as invisible vapor, travels with the wind, cools and condenses into clouds. The clouds release the water as precipitation, rain, snow, sleet or hail, which falls to the ground, flows into streams and rivers, and eventually makes its way back to the ocean, or seeps into the soil where plants draw it up and release it back into the air through their leaves. Clouds are one stage in this endless cycle, a visible moment in water's long journey from sea to sky to land and back again. They're temporary structures, constantly forming and dissolving, but they're part of something permanent and essential to life on Earth. Just one more small fact, and then we drift. Cloud droplets are so small that they fall very slowly. When a tiny water droplet forms in a cloud, gravity does pull on it, trying to draw it downward toward the Earth. But the droplet is so light and so small that air resistance becomes a major factor. As it tries to fall, it has to push air molecules out of the way, and those molecules push back, creating drag that slows the descent dramatically. The result is that a typical cloud droplet falls at a rate of only about 1 centimeter per second, roughly the speed of a snail crawling across a sidewalk. At that rate, a droplet forming in a cloud several thousand feet up would take many hours to reach the ground, if it ever made it at all. In reality, such a slowly falling droplet would likely evaporate long before completing its journey, as it drifted down into warmer, drier air below the cloud. Upward moving air can keep droplets suspended. While the droplets are falling slowly downward due to gravity, the air itself is often moving upward, especially within and beneath clouds. If the upward motion of the air is faster than the downward drift of the droplets will actually rise instead of fall, carried along by the moving air like dust particles caught in a breeze blowing upward. Even if the upward air motion is slower than the fall speed, it can still slow the descent enough to keep the droplets aloft for extended periods. This is why clouds can persist for hours or even days. The droplets are in a constant balance between falling and being lifted, and as long as conditions remain favourable, they stay suspended in the sky. Warm air is less dense than cold air, so it rises. This is a fundamental principle of how the atmosphere behaves, and it's essential to understanding why clouds form where they do. When air is heated, the molecules within it move faster and spread farther apart. This makes the air less dense. There are fewer molecules in a given volume compared to cooler air. Because it's less dense, warm air is lighter than the cooler air surrounding it, and it begins to rise, just like a hot air balloon lifts off the ground because the heated air inside is lighter than the air outside. This rising warm air is the engine that drives cloud formation in many situations. As it rises, it carries moisture with it, lifting water vapour higher and higher into the atmosphere. Rising air expands as pressure decreases with altitude. The atmosphere is held to Earth by gravity, and this creates air pressure, the weight of all the air above pressing down on the air below. At sea level, this pressure is relatively high, because there's a lot of atmosphere overhead. But as you go higher, there's less air above you, so the pressure decreases. When a parcel of warm air rises and encounters this lower pressure, it expands, spreading out to fill more space. This expansion requires energy, and the air uses its own heat energy to expand, which causes it to cool down. It's similar to what happens when you release compressed air from a tyre. The air expands rapidly and feels cold because it's using its heat energy to expand. This principle, expansion causing cooling, is crucial to cloud formation. Expanding air cools, which helps clouds form. As the rising air cools through expansion, it approaches its dew point, the temperature at which its water vapour begins to condense. The air might have been far from its dew point when it was down at the surface, warm and capable of holding lots of moisture. But as it rises and cools, the gap between its temperature and dew point narrows. Eventually, if the air rises high enough and cools enough, it reaches the dew point. At that moment, condensation begins. Water vapour transforms into tiny droplets around condensation nuclei, and a cloud starts to form. This is why clouds often have distinct bases. Flat bottoms that mark the altitude where rising air has cooled to its dew point, and condensation has begun. This cooling from rising is called adiabatic cooling. The term adiabatic comes from Greek words meaning not passable, or impassable, and in physics, it refers to a process that happens without heat being added or removed from outside. When air rises and cools adiabatically, it's not losing heat to its surroundings, it's simply using its own internal heat energy to expand against the lower pressure. The opposite happens when air sinks. It's compressed by the increasing pressure, and that compression converts work into heat, warming the air. This adiabatic cooling and warming is happening all the time in the atmosphere, driving weather patterns, creating clouds, and influencing winds. It's a process powered entirely by the movement of air and the changing pressure with altitude. Clouds often mark places where air has lifted. When you look at the sky and see clouds scattered across it, you're seeing a map of where air has been rising in the atmosphere. Each cloud, whether a small puff of cumulus or a vast sheet of stratus, formed because air rose high enough and cooled enough for condensation to occur. The clear spaces between clouds are places where air isn't rising, or where it's sinking, or where conditions weren't quite right for condensation. By watching how clouds form and where they appear, you can begin to understand the invisible motions of the atmosphere, the currents and updrafts and flows that are constantly reshaping the air around us. Air can lift over mountains, forming clouds on the windward side. When wind encounters a mountain range, it can't simply stop or go around. It has to rise up and over the obstacle. As the air is forced upward along the mountain slope, it expands and cools adiabatically. If there's enough moisture in the air, and if it rises high enough, it will reach its dew point and clouds will form on the side of the mountain facing the wind, the windward side. These orographic clouds, as they're called, can create dramatic effects. You might see a clear sky on one side of a mountain range and a wall of clouds on the other, all because the air is being lifted by the terrain. After the air passes over the peak and descends on the leeward side, it warms and dries out, often creating a rain shadow, a region that receives little precipitation because the air has already released its moisture on the other side of the mountain. Air can lift where warm and cold air meet along fronts. A front is a boundary between two different air masses, one warm and one cold, and these boundaries are zones of active weather. When a mass of warm air meets a mass of cold air, they don't mix easily. Cold air is denser and tends to slide underneath the warm air, forcing it upward. This lifting can be gradual or quite rapid, depending on how different the two air masses are and how fast they're moving. As the warm air is lifted, it cools, and if it contains enough moisture, clouds form along the front. A warm front where warm air is advancing and sliding up over retreating cold air often produces broad areas of steady clouds and gentle precipitation. A cold front where cold air is aggressively pushing beneath warm air can produce narrow bands of towering clouds and more intense weather. Air can also lift from surface heating during the day. On a sunny day, the sun's rays warm the ground, and the ground in turn warms the air immediately above it. Some surfaces heat up more than others. A dark asphalt parking lot will get much hotter than a grassy field, for instance. The air over the hot surface becomes warmer and less dense than the surrounding air, and it begins to rise in what's called a thermal. These thermals are columns of rising warm air, and they're the reason you often see cumulus clouds developing on summer afternoons. The clouds mark the tops of the thermals, the points where the rising air has cooled enough to reach its dew point. Birds and glider pilots often use these thermals, circling within them to gain altitude effortlessly. Just one more small fact, and then we drift. Many clouds belong to a few main families based on height and shape. While every cloud is unique, meteorologists have developed a classification system that groups clouds into categories based on their appearance and the altitude at which they form. This system brings order to the seeming chaos of the sky, allowing observers to identify clouds and understand something about the weather conditions that created them. The classification isn't rigid. Clouds can transition from one type to another, and sometimes they display characteristics of multiple types simultaneously. But it provides a useful framework for thinking about the atmosphere's behaviour. Clouds with the prefix cirro are generally high and thin. These clouds form in the upper reaches of the troposphere, often at altitudes above 20,000 feet, where the air is very cold and the pressure is low. Because they form so high where temperatures are well below freezing, cirro clouds are composed primarily of ice crystals rather than water droplets. Their wispy, delicate appearance reflects this composition. Ice crystals scatter light differently than water droplets, giving these clouds a fibrous or feathery quality. The name comes from the Latin word cirrus, meaning a curl or tuft of hair, which aptly describes their often strand-like appearance. Clouds with the prefix alto are usually mid-level. These clouds typically form at altitudes between 6,000 and 20,000 feet in the middle layer of the troposphere. They can be composed of water droplets, ice crystals, or a mixture of both, depending on the exact temperature at their altitude. Alto clouds often appear as sheets or patches, sometimes covering large portions of the sky. The prefix comes from the Latin altus, meaning high, though in the modern classification system it's understood to mean middle level rather than the highest clouds. These clouds often appear ahead of approaching weather systems, as moisture at mid-levels increases before a front arrives. Clouds with the prefix strato are layered. The term comes from stratus, the Latin word for layer or spread out, and it describes clouds that form in stable air where there's not much vertical motion. Stratus clouds spread horizontally in sheets or blankets rather than building upward into towers. They often form when a large air mass gradually lifts or cools, or when moist air moves over a cool surface. The result is a smooth, uniform layer that can cover the entire sky, creating overcast conditions. Stratus clouds can occur at various altitudes, and when combined with other prefixes, they describe specific types, stratocumulus, for instance, or altostratus. Clouds with the prefix cumulo are puffy and piled. Cumulus means heap or pile in Latin, and these clouds look like what most people imagine when they think of clouds, those cotton ball shapes with distinct edges and bases. Cumulus clouds form in unstable air where there's active vertical motion, rising currents of warm air that build the clouds upward. They have a characteristic structure, a flat base marking the condensation level, and a rounded or dome-shaped top where the rising air pushes the cloud upward. On a fair weather day, you might see many individual cumulus clouds scattered across the sky, each marking a separate thermal updraft. The term nimbus suggests precipitation. When nimbus or nimbo appears in a cloud name, it indicates that the cloud is producing rain or snow. Nimbostratus, for instance, is a thick, dark layer cloud that brings steady precipitation. Cumulonimbus is a towering cumulus cloud that has grown tall enough to produce rain, hail, or even tornadoes. The word comes from the Latin for rain cloud, and its presence in a cloud's name tells you immediately that this is an active, precipitating system. rather than a dry cloud that's merely decorating the sky. Cirrus clouds often look like wispy feathers. When you see these high clouds, they might appear as delicate streaks or hooks, white against the blue sky, sometimes almost translucent. They're composed entirely of ice crystals, and those crystals give them their characteristic appearance. Wind at high altitudes can be very strong, and it shapes cirrus clouds, stretching them out into long strands or mare's tails. Because they're so thin, cirrus clouds don't block much sunlight. You can usually see the sun or stars through them, but they can create beautiful optical phenomena like halos and sundogs when light passes through their ice crystals at particular angles. Stratus clouds often look like a grey blanket. These low-lying layer clouds can cover the entire sky in a uniform sheet, obscuring the sun and creating a dreary, overcast atmosphere. They form in stable conditions where air is lifted gently and uniformly, without the vigorous updrafts that create puffy cumulus clouds. Stratus clouds might produce drizzle or very light rain, but often they simply sit overhead, grey and featureless, filtering the daylight into a soft, diffuse glow. They can persist for hours or even days if conditions remain stable, creating that characteristic dull weather that makes you want to stay indoors with a book and a warm drink. Cumulus clouds often look like soft towers or cotton. On a pleasant day with scattered clouds, those individual puffy clouds you see are likely cumulus. They have distinct boundaries, with bright white tops where the sun illuminates them and darker bases in shadow. They can be small and flat, fair-weather cumulus that look like little cotton balls drifting by, or they can grow taller, developing into towering cumulus that resemble cauliflower heads stacked on top of each other. The growth depends on how unstable the atmosphere is and how much moisture is available. In the right conditions, cumulus can continue building upward for hours, eventually becoming the tall cumulonimbus clouds associated with thunderstorms. A cloud's shape can hint at the motion of the air creating it. When you look at clouds, you're seeing sculpture created by invisible forces, the rising and sinking of air, the speed and direction of wind, the layers of stability and instability in the atmosphere. A smooth, layered cloud suggests stable, uniform lifting. A towering, billowing cloud suggests strong updrafts and instability. Ragged, torn-looking clouds might indicate turbulent conditions where wind shear is pulling the cloud apart. Lenticular clouds, which look like stacks of smooth lenses, form in wave patterns downwind of mountains where air is rising and sinking in a regular pattern. By reading these shapes, you can begin to understand what the atmosphere is doing, even though the air itself is invisible. Just one more small fact, and then we drift. Many high clouds are made mostly of ice crystals. In the upper troposphere, where high clouds form, temperatures are consistently well below freezing, often 30 or 40 degrees below 0 Celsius. At these temperatures, water exists as ice rather than liquid. When water vapor in rising air reaches its dew point at these altitudes, it doesn't condense into liquid droplets. Instead, it deposits directly from vapor into ice crystals, a process called deposition. These ice crystals are different from the rounded droplets in lower clouds. They have geometric shapes, hexagonal plates, needles, columns, and intricate branching dendrites, determined by the temperature and humidity conditions where they form. The crystals are tiny, but their regular structure makes them behave differently than liquid droplets, affecting how they scatter light and how the cloud evolves. Cirrus clouds form high where the air is very cold. You typically find cirrus clouds at altitudes above 20,000 feet, though they can form even higher, sometimes reaching 40,000 feet or more in the tropics. At these heights, the air is thin and the temperature is frigid. The formation of cirrus clouds usually indicates that moist air has reached these high altitudes, perhaps pushed up by large-scale atmospheric motions, or by the exhaust from jet aircraft, which can provide both moisture and condensation nuclei. Because the air is so cold, cirrus clouds persist longer than they would if they were at lower altitudes. There's no risk of the ice crystals melting into droplets that might evaporate. Instead, they can drift for many miles, gradually evaporating as individual crystals sublimate back into water vapor. Ice crystals can make cirrus clouds sparkle softly in sunlight. When sunlight strikes the ice crystals in a cirrus cloud, some of it is reflected directly back, but some passes through the crystal, refracting and bending as it enters and exits. Because the crystals have flat faces and sharp angles, they act like tiny prisms, splitting light into its component colours, or reflecting it in specific directions. When conditions are right, This creates subtle sparkles or a soft shimmer that makes the cloud seem to glow. Unlike the bright white reflection from water droplet clouds, the shimmer from ice crystal clouds has a more delicate quality, sometimes with hints of colour around the edges. Cirrus often appear ahead of changing weather patterns. When you see cirrus clouds thickening and spreading across the sky, it can be a sign that a weather system is approaching. These clouds often form in the rising air ahead of a warm front, where moist air is being lifted gradually over a wedge of colder air. As the front gets closer, the cirrus may thicken into cirrostratus, and then lower into altostratus, and eventually precipitation may begin. This progression doesn't happen quickly. It might take a day or even longer for the weather to arrive after the first cirrus appears, but for centuries people have recognized cirrus as a sign that fair weather might not last. Cirrostratus can create a thin veil across the sky. While cirrus clouds appear as separate strands or patches, cirrostratus forms a more continuous layer, though it's still thin enough to be somewhat transparent. This cloud can cover the entire sky in a milky sheet, turning the blue into a pale, whitish colour. The sun or moon can usually still be seen through cirrostratus, appearing as a bright disk behind the veil. This type of cloud forms when moist air spreads out at high altitude, perhaps as it overruns a front or diverges from a centre of high-level flow. The thinness of the layer, just ice crystals spread throughout a large volume of air, gives it that translucent quality. That thin veil can produce halos around the sun or moon. One of the most beautiful optical phenomena created by clouds occurs when light passes through the ice crystals in cirrostratus. If the crystals are oriented randomly and have the right hexagonal plate structure, they can refract light in a way that creates a halo, a ring of light around the sun or moon. The most common halo has a radius of 22 degrees, which is about the width of an outstretched hand held at arm's length. The halo appears as a bright circle, sometimes with a slight reddish tinge on the inside edge and a bluish tinge on the outside because different colours of light are refracted at slightly different angles. Seeing a halo is a sure sign that there are ice crystals overhead. Even if the cirrostratus is so thin you might not notice it otherwise. Halos happen when light passes through ice crystals and bends. The hexagonal structure of ice crystals creates specific angles between their faces, 60 degrees, 90 degrees, and 120 degrees. When light enters one face of a crystal and exits through another face at one of these angles, it bends by a predictable amount. For the common 22-degree halo, light is entering and exiting through faces that are 60 degrees apart, and the combined refraction creates that specific radius. Other orientations and crystal shapes can create different optical effects. Sundogs, which are bright spots to the left and right of the sun. Light pillars, which are vertical shafts of light above or below the sun or moon. And tangent, arcs, which appear to touch the top or bottom of the halo. Each phenomenon tells you something about the size, shape, and orientation of the ice crystals in the clouds overhead. High clouds can be so thin they look like brush strokes. Sometimes cirrus appears as if someone took a giant paintbrush and swept it across the sky, leaving delicate streaks of white against the blue. These clouds are being shaped by wind at high altitude, stretched and pulled by currents that can reach hundreds of miles per hour. The thinness comes from the fact that there's not much moisture available at such high altitudes. The air is very dry, so only a small amount of water vapor is available to form ice crystals. The result is these ethereal, almost ghostly clouds that seem more like suggestions of clouds rather than substantial structures. They can glow pink or gold at sunrise and sunset. High clouds are among the last to catch sunlight in the evening and the first to be illuminated in the morning. When the sun is below the horizon for an observer on the ground, it can still be shining on clouds many thousands of feet up. At sunrise and sunset, sunlight passes through more of the atmosphere than it does at midday, and the shorter wavelengths, the blues and greens, are scattered away, leaving the longer wavelengths, the reds, oranges, and pinks. These warm colours illuminate the high clouds, making them glow in shades that range from soft pink to deep crimson to brilliant gold. The effect can be spectacular, turning ordinary wispy cirrus into something that looks painted or illuminated from within. High clouds often feel calm because they move slowly across our view. Even though the winds at high altitude can be very strong, the clouds are so far away that their motion appears slow and serene from the ground. A cirrus cloud might be racing along at 100 miles per hour, but because it's 6 or 7 miles above you, It seems to drift lazily across the sky. This distance creates a sense of peace and stillness, even though the actual conditions where the cloud exists are quite dynamic. It's a reminder that our perception of motion depends greatly on perspective and distance, and that the atmosphere is far more active than it appears from our vantage point on the surface. Just one more small fact, and then we drift. Altostratus clouds can make the sky look milky or softly grey. These mid-level layer clouds form a uniform sheet that typically covers the entire sky, creating an overcast condition where you can't see the sun directly, though you might be able to tell where it is as a brighter area behind the cloud layer. Altostratus is thicker than cirrostratus but thinner than the low nimbostratus clouds that produce steady rain. It's composed of water droplets, ice crystals, or both, depending on the temperature at its altitude. The cloud creates a diffuse light, softening shadows and giving the landscape a flat, even illumination. It's the kind of sky that makes photographers happy because there are no harsh contrasts, just gentle gradations of tone. Altocumulus clouds can appear as small patches or ripples. Unlike the uniform sheet of altostratus, altocumulus has texture and structure. It often appears as a field of individual cloudlets or rolls, sometimes arranged in rows or patterns. These clouds form at mid-levels where there's some instability or organization in the atmosphere. Perhaps a layer where rising and sinking air creates a regular pattern, or where gravity waves are propagating through the atmosphere like ripples on water. The individual cloudlets might be white or grey, and they often have shading that gives them a three-dimensional appearance. Looking at a sky filled with altocumulus can be mesmerizing, as the repeated patterns create a sense of order in the chaos of the atmosphere. Some altocumulus patterns are nicknamed mackerel sky. When altocumulus arranges itself in regular rows of small cloudlets, it can resemble the scales on a mackerel fish, hence the name. This pattern often forms when there are waves in the atmosphere, gentle oscillations of air moving up and down in a regular rhythm. The clouds form in the upward moving parts of the wave where air cools and reaches its dew point, while the spaces between represent the downward moving parts where air is sinking and warming. Sailors and weather observers have long recognised mackerel sky as a sign of changing weather, often associated with an approaching front. The old saying goes, mackerel sky, never long wet, never long dry, suggesting unsettled conditions ahead. Low stratus can create an overcast day with a smooth ceiling. When a low-level stratus cloud forms, it can cover the sky completely in a featureless grey layer that might be only a few hundred or 1,000 feet above the ground. This creates the classic dreary, overcast weather where the sky seems to press down and the light is dim and flat. These clouds often form when moist air moves over a cool surface, cooling from below until it reaches its dew point, or when gentle lifting cools an entire air mass uniformly. They can persist for days in stable conditions, especially in coastal areas or during winter when the ground is cold. While they might produce drizzle, often they simply sit overhead, grey and unchanging, filtering what light makes it through into a soft, shadowless glow. Stratocumulus are low, lumpy layers with breaks between patches. These clouds combine characteristics of both stratus and cumulus. They form in layers like stratus, but with some vertical development and texture like cumulus. The result is a field of low clouds that have a bumpy, rolling appearance, with darker areas in the thicker parts and brighter areas where the cloud is thinner or where gaps let sunlight through. Stratocumulus often forms when a layer of stratus begins to break up, or when weak convection creates some vertical motion within a stable layer. These clouds are very common, especially over oceans, and they can cover vast areas. From an airplane, stratocumulus often looks like a landscape of grey hills and valleys stretching to the horizon in all directions. Low clouds can reflect city lights at night, making a bright ceiling. On a cloudy night over a city, the underside of the low clouds often glows with an orange or yellowish light reflected from streetlights, buildings, and signs below. The water droplets in the cloud scatter this light, sending it in all directions, including back down toward the ground. The result is that a cloudy night in the city can be much brighter than a clear night, as if the cloud layer is acting like a giant reflector or screen. The effect can be dramatic, especially when the clouds are low. The entire sky might have a soft artificial glow, bright enough to navigate by without a flashlight. In rural areas without much artificial light, cloudy nights remain dark, but in urban areas, the the clouds transform the night into something much brighter. Low clouds can also soften moonlight into a gentle glow. When the moon is bright and the sky is cloudy, the clouds diffuse the moonlight, spreading it across the entire visible sky rather than concentrating it in a single bright point. This creates an ethereal, silvery illumination that's softer and more even than direct moonlight. The landscape below takes on a dreamlike quality, with gentle shadows and a pale glow that seems to come from everywhere and nowhere at once. It's the kind of light that makes everything look slightly magical, as if the whole world has been placed behind a frosted glass window. Cloud bases often look flat because condensation happens at a similar level. When you look at a field of cumulus clouds, one of the most striking features is that they all seem to sit on an invisible platform. Their bases are at roughly the same height. This happens because the bases mark the altitude where rising air reaches its dew point and condensation begins. For a given air mass with relatively uniform temperature and moisture characteristics, the condensation level will be consistent across a region. Below that level, the rising air is still unsaturated and no cloud forms. Above it, water vapour condenses into droplets, and the cloud becomes visible. The result is that flat, uniform base across many separate clouds. The height of the cloud base depends on temperature and humidity. On a hot, dry day, rising air has to climb quite high before it cools enough to reach its dew point, so cloud bases will be relatively high, perhaps several thousand feet up. On a cool, moist day, the air doesn't have to rise as far to reach saturation, so cloud bases will be lower, sometimes just a few hundred feet above the ground. Meteorologists can calculate the approximate cloud base height using surface temperature and dew point measurements, and this calculation is remarkably reliable. The relationship between these three values, temperature, dew point, and cloud base height, is a direct result of how adiabatic cooling works as air rises. When air is moist, clouds can form closer to the ground. In humid conditions where the air already contains a lot of water vapour, the gap between the actual temperature and the dew point is small. This means rising air doesn't have to cool much before condensation begins. The result is low cloud bases, and in very humid conditions, fog might form at ground level. In tropical regions or in temperate areas during humid summer weather, you often see low, ragged clouds or fog forming in valleys and low-lying areas, especially in the early morning when the air is coolest and most likely to reach saturation. Just one more small fact, and then we drift. Fog is simply a cloud at ground level. There's no fundamental difference between fog and a cloud. Both are made of tiny water droplets or ice crystals suspended in air. The only distinction is that fog is in contact with the ground while clouds are elevated above it. If you're standing on a mountain and a cloud passes over you, you're experiencing fog, even though someone looking up from the valley below would call it a cloud. The processes that create fog are similar to those that create clouds. Air must cool to its dew point so that water vapour condenses. But with fog, this cooling happens near the surface rather than at altitude. Fog forms when air near the ground cools to the dew point. There are several ways this can happen, each creating slightly different types of fog. The air might cool because the ground beneath it has radiated away its heat during the night, or moist air might blow over a cold surface, like warm ocean air moving over cold coastal waters. Or the air might be cooled by mixing with a colder air mass. In each case, the result is the same. The air becomes saturated, water vapour condenses into tiny droplets, and visibility drops as those droplets scatter light and obscure distant objects. Radiational fog often forms on clear nights when the ground cools quickly. After sunset, the ground begins to lose heat through radiation. It emits infrared radiation into space, and without sunlight coming in to replace that lost heat, the ground temperature drops. On a clear night, this cooling can be quite efficient because there are no clouds to trap and reflect the outgoing radiation back down. The ground cools, and the air in contact with the ground also cools. If the air is moist enough, it will reach its dew point and fog will begin to form. This type of fog typically develops after midnight and can be quite thick by dawn. It's most common in valleys and low-lying areas where cool air drains and collects. Valley fog forms when cool air settles into low areas. Cold air is denser than warm air, so it flows downhill, much like water would. On calm nights, cool air slides down slopes and collects in valleys, creating a pool of cold, dense air. If this air is moist, it will saturate and form fog that fills the valley floor. From higher elevations, valley fog can create beautiful scenes, a sea of white filling the low areas while hilltops and mountains remain clear. These fog pools can be quite persistent, lasting well into the morning or even all day in winter, because the cool air is trapped in the valley and the sun's rays may not be strong enough to warm it sufficiently to evaporate the fog. Coastal fog can form when moist air moves over cold water. This is advection fog, caused by horizontal movement of air rather than radiational cooling. When warm, moist air blows across a cold ocean current or cold coastal waters, the lower layers of the air are cooled by contact with the water surface. If the air cools below its dew point, fog forms. This type of fog can be very thick and can persist for days, especially in regions where prevailing winds consistently blow warm air over cold water. San Francisco's famous fog is largely of this type, formed when moist Pacific air moves over the cold California current. The fog rolls in from the ocean, pouring over hills and through valleys, creating dramatic and iconic scenes. Fog droplets are similar to cloud droplets, tiny and suspended. The individual droplets in fog are about 10 to 20 micrometers in diameter, just like cloud droplets. They're small enough to remain suspended in the air, drifting on gentle currents rather than falling to the ground. When you walk through fog, you're moving through billions of these tiny droplets, though you usually only notice them when they accumulate on surfaces. Beads of water on a spider web, moisture on your hair, water dripping from leaves. The droplets are so small that they don't feel like rain. Instead, they create a general dampness, a wetness in the air itself. Fog can make sound feel softer by changing how it travels. Sound waves propagate through air, and anything that affects the air affects how sound travels. The water droplets in fog absorb and scatter sound waves, particularly higher frequency sounds. This has the effect of muffling distant sounds and reducing how far sound carries. In thick fog, the world becomes quieter, more intimate. You might hear sounds close by quite clearly, but anything farther away seems muted or absent entirely. This creates an eerie atmosphere, especially in fog at night, when familiar landscapes become mysterious and sounds seem to come from nowhere and everywhere at once. Fog can make lights look larger due to scattering. When you see a streetlight or a car's headlights through fog, the light appears to spread out, creating a glow or halo much larger than the actual light source. This happens because the water droplets scatter light in all directions. Some of the light from the source hits droplets between you and the light, and those droplets scatter some of that light toward your eyes. This scattered light comes from a region much larger than the light source itself, so the light appears to bloom or spread. The thicker the fog, the more pronounced this effect, until in very dense fog, individual light sources can become just soft glows without clear boundaries. Mist is like thinner fog with slightly better visibility. The distinction between mist and fog is somewhat arbitrary, based on how much the visibility is reduced. Typically, fog is defined as conditions where visibility is less than 1 kilometer, while mist is when visibility is between 1 and 2 kilometers. Both are composed of tiny water droplets suspended in the air, but mist has fewer droplets per volume of air, so it's less dense. Mist creates a softer effect than fog, a slight haziness that takes the edge off distant views without obscuring them completely. It's common in the early morning or evening, or in humid conditions where the air is close to saturation but not quite there. Fog often lifts when sunlight warms the ground and the air mixes. After dawn, as the sun rises and begins to warm the ground in turn warms the air above it. This warming has two effects. It increases the temperature of the air, moving it away from the dew point, and it can create gentle mixing and turbulence that breaks up the stable layer of fog. The fog droplets evaporate back into water vapor, and visibility improves. The lifting often happens from the ground up. You might see the fog thinning at the surface first, while a layer of stratus cloud remains overhead. Eventually, if warming continues, even that layer might dissipate, leaving a clear sky. The process can be quite beautiful to watch, as shafts of sunlight break through thinning fog, illuminating the remaining mist and creating an ethereal landscape. Just one more small fact, and then we drift. Many cloud droplets are too small to fall as rain on their own. A typical cloud droplet, measuring 10 to 20 micrometers across, is far too small and light to overcome air resistance and fall to the ground. it would evaporate long before completing the journey. For precipitation to occur, droplets need to grow much larger, at least 100 times larger in diameter, which represents about 1,000,000 times more volume and mass. A typical raindrop is around 1 to 3 millimeters in diameter, enormous compared to a cloud droplet. The question of how droplets grow from cloud-sized to raindrop-sized has been central to understanding precipitation, and the answer involves several different processes. Droplets can grow by colliding and merging. In a cloud with lots of droplets, especially one with vigorous updrafts that keep the droplets suspended and moving around, droplets frequently bump into each other. When they collide, they can stick together, merging into a single larger droplet. This process is called collision and coalescence. A slightly larger droplet falls a bit faster than smaller ones, so as it falls through the cloud, it sweeps up smaller droplets in its path, growing larger with each collision. The larger it gets, the faster it falls, and the more droplets it collects in a runaway process that can quickly produce drops large enough to fall as rain. This process works best in warm clouds where temperatures are above freezing, and it's responsible for much of the rainfall in tropical regions. This process is called collision coalescence. The name describes exactly what happens. Droplets collide with each other and coalesce, or merge, into larger drops. For the process to work efficiently, the cloud needs to have a range of droplet sizes. If all the droplets are exactly the same size, they fall at the same speed and rarely collide. But if there's a distribution of sizes, some larger droplets falling faster than smaller ones, then collisions become frequent. The larger droplets act as collectors, sweeping through the cloud and gathering smaller droplets like a snowball rolling downhill and gathering more snow. Within a cloud with strong updrafts, droplets can be carried up and down multiple times, colliding and growing on each cycle until they're finally heavy enough that even the strongest updrafts can't keep them aloft. In cold clouds, ice crystals can also grow and fall. When temperatures in a cloud drop below freezing, ice crystals can form alongside supercooled water droplets, liquid droplets that remain liquid even though they're colder than 0 degrees Celsius. This situation creates an interesting dynamic because ice crystals and liquid droplets behave differently. The presence of ice changes how precipitation forms through a process quite different from collision and coalescence. Ice crystals can grow by collecting water vapor more efficiently than droplets. This happens because of a fundamental property of water. At the same temperature below freezing, the saturation vapor pressure over ice is lower than over liquid water. What this means is that in a cloud containing both ice crystals and supercooled droplets, the air can be saturated with respect to the droplets, but supersaturated with respect to the ice. Water vapor will evaporate from the droplets and deposit onto the ice crystals. The crystals grow while the droplets shrink, and over time, the ice crystals can become much larger than the original cloud droplets. This process can be quite rapid, allowing ice crystals to grow to precipitation size relatively quickly. This is part of the Bergeron process. Named after the Norwegian meteorologist Tor Bergeron, who described it in the 1930s, the Bergeron process, also called the Bergeron-Findeisen process or the ice crystal process, explains how precipitation forms in clouds that contain both ice and supercooled water. The process depends on the vapor pressure difference between ice and water, and it's responsible for much of the precipitation in mid-latitude regions, where clouds often extend into below freezing temperatures. The ice crystals that grow through the Bergeron process can become snowflakes, or if they fall through warmer air near the ground, they can melt and fall as rain. When droplets or crystals get heavy enough, they fall as precipitation. Whether grown through collision and coalescence or through the ice crystal process, once a particle in a cloud reaches a certain size and weight, the pull of gravity overcomes the resistance of air and the support of updrafts. The particle begins to fall, and if conditions are right, it will continue falling all the way to the ground. The journey can be several miles long, and it might take many minutes for a raindrop or snowflake to complete it. Along the way, the particle might continue to change, collecting more droplets, partially evaporating, melting if it passes through warm layers, or even being carried back up by strong updrafts in severe storms. Some precipitation evaporates before reaching the ground, especially in dry air. When rain falls through a layer of air that's well below saturation, with low humidity, the drops begin to evaporate. Water molecules leave the liquid drops and become vapor, shrinking the drops. If the layer of dry air is thick enough or the drops are small enough, they can evaporate completely before reaching the surface. This creates an interesting visual phenomenon that meteorologists call virga. Virga is precipitation that falls and evaporates before it arrives. When you see virga, it looks like streaks or curtains of rain or snow trailing beneath a cloud but not reaching the ground. The precipitation starts falling from the cloud base, but as it descends into drier air, it evaporates, creating those characteristic trailing wisps. Virga can occur with all types of precipitation, rain, snow, or ice crystals, and it's particularly common in arid regions where the air near the ground is very dry. Seeing virga is a reminder that precipitation is a process, not just an event, and that the journey from cloud to ground can be complex. Rain is often the final step of a long, gentle growth process inside a cloud. When you feel rain falling on your face, you're experiencing the culmination of processes that might have begun hours earlier and thousands of feet above you. The water in those drops has travelled through the water cycle, evaporated from the ocean or a lake, carried by winds, lifted in rising air, condensed into tiny cloud droplets, grown through collision or the ice process into raindrops, and finally fallen back to earth. The rain will soak into the ground, flow into streams and rivers, perhaps be taken up by plants, and eventually make its way back to the atmosphere to begin the cycle again. It's a process that's been continuing for billions of years, and the rain falling today is part of that ancient ongoing flow. Just one more small fact, and then we drift. Cumulonimbus clouds are tall clouds associated with storms. These are the giants of the cloud world, sometimes reaching heights of 40,000 feet or more, extending from a low base near the ground all the way up to the top of the troposphere. They're the clouds that produce thunderstorms, heavy rain, hail, strong winds, and sometimes tornadoes. But despite their fearsome reputation, they follow the same basic principles as all clouds. They form when moist air rises and cools to its dew point. What makes cumulonimbus different is the scale and intensity of the processes involved. They can grow upward when air is warm and rising strongly. Cumulonimbus forms in conditions of extreme atmospheric instability, where the air near the surface is much warmer than the air aloft. This creates powerful updrafts, columns of rising air that can reach speeds of 50, 60, or even 100 miles per hour in severe storms. These updrafts continuously feed the storm with warm, moist air from below, providing the energy and moisture needed to sustain the towering cloud. The cloud builds upward as the rising air cools and condenses, creating new cloud material at higher and higher altitudes. In the strongest storms, the top of the cloud can reach the tropopause, the boundary between the troposphere and stratosphere, where rising air can go no further. A cumulonimbus cloud can have an anvil-shaped top. When the rising air in a cumulonimbus reaches the tropopause, it can't continue rising because the stratosphere above is stable and warm. Instead, the air spreads out horizontally, flowing away from the updraft in all directions. This creates the characteristic anvil shape, a flat, spreading top that extends far downwind from the main body of the storm. The anvil is composed of ice crystals, since temperatures at these high altitudes are well below freezing. It can be tens of miles wide, and it signals that the storm has reached its maximum vertical extent. The anvil forms when the cloud reaches a stable layer and spreads out. The tropopause acts like a lid on the troposphere, preventing further vertical motion. When the rising air in a thunderstorm hits this lid, it has nowhere to go but sideways. Upper-level winds carry the spreading ice crystals downwind, stretching the anvil in the direction of the wind. Sometimes the anvil can extend for 50 miles or more from the main storm, creating a massive shield of ice cloud overhead. Flying through an anvil in an airplane, you'd experience smooth conditions. The turbulent updrafts are in the main body of the storm, while the anvil is relatively calm, just a vast field of ice crystals drifting slowly downward. Thunderstorms recycle air up and down within the cloud. Inside a mature cumulonimbus, the air is in constant motion. The main updraft carries warm, moist air from near the surface up to high altitudes. But there are also downdrafts, descending currents of cooler air. These form when precipitation starts falling, dragging air down with it, or when evaporation of rain cools the air and makes it negatively buoyant. The downdrafts spread out when they reach the surface, creating gusty winds and sometimes advancing as a gust front ahead of the storm. Meanwhile, the updraft continues to feed the storm from behind. This complex circulation, up in one part of the storm, down in another, is what makes thunderstorms such dynamic, evolving structures. Lightning is an electrical discharge caused by charge separation in the cloud. Inside a thunderstorm, ice crystals, graupel, soft hail, and water droplets are constantly colliding as they rise and fall in the turbulent air. These collisions result in a separation of electrical charge, with lighter, smaller ice crystals becoming positively charged and being carried upward, while heavier, larger particles become negatively charged and accumulate in the middle and lower parts of the cloud. The result is a strong electrical field, with positive charge near the top of the cloud and negative charge in the middle to lower regions. When the electrical potential becomes strong enough to overcome the insulating properties of air, a discharge occurs. Lightning. The lightning can occur within the cloud, between the cloud and the ground, or even between different clouds. Thunder is the sound of rapidly heated air expanding. A lightning bolt is extremely hot, hotter than the surface of the sun, reaching temperatures of around 30,000 degrees Celsius. This intense heat causes the air in the lightning channel to expand explosively, creating a shock wave that propagates outward as sound. That sound is thunder. The rumbling quality of thunder comes from the fact that different parts of the lightning channel are at different distances from you, so the sound arrives at slightly different times. Also, sound waves from the lightning reflect off clouds, the ground, and other surfaces, creating echoes and reverberations that extend the sound into a prolonged rumble. You see the lightning instantly, but the sound travels much slower, about 1 kilometer every 3 seconds, so there's a delay between the flash and the thunder. Not all tall clouds produce severe weather. While cumulonimbus can create impressive storms, many develop and dissipate without producing anything more than some rain, and perhaps a little thunder. The severity of a storm depends on many factors: how unstable the atmosphere is, how much moisture is available, whether there's wind shear that can organize the storm, and weather conditions allow the storm to persist and intensify. Some cumulonimbus clouds are relatively small and short-lived, producing a brief shower and then evaporating. Others develop into supercells, large rotating storms that can persist for hours and produce severe weather including large hail, damaging winds and tornadoes. Understanding which storms will become severe and which won't is one of the challenges of meteorology. Storm clouds still follow basic rules of heat, moisture and motion. Even the most impressive thunderstorm is simply following the fundamental principles that govern all weather. Warm air rises, rising air cools and can condense its moisture. Condensation releases latent heat that fuels further rising, and the atmosphere constantly works to redistribute heat and moisture from areas of excess to areas of deficit. A thunderstorm is just a particularly energetic expression of these principles, a dramatic way for the atmosphere to move heat from the warm, moist boundary layer up to the cooler upper atmosphere. The storm is temporary. Once the instability is relieved and the available moisture is depleted, the storm weakens and dissipates, leaving behind cooler, more stable conditions. Even strong clouds are part of the atmosphere balancing energy. The Earth receives energy from the sun, with more energy arriving at the equator than at the poles. The atmosphere and oceans work constantly to redistribute this energy, moving heat from warm regions toward cooler ones. Clouds play a crucial role in this redistribution. When water evaporates, it absorbs energy as latent heat. This energy is carried with the water vapor as it moves through the atmosphere. When the vapor condenses into clouds and precipitation, that latent heat is released, warming the surrounding air. This heating can drive further motion and weather patterns. Storms, in particular, are efficient at moving heat upward and poleward, helping the planet maintain its energy balance. From this perspective, even the most violent thunderstorm is simply the atmosphere doing its job, moving energy from where it's abundant to where it's needed. Just one more small fact and then we drift. Clouds can cool Earth by reflecting sunlight back to space. When sunlight strikes the top of a cloud, much of it is reflected, bounced back towards space without ever reaching the Earth's surface. This is especially true for thick, bright clouds that act like giant mirrors. The reflected sunlight carries energy away from the Earth system, energy that would otherwise be absorbed by the land or ocean and converted to heat. This cooling effect is significant. On a cloudy day, temperatures are typically several degrees cooler than on a sunny day, with similar conditions, precisely because the clouds are blocking some of the incoming solar radiation. This reflective effect is called albedo. Albedo is a measure of how much light or radiation a surface reflects. A perfectly reflective surface has an albedo of 1 or 100%, while a perfectly absorbing surface has an albedo of 0. Fresh snow has a high albedo, around 80 to 90%. Dark ocean water has a low albedo, around 6%. Clouds have albedos that vary depending on their thickness and composition, but typically range from 30 to 90%. Thick stratus or stratocumulus clouds can reflect as much as 90% of the sunlight hitting them, making them highly effective at cooling the planet. This reflective property is one reason why clouds are so important in regulating Earth's temperature. Thick, bright clouds generally reflect more sunlight. The reflectivity of a cloud depends mainly on how many droplets or ice crystals it contains and how thick it is. A thick cloud has more opportunities to scatter and reflect incoming sunlight. Photons bounce from droplet to droplet, and many eventually bounce back out the top of the cloud. A thin cloud allows more light to pass through. Similarly, clouds with many small droplets are more reflective than clouds with fewer large droplets, because the total surface area available for scattering is greater. This is why marine stratocumulus clouds, which cover vast areas of ocean and contain many small droplets, have such high albedos and play such an important role in Earth's energy balance. Clouds can also warm Earth by trapping some outgoing heat. Earth doesn't just receive energy from the sun, it also radiates energy back to space in the form of infrared radiation. This outgoing radiation is how Earth cools itself, maintaining a balance between incoming solar energy and outgoing thermal energy. But clouds can interfere with this cooling process. The water droplets and ice crystals in clouds absorb some of the outgoing infrared radiation and re-emit it in all directions, including back down toward the surface. This acts like a blanket, reducing the rate at which Earth loses heat to space. This warming effect is like a blanket that slows heat loss. On a clear night, the ground can cool rapidly through radiational cooling, losing heat directly to space. The temperature can drop significantly, and frost might form if conditions are right. But on a cloudy night, the clouds intercept much of the outgoing infrared radiation and radiate some of it back to the ground. The result is that temperatures don't drop as much. The low temperature on a cloudy night might be 5 or 10 degrees warmer than on a clear night with similar conditions. This is the greenhouse effect of clouds, and it's particularly strong with low, thick clouds that are close to the surface. High, thin clouds often trap heat more than they reflect sunlight. For high cirrus clouds, the warming effect can dominate over the cooling effect. These clouds are thin enough that they don't reflect much incoming solar radiation. Much of the sunlight passes right through them, but they're very cold, which makes them effective at absorbing outgoing infrared radiation from the warm surface below. They then re-emit this radiation, but because they're so cold, they emit at longer wavelengths and with less intensity, and much of what they emit goes sideways or down rather than up to space. The net effect is that high thin clouds tend to warm the planet slightly, trapping more heat than they reflect. Low thick clouds often reflect sunlight strongly and can cool the surface. Conversely, low stratocumulus or stratus clouds are very effective at reflecting sunlight because they're thick and bright, but they're not as effective at trapping outgoing infrared radiation because they're relatively warm. Their temperature is similar to the surface below. The net effect is that these clouds tend to cool the planet. The vast decks of stratocumulus that cover subtropical and mid-latitude oceans are thought to have a significant net cooling effect on Earth's climate, and changes in these clouds could substantially affect global temperatures. Cloud effects depend on cloud type, thickness, and height. The radiative effect of any given cloud is the result of a complex interplay between its reflective properties, which depend on thickness, droplet size, and composition, and its thermal properties, which depend on temperature and thus height. Scientists use detailed measurements from satellites and aircraft to study these properties and incorporate them into climate models. Understanding clouds remains one of the biggest challenges in climate science because clouds can both cool and warm, and their net effect depends on details that can vary with time and location. Clouds help distribute heat by releasing latent heat when water condenses. Beyond their radiative effects, clouds play an active role in moving heat around the atmosphere through the water cycle. When water evaporates from the ocean, it absorbs a large amount of energy, about 2.5 million joules per kilogram, which is stored as latent heat in the water vapour. This vapour can be transported over long distances by winds, When it finally condenses into clouds, that stored energy is released, warming the air. This process moves heat from the surface, where evaporation occurred, to higher altitudes or different latitudes where condensation occurs. It's a crucial mechanism for redistributing energy in the atmosphere. That released heat can influence winds and weather patterns. The warming that occurs when water vapor condenses can strengthen updrafts, intensify storms, and drive larger-scale atmospheric circulations. In tropical regions, the enormous amount of latent heat released by deep convective clouds helps drive the Hadley circulation, which moves air from the equator toward the poles. In mid-latitudes, the release of latent heat in storm systems can intensify low-pressure centers and strengthen winds. The interaction between moisture, condensation, latent heat release, and atmospheric motion is a fundamental part of how weather works, and it's all intimately connected to clouds. Just one more small fact, and then we drift. Your breath contains water vapor. Every time you exhale, you're releasing water into the air. This water comes from the moist surfaces in your lungs, water that has evaporated from the linings of your airways and alveoli. The air you breathe out is saturated with this water vapor at body temperature. You can't normally see this vapor because it's invisible, just like the water vapor in the atmosphere, but you can see evidence of it under the right conditions. Warm breath can briefly fog a cold window because vapor condenses into droplets. When you breathe onto a cold window on a winter day, the warm, moist air from your lungs encounters the cold glass surface. The glass cools the air immediately next to it, and that air quickly reaches its dew point. Water vapor condenses into tiny droplets on the glass, creating fog or mist that temporarily obscures your view. Within moments, the droplets might evaporate again as they warm up, or they might run down the glass in little rivulets. This simple phenomenon is a miniature version of what happens when clouds form. Warm, moist air cooled to its dew point, resulting in visible water droplets. Indoor air can be dry or humid depending on temperature and ventilation. The humidity inside a building depends on many factors: how much moisture is being added to the air through cooking, showering, breathing, and plants, how much moisture is being removed through ventilation or dehumidifiers, and the temperature, since warm air can hold more moisture than cool air. In winter, heated indoor air often becomes very dry because the heating process doesn't add moisture, and the cold outdoor air that infiltrates contains little moisture to begin with. In summer, indoor air might be more humid, especially in climates where the outdoor air is humid and ventilation brings that moisture inside. Humidity changes how warm or cool the air feels on your skin. When the air is dry, sweat evaporates readily from your skin, and this evaporation cools you. It's your body's primary cooling mechanism. But when the air is humid, evaporation slows because the air is already close to saturation and can't accept much more water vapor. As a result, you feel warmer and more uncomfortable at the same temperature. This is why a hot, humid day feels much worse than a hot, dry day, even though the actual air temperature might be the same. The humidity affects your comfort directly through its impact on evaporative cooling. Outside, clouds are constantly forming and dissolving. The sky is never truly static. At any given moment, somewhere in the atmosphere, air is rising and cooling, water vapor is condensing, and new clouds are forming. Simultaneously, other clouds are evaporating, their droplets turning back into vapor as they mix with drier air or warm up. Some clouds persist for hours, growing and evolving. Others last only minutes, appearing briefly and then vanishing as conditions change. This constant formation and dissolution is part of the dynamic nature of the atmosphere, which is always in motion, always responding to the unequal heating of Earth's surface and the rotation of the planet. A cloud can be temporary, but the water in it continues the cycle. The cloud you see drifting overhead might dissipate within the hour, its droplets evaporating back into invisible vapor. But the water molecules that made up those droplets don't disappear, they simply change form. They might remain as vapor for days, travelling hundreds of miles on the wind before condensing again into a different cloud. Or they might condense and fall as rain within hours, only to evaporate from a puddle and return to the atmosphere. Each water molecule is on a continuous journey through the water cycle, spending time as vapor, as cloud droplets, as rain, as ocean, as ice, as groundwater, as part of a plant, and then back to vapor again. The same water can move from ocean to cloud to rain and back again. If you could follow a single water molecule through its travels, you'd see a complex path. Perhaps it evaporates from the Pacific Ocean, rises in a thermal over a warm spot, condenses into a cloud, falls as rain on a forest, soaks into the soil, is taken up by a tree, transpires from a leaf back into the atmosphere, condenses in another cloud, falls as rain again, flows into a stream, travels to a river, and eventually makes its way back to the ocean. This journey might take days, or weeks, or years, but it's all part of the same continuous cycle that has been operating for as long as Earth has had water and an atmosphere. Clouds are proof that invisible air can carry hidden moisture. When you look at a clear blue sky, it's easy to forget that the air contains water, invisible water vapor mixed throughout the atmosphere. But clouds make this invisible moisture visible. They're like markers, showing where the air has risen and cooled enough to release its hidden water. Every cloud is evidence of moisture that was there all along, just waiting for the right conditions to reveal itself. In this way, clouds help us see something we couldn't otherwise perceive: the water content of the air, the vertical motions of the atmosphere, the processes that drive weather and climate. Tonight, you can let thoughts behave like clouds, arrive, change shape, and pass. As you rest, consider that thoughts are a bit like clouds. They appear in consciousness, sometimes small and wispy, sometimes larger and more substantial, sometimes charged with emotion like a thundercloud. But like clouds, thoughts are temporary. They form, they persist for a while, they change and evolve, and eventually they dissipate. You don't have to hold on to them or push them away. You can simply watch them drift by, acknowledging them without getting caught up in them, knowing that each thought will pass just as clouds pass across the sky. And as you rest, the sky keeps writing slowly, patient, harmless and rhythmic. Above you, even if you can't see it, the atmosphere continues its ancient work. Air rises and falls, moisture condenses and evaporates, clouds form and dissolve. The processes are gentle, continuous, and utterly indifferent to human concerns. They've been happening for billions of years, long before there were people to observe them, and they'll continue long after we're gone. There's something peaceful in that, the knowledge that these vast, slow processes continue, regardless, that the sky will keep creating its ephemeral sculptures of water and air, writing and rewriting its story in droplets and ice crystals, patient and endless and beautiful. Just one more small fact, and then we drift. The clouds you saw today are gone now, evaporated or transformed or fallen as rain somewhere distant. But new clouds are forming even as you close your eyes, and tomorrow there will be new shapes in the sky, new patterns of light and shadow, new evidence of the atmosphere's constant motion. The water cycle continues, clouds rise and fall, and the gentle processes that govern vapor and droplets and ice continue their work. Quiet and patient and eternal. Rest now, knowing that these processes require nothing from you, that they'll continue through the night while you sleep, that when you wake the sky will have written something new, and that all of it, every cloud, every drop of rain, every crystal of ice, is part of something ancient and beautiful and fundamentally peaceful. The next story is about to begin. Please relax and enjoy. The sun is a star at the center of our solar system. It sits there, quiet and enormous, anchoring everything around it with gravity and light. When you think about the sun, you might picture something fierce or blinding, but tonight we're going to think about it differently. Tonight the sun is just a steady presence, a kind of cosmic hearth that has been burning gently for longer than anything you can imagine. There's no urgency here, no need to hold on to these facts too tightly. They're just here to keep you company as your mind begins to settle, as your breathing slows, and as the day finally releases its hold on you. The sun is a huge sphere of hot gas, mostly hydrogen and helium. That's all it is, really. Gas, held together by its own gravity, compressed and heated until it glows. There's something calming about that simplicity. No solid ground, no surface you could stand on, just layers of gas pressing inward, getting hotter and denser the deeper you go. The sun contains most of the solar system's total mass. When scientists add up everything in our neighborhood of space, all the planets, all the moons, all the asteroids and comets and dust, the sun accounts for more than 99% of it all. Everything else, including Earth, is just a collection of leftovers, small fragments that didn't fall into the sun when the solar system was forming. The sun's gravity holds the planets in their orbits. That invisible pull reaches out across millions and billions of miles keeping Earth on its steady path year after year, century after century. We orbit because the Sun is there, massive and patient, never letting go. The Sun looks constant, but it is always active in gentle ways. If you could watch it closely over hours or days, you'd see patterns shifting across its surface, bright regions and dark regions coming and going, loops of glowing gas rising and falling. But from here, from Earth, it just looks like a steady circle of light. That's okay. You don't need to see the details to feel the constancy. The Sun's energy comes from nuclear fusion in its core. Deep inside, where the pressure is immense and the temperature climbs to millions of degrees, hydrogen atoms are squeezed together so tightly that they combine. Fusion combines hydrogen into helium. 4 hydrogen nuclei become 1 helium nucleus, and in that transformation, a tiny amount of mass is converted into energy. It's the same process that powers hydrogen bombs, but in the Sun it happens in a controlled, sustained way, not as an explosion but as a continuous burn that has lasted for billions of years. Fusion releases energy as light and heat. That energy starts deep in the core, but it doesn't escape right away. It takes a long, slow journey outward, bouncing and scattering through the Sun's inner layers, sometimes taking hundreds of thousands of years to work its way from the center to the surface. By the time it reaches the surface and radiates out into space, it's the sunlight you know, the warmth on your skin, the brightness in the sky. The Sun has been shining for billions of years, about 4.5 billion years to be more precise, though precision isn't really the point tonight. The point is just to know that the Sun is old, ancient even, and that it has been doing this same steady work since long before there were people to notice it, long before there was anything alive on Earth at all. The Sun is close compared with other stars, which is why it looks so large in our sky. The nearest star beyond the Sun is more than 4 light-years away, a distance so great that even travelling at the speed of light, the fastest anything can go, it would take over 4 years to get there. The Sun, by contrast, is only 8 light-minutes away, close enough that its light reaches us in the time it takes to boil water or listen to a couple of songs. That closeness is what makes the Sun special to us, what makes it the Sun and not just another point of light. Just one more small fact, and then we drift. Sunlight takes time to travel to Earth. Even though light is fast, the fastest thing there is, it still needs time to cross the distance between the Sun and our planet. That travel time is a little over 8 minutes, 8 minutes and 20 seconds if you want to be exact, though again, exactness can wait for another day. When you feel sunlight, you're receiving a message from minutes ago. The light that touches your face left the Sun's surface 8 minutes earlier. In a way, you're always seeing the Sun as it was, not as it is. It's a small delay, barely noticeable, but it's there. A reminder that even light has to travel, that even the fastest things take time. The Sun's light spreads outward in all directions. It doesn't aim for Earth specifically. It just radiates, sending energy out in every direction equally, and Earth happens to be in the path of a tiny sliver of that outward flow. Earth receives only a small fraction of the Sun's total output. If you imagine the Sun's energy as a sphere expanding outward, Earth would intercept only about 1 part in 2 billion of it. Everything else flies off into space, warming nothing, lighting nothing, just travelling outward until it fades into the cold emptiness between stars. Even that small fraction is enough to power weather and life. Every gust of wind, every rainstorm, every growing plant, every breath you take, all of it traces back to that thin stream of sunlight falling on Earth's surface, day after day, year after year. Sunlight includes many wavelengths, not just visible light. When you see sunlight, you're seeing only a narrow band of the electromagnetic spectrum, the part your eyes happen to be sensitive to. But sunlight also carries wavelengths you can't see. Some sunlight is infrared, which we feel as warmth. You can't see infrared light, but you can feel it when you stand in the sun and your skin grows warmer. That warmth is just another form of light, vibrating at frequencies too slow for your eyes to detect. Some sunlight is ultraviolet, which Earth's atmosphere helps filter. Ultraviolet light carries more energy than visible light, enough to damage living cells if too much gets through, but the ozone layer high in the atmosphere absorbs most of it before it reaches the ground. What does get through is enough to tan your skin or, over time, cause sunburn, but it's a small fraction of what the sun actually emits. Daylight on Earth is a gentle result of rotation, not the sun turning on and off. The sun doesn't sleep. It doesn't dim at night. Night happens because Earth turns, rotating on its axis once every 24 hours, and as it turns, different parts of the planet face toward the sun or away from it. When your part of Earth turns away, the sun's light is blocked by the planet itself, and you experience night. When your part turns back toward the sun, light returns, and you have day. It's a slow, steady spin, one that's been going on for as long as Earth has existed, and it will keep going long after you've drifted off to sleep tonight. Just one more small fact, and then we drift. The sun has layers, like a deep, glowing onion of heat. If you could slice the sun open, not that you'd want to, not that you could, you'd see that it's not uniform all the way through. The core is where fusion happens. That's the centre, the hottest and densest part, where hydrogen becomes helium and energy is born. The core is small compared to the sun's total size, only about a quarter of the sun's radius, but it contains more than half of the sun's mass, all of it squeezed down by the weight of everything above it. Outside the core is the radiative zone. This is a thick shell of gas where energy from the core begins its slow journey outward. In the radiative zone, energy moves outward mainly by radiation. Photons of light are emitted, absorbed, re-emitted, absorbed again, bouncing around in a random walk that takes thousands or even hundreds of thousands of years to complete. It's not a straight path. It's a chaotic, wandering journey, each photon scattering off particles of gas, changing direction over and over, inching outward bit by bit. Beyond that is the convective zone. Here the gas is cooler and less dense than in the radiative zone, and energy starts to move in a different way. In the convective zone, hot material rises and cooler material sinks. It's like a pot of water simmering on a stove, where heat at the bottom causes the water to rise, and cooler water at the top sinks back down to take its place. This slow churning helps bring energy toward the surface. The convective zone is where the sun's internal heat starts to become something you could almost recognize, where the abstract energy of fusion becomes the motion of gas, rising and falling in great loops that span thousands of miles. The sun's visible surface is called the photosphere. This is the layer you see when you look at the sun, though you shouldn't look directly, of course. The photosphere is where the sun's gas becomes thin enough that light can escape into space. Below this, the gas is too dense, too opaque, and light just gets absorbed and re-emitted over and over. Above this, the gas is too thin to emit much light at all. The photosphere is the Goldilocks layer, the place where conditions are just right for light to break free and travel outward. Above the photosphere is the chromosphere. This is a thin layer of gas that glows faintly, usually only visible during a solar eclipse when the bright photosphere is blocked. The chromosphere is hotter than the photosphere, which seems strange. You'd expect the sun to get cooler as you move away from the core, but the reasons for this heating are still being studied. Farther out is the corona, the sun's outer atmosphere. The corona extends far into space, millions of miles out, fading gradually until it blends into the solar wind. The corona is also surprisingly hot, even hotter than the chromosphere, reaching temperatures of 1,000,000 degrees or more. How the corona gets so hot is one of the ongoing puzzles in solar physics, something scientists are still working to understand. But for now, tonight, you don't need to solve it. You just need to know it's there, a vast glowing halo surrounding the sun, invisible most of the time but always present. Just one more small fact, and then we drift. The sun's surface looks textured because of convection. If you could see the sun up close, if you had a telescope powerful enough and filters dark enough to protect your eyes, you'd notice that the surface isn't smooth. It looks grainy, covered in a shifting pattern of bright cells surrounded by darker lanes. Those bright, grainy cells are called granules. Each granule is a region of rising hot gas. The gas rises because it's hotter and less dense than the gas around it, buoyed upward by convection. When it reaches the surface, it spreads out, cools slightly, and then sinks back down. The darker edges are where cooler gas sinks back down. It's a continuous cycle, each granule lasting only about 10 or 20 minutes before it breaks up and reforms. The pattern is always there, always changing, like the surface of a slowly simmering soup. This pattern is like slow simmering, not violent motion. It's easy to imagine the sun as a violent, explosive place, but most of what happens there is actually quite gradual. The gas moves, yes, but not at terrifying speeds. The granules rise and fall at a few hundred meters per second, which sounds fast until you remember how large the sun is. On a human scale, it would be like watching paint dry, or watching clouds drift across the sky. Gentle, inevitable, calm. The sun rotates, but not all parts rotate at the same speed. The sun isn't a solid object, so different parts of it can rotate at different rates. The equator rotates faster than the regions near the poles. At the equator, the sun completes one rotation in about 25 days. Near the poles, it takes closer to 35 days. This is called differential rotation, and it happens because the sun is made of gas and plasma, not rock or metal. There's no rigid surface to keep everything moving together. The sun's rotation helps shape its magnetic field. As the sun rotates, it drags its magnetic field along with it, twisting and stretching the field lines. The magnetic field is always changing and shifting. It's not a simple bar magnet, North Pole and South Pole neat and symmetrical. It's a tangled, complex structure with loops and knots and regions where the field is strong and regions where it's weak. Much of the sun's activity is really magnetic patterns moving over time. Sunspots, flares, prominences, all of these are driven by the sun's magnetic field, by the way the field twists and reconnects and releases energy. Just one more small fact and then we drift. Sunspots are darker regions on the sun's surface. They're not actually dark. If you could see a sunspot on its own, it would glow brightly, hot enough to vaporize any material you can think of. But they look dark compared to the surrounding areas because they're cooler. They look dark because they are cooler than surrounding areas. A typical sunspot might have a temperature of around 3,500 degrees Celsius, while the rest of the photosphere is closer to 5,500 degrees. That difference is enough to make them stand out as dark patches against the bright background. Sunspots are linked to strong magnetic fields. Where the sun's magnetic field is particularly strong, it can inhibit the convection that normally brings heat to the surface. The result is a region that's slightly cooler and therefore slightly darker. Sunspots can appear alone or in groups. Sometimes you'll see just one or two small spots. Other times you'll see large complex groups with dozens of spots clustered together, some of them larger than the entire Earth. Sunspots change over days and weeks. They grow, they shrink, they merge with other spots or split apart. They drift across the sun's surface as the sun rotates, appearing on one side, moving across the face of the sun, and then disappearing around the other side. If you watch the sun every day, you'd see them come and go, a slow parade of dark patches marching across the glowing disk. The sun can also have bright regions called faculae. These are areas where the magnetic field is strong, but the effect is different. Instead of cooling the surface, the field allows more heat to escape, making these regions brighter than their surroundings. Faculae are often easier to notice near the sun's edge. Near the centre of the sun's disk, they don't stand out much, but near the edge, where you're looking through the sun's atmosphere at an angle, they become more visible, like bright streaks or patches. Prominences are loops of glowing plasma arcing above the surface. Plasma is just gas that's so hot its atoms have lost some of their electrons, giving it special properties and allowing it to respond to magnetic fields. Prominences follow magnetic field lines like slow ribbons. They can stretch for tens of thousands of miles, great arcs of glowing gas suspended above the sun's surface, held in place by invisible magnetic forces. Some prominences are stable, lasting for days or even weeks. Others are more dynamic, rising and falling, sometimes erupting outward into space. Many solar features are beautiful examples of physics staying organized. Despite the heat, despite the chaos of all that gas churning and boiling, the sun's magnetic field creates structure. It organizes the chaos into patterns, loops, arcs, spots, bright regions and dark regions. It's a reminder that even in extreme environments, physics still works, still creates order, still follows rules. Just one more small fact, and then we drift. The corona is the sun's outer atmosphere. It's the part of the sun that extends farthest into space, a vast halo of hot, thin gas that surrounds the visible disk. The corona extends far into space. There's no sharp boundary where the corona ends. It just fades gradually, becoming thinner and thinner until it blends into the solar wind and the space between planets. During a total solar eclipse, when the moon blocks the bright photosphere, the corona becomes visible as a pearly white glow surrounding the darkened sun, with delicate streamers and plumes extending outward. The corona is surprisingly hot compared with the surface below. The photosphere, the visible surface, is about 5,500 degrees Celsius. The corona, despite being farther from the core, is more than 1,000,000 degrees Celsius. This is one of the great mysteries of solar physics. Heat normally flows from hotter regions to cooler regions, so you'd expect the temperature to drop as you move away from the sun's core. But the corona defies that expectation. Scientists study the corona to understand heating and magnetic effects. Current theories suggest that the sun's magnetic field plays a key role, perhaps releasing energy as field lines twist and snap and reconnect, heating the surrounding gas. It's still an active area of research, still something scientists are working to fully understand. The sun releases a steady flow of particles called the solar wind. The corona is so hot that it's not gravitationally bound to the sun. The gas has enough energy to escape, streaming outward in all directions. The solar wind moves outward through the solar system. It's not a fast wind by the standards of, say, a hurricane, but it's steady, flowing past Earth at a few hundred kilometers per second, carrying charged particles, electrons, protons, and heavier ions, out into space. Earth's magnetic field helps deflect many solar wind particles. The Earth has its own magnetic field, generated by the motion of molten iron in its core, and that magnetic field acts like a shield, deflecting most of the solar wind around the planet. The solar wind helps shape Earth's space environment. It compresses the magnetic field on the side facing the sun and stretches it out into a long tail on the night side, creating a region called the magnetosphere. Changes in the solar wind can influence auroras on Earth. When the solar wind is stronger or more turbulent, it can disturb Earth's magnetic field, sending particles spiraling down into the atmosphere near the poles, where they collide with air molecules and create the shimmering lights of the aurora borealis and aurora australis. Most of the time, the solar wind is a quiet, continuous stream. It's not dramatic. It's not something you'd notice unless you had the right instruments. It's just there, a gentle breeze of particles flowing outward from the sun, day after day, year after year, filling the space between worlds. Just one more small fact, and then we drift. The sun has an activity cycle that rises and falls over time. This is often called the solar cycle. The number of sunspots, the frequency of flares, the intensity of the solar wind, all of these vary in a regular pattern. The cycle is about 11 years long on average. Sometimes it's a bit shorter, sometimes a bit longer, but 11 years is a good rough estimate. During higher activity, sunspots are more common. There might be dozens or even hundreds of sunspots visible at any given time, clustered in bands north and south of the sun's equator. During lower activity, sunspots are fewer. At solar minimum, the quiet part of the cycle, there might be weeks or even months when the sun's surface is completely spotless, smooth and bright from edge to edge. The solar cycle is connected to changes in the sun's magnetic field. Over the course of a cycle, the sun's magnetic field gradually becomes more tangled and complex, and then it reorganizes itself, resetting to a simpler state before starting the process all over again. Over a cycle, the sun's magnetic poles switch. The north magnetic pole becomes the south magnetic pole and vice versa. It takes about 11 years for this switch to happen, and then another 11 years to switch back. So a complete magnetic cycle is actually about 22 years. The sun cycle is like a slow heartbeat rather than a sudden switch. It's not that the sun turns on and off. It's more like a rhythm, a gentle rise and fall in activity, a breathing in and breathing out. The cycle affects the frequency of solar flares and eruptions. Solar flares are sudden bursts of energy, bright flashes of light and radiation that can occur when magnetic field lines snap and reconnect. They're more common during solar maximum, the active part of the cycle, but they can happen at any time. Even then, the sun remains a steady, reliable source of light for Earth. The changes in the cycle are real, but they're small compared to the sun's overall output. The amount of light reaching Earth varies by less than 1% over the cycle. You wouldn't notice it in your daily life. The sun still rises and sets, still warms the Earth, still drives the weather and the seasons, regardless of where it is in its cycle. Just one more small fact, and then we drift. The sun is the main source of energy for Earth's climate system. Almost all the energy that drives weather, ocean currents, and the water cycle comes from the sun. Sunlight warms land and oceans. When sunlight strikes the surface of the Earth, Some of it is reflected back into space, but most of it is absorbed, heating the ground and the water. Warmth drives evaporation, which helps form clouds and rain. Water evaporates from the oceans, from lakes and rivers, from the soil and from the leaves of plants, rising into the atmosphere as invisible vapor. When that vapor cools and condenses, it forms clouds, and eventually the water falls back to the surface as rain or snow, completing the cycle. Earth seasons are caused by Earth's tilt, not Earth's distance from the Sun. Earth's orbit around the Sun is nearly circular, so the distance between Earth and the Sun doesn't change much over the course of a year. What does change is the angle at which sunlight strikes different parts of the planet. Earth's axis is tilted about 23.5 degrees relative to its orbit, and that tilt means that during part of the year, the northern hemisphere is tilted toward the Sun, receiving more direct sunlight and experiencing summer, while the southern hemisphere is tilted away, receiving less direct sunlight and experiencing winter. 6 months later, the situation is reversed. Day length changes through the year because of that tilt. In summer, the sun rises earlier and sets later, giving you more hours of daylight. In winter, the sun rises later and sets earlier, and the days are shorter. At the equator, where the tilt has less effect, day length stays roughly the same all year round. At the poles, the effect is extreme. During summer, the sun never sets, and during winter, it never rises. Sunlight helps set many biological rhythms in living things. Plants and animals, including humans, have evolved in a world where light comes and goes in a regular cycle, and their internal biology reflects that. Morning light is a strong cue for the body's internal clock. When light enters your eyes in the morning, it signals to your brain that it's time to wake up, time to be active. This helps synchronize your circadian rhythm, your internal sense of time, with the external cycle of day and night. The sun's position helps guide animal migration and navigation. Many birds, for example, use the position of the sun in the sky to help them find their way during migration. They have an internal sense of time that allows them to compensate for the sun's movement across the sky, effectively using the sun as a compass. Plants respond to sunlight for growth and timing. They grow toward the light, a process called phototropism, and many plants also track the time of year based on the length of the day, using that information to decide when to flower or when to drop their leaves. Even indoors, your day-night rhythm is still connected to the sun. Even if you spend most of your time inside, away from direct sunlight, the cycle of light and dark still affects you. Artificial light can mimic some of the effects of sunlight, but it's not quite the same. Natural light has a quality, a spectrum, and an intensity that your body recognizes and responds to. The sun, in a sense, is still part of your daily life, even when you're not thinking about it, even when you're asleep. Just one more small fact, and then we drift. The sun is one star among hundreds of billions in the Milky Way. Our galaxy, the Milky Way, is a vast spiral of stars, gas and dust, stretching across about 100,000 light-years. The sun is just one of those stars located out in one of the spiral arms about halfway, between the centre of the galaxy and the edge. It is a medium-sized star, not the largest type. There are stars much larger than the sun, giants and supergiants that dwarf it in size and brightness. And there are stars much smaller, red dwarfs that glow faintly and burn their fuel so slowly they could last for trillions of years. The sun is somewhere in the middle, a perfectly average, ordinary star. The sun's age is about 4.6 billion years. That's a number so large it's hard to grasp, but it means the sun is old. Older than any rock on Earth. Older than the Earth itself. The sun formed from a cloud of gas and dust. Somewhere in the Milky Way, about 4.5 billion years ago, there was a cloud of gas, mostly hydrogen and helium left over from the Big Bang, mixed with heavier elements created in earlier generations of stars. Something, perhaps the shock wave from a nearby supernova, perhaps just the cloud's own gravity, caused the cloud to start collapsing. As it collapsed, it began to spin, and most of the material fell toward the centre, forming the sun. That same cloud also formed the planets. The leftover material, the part that didn't fall into the sun, formed a disk around the young star. In that disk, dust grains stuck together, forming larger and larger clumps, and eventually those clumps became the planets, moons, asteroids, and comets of the solar system. Everything you see in the night sky, everything in our solar system, came from that same cloud. The sun will not shine the same way forever, but its changes are slow. The sun is slowly getting brighter as it ages, as the helium accumulates in its core and the fusion process becomes slightly more efficient. Billions of years from now, the sun will run out of hydrogen in its core and begin to change more dramatically, swelling into a red giant and eventually shedding its outer layers. But those changes are so far in the future that they're almost irrelevant. The sun's life is measured in billions of years. On human timescales, it is wonderfully steady. It has been shining for as long as there has been life on Earth, and it will continue to shine, essentially unchanged, for as long as anyone alive today could ever need to care about. The elements in your body were formed in earlier generations of stars. The hydrogen in your body is primordial, left over from the Big Bang, but the carbon, nitrogen, oxygen, and all the other heavier elements were created inside stars that lived and died long before the sun was born. Those stars fused lighter elements into heavier ones, and when they died, some quietly, some in spectacular supernova explosions, they scattered those elements into space, enriching the gas clouds that would eventually form new stars and planets. The sun is part of that long chain of cosmic recycling. The atoms in your body, the iron in your blood, the calcium in your bones, all of it came from stars. You are quite literally made of stardust, and the sun is the latest star in a long lineage to illuminate your world. Just one more small fact, and then we drift. Sunlight in the morning can help set your circadian rhythm for the day. Your body has an internal clock, a biological timer that runs on a cycle of about 24 hours, and light is the main signal that keeps that clock synchronized with the outside world. When light enters your eyes, especially bright blue-rich light like the kind you get from the sun in the morning, it sends a signal to a part of your brain called the suprachiasmatic nucleus, which acts as the master clock for your body. That signal tells your brain it's daytime, it's time to be awake and alert, and it helps set the timing for all the other rhythms in your body. When you feel hungry, when you feel sleepy, when your body temperature rises and falls. Darkness at night helps your brain prepare for sleep. When the sun sets and light levels drop, your brain starts to produce melatonin, a hormone that makes you feel drowsy and helps you fall asleep. The absence of light is just as important as the presence of light, a signal that tells your body it's time to rest. The sun's daily cycle is a gentle cue your body has evolved with. For millions of years, for all of human history until very recently, people lived their lives in sync with the sun. They woke when the sun rose and slept when it set. Artificial light has changed that, allowing us to stay awake long after dark, but our biology still remembers the old pattern. The sun's rhythm is still written into our cells. Warmth from sunlight can be stored in walls, floors, and oceans. During the day, sunlight heats surfaces, and those surfaces hold on to that heat for a while, releasing it slowly over time. A brick wall or a concrete floor can absorb heat during the day and radiate it back out at night, keeping a room warm even after the sun has set. The oceans, with their vast capacity to store heat, absorb sunlight during the summer and release it, during the winter, moderating the climate and keeping temperatures from swinging too wildly. Evening comfort often comes from the day's heat slowly releasing. When you sit outside on a warm evening, the warmth you feel might not be from the sun directly. It might have set already, but from the heat that the ground and the buildings absorb during the day, now gently radiating back out into the cooling air. The sun's light can feel like a quiet memory, present even after it's gone. Even when the sun is below the horizon, its light lingers. The sky stays bright for a while after sunset, illuminated by sunlight scattering off the atmosphere. And even when the sky is fully dark, the warmth remains. The heat stored in the earth and the air, a reminder that the sun was there, that it will be there again. You don't need to think about the sun for it to keep working. It doesn't need your attention or your awareness. It just keeps shining, keeps warming the earth, keeps driving the cycles of weather and life, completely indifferent to whether anyone notices. The sun holds the solar system steady with gravity. Its immense mass creates a gravitational well that keeps everything in orbit, from Mercury, closest to the sun, to Neptune and the distant reaches of the Kuiper Belt. The planets don't fall into the sun because they're moving, orbiting, their sideways motion balanced against the sun's pull. And they don't fly off into space because the sun's gravity keeps them tethered. It's a stable arrangement, one that has lasted for billions of years and will last for billions more. Tonight, you can let that steadiness become a feeling of safety. The sun is out there, even though you can't see it right now, even though it's nighttime where you are. It's still shining, still holding everything together, still doing what it has always done. There's something comforting in that, in knowing that some things are constant, that some things can be relied upon. The sun will rise again, in its own time, and you can rest until then. You don't need to worry about it. You don't need to do anything. The sun will take care of itself, and the world will turn and morning will come, as it always has, as it always will. Just one more small fact and then we drift. But there are no more facts. There's just this moment, this quiet, this slow release of the day. You've followed the sun from its core to its corona, from its birth billions of years ago to the light that touched your face this morning. You've learned about layers and cycles, about fusion and magnetic fields, about the gentle ways the sun shapes your world and your life. And now, all of that can fade away. You don't need to remember any of it. You don't need to hold on to the facts or the numbers or the names. They were just here to give your mind something to follow, something calm and steady to trace as you let go of the day's thoughts and worries. The sun is still out there, doing its work, burning hydrogen into helium, sending light streaming out into space. It doesn't need you to understand it. It doesn't need you to think about it. It just keeps going, patient and constant, a quiet anchor in the vastness of space. And you can take that constancy with you into sleep, a sense that the universe is orderly, that the cycles continue, that there's no rush, no urgency, nothing that needs your attention right now. Your breathing has slowed, the tension in your shoulders is eased, the thoughts that were racing through your mind have quieted. There's just the rhythm of your breath, the weight of your body sinking into the bed, the gentle darkness behind your closed eyes. The sun's story is over for tonight, but the sun itself continues, shining somewhere beyond the horizon, warming the other side of the world, lighting someone else's morning while you rest. Let your mind wander if it wants to wander. Let it drift to the image of the sun as a glowing sphere, layers upon layers of hot gas, slowly churning, slowly rotating, the core burning bright at the center, the surface shimmering with granules and spots, the corona reaching out into space like a halo. Or let it drift to something simpler, just the feeling of sunlight, warm on your skin, the way it looks filtering through leaves or reflecting off water. Or let it drift to nothing at all, just the soft darkness, the quiet, the stillness. There's no need to fight sleep. There's no need to force anything. Sleep will come in its own time, just as the sun will rise in its own time. You can trust that. You can let go. The sun holds the planets in their orbits with gravity steady and reliable, and in the same way, sleep will hold you, gently, inevitably. You're safe here. You're allowed to rest. The day is done. The facts are done. The sun is shining somewhere, and you are here, breathing slowly, letting go, drifting. The sun's light travels 8 minutes to reach Earth, but you don't need to wait for anything. You're already where you need to be. The warmth is already here, stored in the walls, in the air, in the memory of the day. The light is already here, even in the darkness, a soft presence, a quiet knowing that morning will come. And until then, there is only this, the slow, steady rhythm of your breath, the feeling of your body at rest, the gentle pull of sleep drawing you deeper, deeper into warmth, into darkness, into the quiet place where thoughts dissolve and nothing is required of you. Just one more small fact, and then we drift. But we've already drifted. We're drifting now. The sun is a star at the center of our solar system, and you are here, at the center of your own quiet moment, letting everything else fall away. The facts about the sun, the science, the numbers, they're all fading now, becoming less distinct, less important, until they're just a soft murmur, a distant hum, something that might have been interesting once, but now is just part of the background, part of the gentle, static that lulls you towards sleep. The sun will be there tomorrow. It will rise as it always does, pouring light over the horizon, warming the air, starting the cycle again. But that's tomorrow's concern, not tonight's. Tonight, You rest. Tonight, you let the sun do its work without you. Let the earth turn without your attention. Let the universe continue its slow, steady rhythms while you sink into sleep. The sun holds the solar system steady, and sleep holds you steady, and everything is exactly as it should be. The granules on the sun's surface rise and fall, each one lasting only minutes before it breaks apart and reforms, a constant churning, a constant renewal. Your thoughts are like that, rising and falling, appearing and dissolving, and you don't need to hold on to any of them. Let them rise, let them fall, let them drift away like the solar wind, streaming out into space, carrying particles of worry and tension and the remnants of the day far, far away from you until there's nothing left but stillness. The corona is surprisingly hot, hotter than the surface below it, and no one fully understands why. It's a mystery, one of many mysteries in the universe, and that's okay. You don't need to solve it. You don't need to understand everything. Some things can remain unknown, unexplained, soft around the edges, and that doesn't diminish them. The sun is beautiful and complex and ancient, and you are here, breathing, resting, alive in this moment, and that's enough. 8 minutes. That's how long it takes sunlight to reach Earth. 8 minutes of travel through the void, crossing 93 million miles of empty space, and then it arrives, gentle and warm, touching the surface of the planet, touching your skin, becoming part of your day. But those 8 minutes are nothing compared to the time it took for that light to journey from the core to the surface. Hundreds of thousands of years of bouncing and scattering, a slow, patient escape from the heart of the sun. Everything takes time. Everything unfolds at its own pace. Even light, the fastest thing in the universe, needs time to travel. And you, too, can take your time. You can let sleep come slowly, naturally, without rushing, without forcing. The sun's magnetic field twists and tangles, creating sunspots and prominences, loops of glowing plasma suspended in space, held by invisible forces. Your thoughts are tangled too, threads of the day woven together, and now you can let them untangle, let them smooth out, let them release their hold on you. There's nothing you need to figure out right now. There's nothing you need to plan or worry about or solve. It can all wait. It can all dissolve into the quiet. The solar cycle rises and falls, 11 years from peak to peak, a slow heartbeat, a breathing in and out of activity. Your own breath rises and falls, in and out, a rhythm you don't have to think about, a rhythm that continues on its own, steady and reliable. You can follow that rhythm if you like, or you can let it fade into the background, just another part of the quiet, another part of the stillness. The sun is one star among hundreds of billions, ordinary and average, nothing special except that it's ours, except that it's close enough to warm us, close enough to light our days, and you are one person among billions, ordinary and average in some ways, unique in others, and tonight that doesn't matter. Tonight, you're just here, resting, part of the vast, quiet universe, connected to the sun by 8 minutes of light, connected to the earth by gravity, connected to sleep by the simple, inevitable need to rest. The atoms in your body came from stars, formed in the cores of ancient suns, scattered into space when those stars died, gathered together again in the cloud that became our solar system. You are stardust, shaped by billions of years of cosmic history, and tonight you return to the stars in a way, returning to the quiet, the darkness, the stillness from which everything came. Sleep is a kind of return, a letting go, a sinking back into the void that holds everything. The sun doesn't need you to watch it. It doesn't need your awareness or your attention. It shines whether you're awake or asleep, whether you're thinking about it or not. And in the same way, your body doesn't need your attention to keep breathing, to keep your heart beating, to keep you alive. You can let go of control. You can trust your body to do what it needs to do. You can trust sleep to come, to hold you, to carry you through the night. Just one more small fact, and then we drift. But we've already drifted so far. We're already deep in the quiet, deep in the soft darkness, and there are no more facts, no more explanations, no more words. There's just this, the gentle weight of your body, the slow rhythm of your breath, the feeling of letting go, of sinking, of drifting down into sleep like sunlight sinking through water, soft and golden and fading, fading, fading into the deep. The sun will rise again in its own time and you can rest until then. The next story is about to begin. Please relax and enjoy. The moon hangs in our sky at an average distance of about 238,855 miles from Earth, though this number shifts constantly as our natural satellite follows its elliptical path around our planet. This distance, while vast by human standards, represents one of the closest celestial relationships in our solar system. The moon orbits Earth roughly once every 27.3 days, measured relative to the background stars, though the cycle from new moon to new moon takes slightly longer at 29.5 days due to Earth's own motion around the sun. This gentle perpetual dance has continued for billions of years, creating the rhythmic patterns that govern tides, influence ecosystems, and provide a steady companion in our night sky. The moon's formation remains one of the most fascinating stories in planetary science, and the leading explanation involves a collision of almost unimaginable violence that paradoxically created the serene object we see today. Scientists currently think that about 4.5 billion years ago, when Earth was still very young and hot, a Mars-sized object collided with our planet in a grazing impact. This impactor, sometimes called Theia by researchers, struck Earth at just the right angle and speed to blast enormous amounts of material into orbit rather than merging completely or bouncing away. The debris from this catastrophic encounter, a mixture of material from both Earth's outer layers and the impactor itself, formed a ring of molten rock and vapour circling our planet. Over time, measured in years and centuries and millennia, this ring gradually coalesced through gravitational attraction, building up into the moon we know today. Evidence for this giant impact hypothesis comes from multiple sources, including the similar composition of Earth and moon rocks, the moon's relatively small iron core compared to Earth's, and the angular momentum of the Earth-Moon system. When we look at the moon's surface, we see a landscape frozen in time, preserving a record of the solar system's violent youth. The most prominent features visible even to the naked eye are the dark patches called maria, a Latin word meaning seas, though no water flows there and perhaps never has. These maria formed between 3.8 and 3 billion years ago during a period of intense asteroid and comet bombardment. When these massive objects struck the moon's surface, they created enormous impact basins that subsequently filled with molten basaltic lava flowing up from the moon's interior. The lava spread across the basin floors in vast sheets, sometimes hundreds of feet thick, before cooling and solidifying into the smooth, dark plains we observe today. The lighter areas surrounding these dark maria are the lunar highlands, representing the moon's original crust, which formed when the early moon's surface was a global ocean of molten rock. As this magma ocean slowly cooled over millions of years, lighter minerals floated to the top while denser materials sank, creating the layered structure that produced the bright highland rocks. The surface of the moon bears the scars of billions of years of impacts, and examining these craters tells us much about the history of our corner of the solar system. Unlike Earth, where erosion from wind and water, tectonic activity, and biological processes constantly reshape the surface, the moon preserves its impact record with remarkable fidelity. The largest impact basin on the moon's near side is the Imbrium Basin, measuring about 750 miles across, created by an impact so powerful it sent shockwaves through the entire moon and scattered debris across the lunar surface. The youngest large crater visible through binoculars is Tycho, a relatively fresh impact feature only about 108 million years old, whose bright rays of ejected material extend across much of the moon's southern hemisphere. These rays appear bright because the impact excavated fresh material from beneath the lunar surface, material that hasn't yet been darkened by billions of years of exposure to solar radiation and micrometeorite bombardment. The process that darkens lunar soil happens slowly but inexorably, as energetic particles from the sun and tiny impacts gradually alter the chemical structure of the surface minerals. The moon's lack of atmosphere has profound implications for its surface conditions and appearance. Without air to scatter sunlight, the lunar sky remains utterly black even during the day, with stars visible alongside the sun for any observer standing on the moon. The absence of atmospheric protection means that the lunar surface experiences temperature extremes unknown on Earth, ranging from about 260 degrees Fahrenheit in direct sunlight at the lunar equator to minus 280 degrees Fahrenheit in the permanent shadows near the poles. These temperatures shift not gradually but abruptly, with the boundary between sunlight and shadow marking a transition of hundreds of degrees within the span of a few feet. The moon's day-night cycle lasts nearly a month by Earth standards, with each location experiencing about 14 Earth days of continuous sunlight followed by 14 Earth days of darkness. This extended exposure to solar radiation during the lunar day heats the surface slowly but thoroughly, while the equally long night allows heat to radiate into space without atmospheric insulation to retain warmth. One of the moon's most remarkable characteristics, often taken for granted but actually quite unusual, is that we always see the same face from Earth. This phenomenon results from a process called synchronous rotation or tidal locking, where the moon's rotation period exactly matches its orbital period around Earth. This wasn't always the case. When the moon first formed, it likely rotated much faster. However, Earth's gravity creates tidal bulges in the moon's structure, not just in any hypothetical oceans, but in the solid rock itself. As the moon rotated, these bulges tried to move, but Earth's gravity pulled on them, creating friction and gradually slowing the moon's rotation. Over hundreds of millions of years, this tidal friction continued until the moon's rotation rate synchronized with its orbit, leaving the same hemisphere perpetually facing Earth. The far side of the moon, never visible from Earth without spacecraft, differs noticeably from the near side, possessing far fewer maria and a thicker crust. Scientists think this asymmetry may relate to Earth's influence during the moon's formation and early history, though the complete explanation remains an active area of research. The moon exerts a powerful influence on Earth through gravitational tides, creating a twice-daily rhythm in our oceans that has shaped coastal ecosystems and human maritime activities throughout history. The basic mechanism of tides involves the gravitational attraction between the moon and Earth's water, though the actual physics proves more subtle than simple attraction. The moon's gravity pulls on the side of Earth nearest to it, with slightly more force than it pulls on Earth's centre, which in turn experiences more pull than the far side. This differential gravitational force stretches Earth very slightly into an oval shape, with bulges on both the near and far sides. Because Earth's surface is mostly solid rock, this stretching amounts to only inches, but the oceans, being fluid, respond more dramatically, creating the oceanic tides. As Earth rotates beneath these tidal bulges, different locations pass through high and low tide, approximately every 12 hours and 25 minutes. The Sun also creates tides, though its effect is smaller than the Moon's despite the Sun's vastly greater mass, because tidal force depends on the difference in gravitational pull across Earth's diameter, and the Moon's proximity makes its differential effect stronger. The twice-monthly cycle of spring and neap tides demonstrates the interplay between solar and lunar tidal influences. Spring tides, which occur during new and full moons, happen when the Sun and Moon align and their tidal effects combine, creating higher high tides and lower low tides than average. The term spring refers not to the season but to the idea of the tide springing or rising higher. Neap tides occur during the Moon's first and third quarters when the Sun and Moon form a right angle as seen from Earth, causing their tidal effects to partially cancel each other, resulting in more moderate tidal ranges. The magnitude of tides varies considerably depending on local geography, with some locations experiencing tidal ranges of only a foot or two, while others, particularly in narrow bays and estuaries where tidal waters are funneled and amplified, see ranges exceeding 50 feet. The Bay of Fundy in Canada holds the record for the highest tides on Earth, with a maximum range of about 53 feet, creating dramatic transformations of the coastline twice daily. Beyond their effects on ocean levels, tides have more subtle but profound impacts on Earth's rotation and the Moon's orbit. The friction between tidal waters and the ocean floor, along with the deformation of Earth's solid body, dissipates energy and gradually slows Earth's rotation. This lengthening of Earth's day proceeds at a rate of about 1.7 milliseconds per century, a tiny change imperceptible in human lifetimes but significant over geological time. When Earth rotates with shallow seas sloshing across continental shelves, the tidal friction becomes particularly effective at extracting rotational energy. This energy doesn't vanish but rather transfers to the Moon's orbital motion through a complex gravitational interaction involving the slight offset of Earth's tidal bulge. Because Earth rotates faster than the Moon orbits, Earth's rotation drags the tidal bulge slightly ahead of the direct Earth-Moon line. This offset bulge then gravitationally pulls on the Moon in the direction of its orbital motion, accelerating the Moon and causing it to slowly spiral outward. laser-ranging measurements, which bounced light off reflectors placed on the lunar surface by Apollo astronauts, confirm that the moon recedes from Earth at about 1.5 inches per year. Looking backward in time, this lunar recession means the moon was closer to Earth in the past and much closer in the very distant past. When the moon first formed at perhaps 10 to 15,000 miles from Earth, compared to today's roughly 240,000 miles, it would have appeared enormous in Earth's sky, subtending an angle perhaps 15 to 20 times larger than today. The tides raised by this nearby moon would have been correspondingly stronger, possibly reaching heights of hundreds of feet and occurring every few hours as the young Earth spun, rapidly on its axis. Some scientists have speculated that these extreme tides may have influenced the development of Earth's early crust, and perhaps even played a role in mixing the primordial oceans in ways that affected the chemistry relevant to the origin of life, though such ideas remain highly speculative. The moon's gradual distancing has another eventual consequence that becomes apparent during solar eclipses. Currently, the moon's apparent size in our sky matches the sun's apparent size almost exactly, a cosmic coincidence that allows for the spectacular phenomenon of total solar eclipses, where the moon can precisely cover the sun's bright disk while leaving the faint outer atmosphere, the corona, visible. This match occurs because although the sun is about 400 times larger than the moon, it's also about 400 times farther away, making the two objects appear nearly the same size from Earth. However, as the moon continues to recede, its apparent size will gradually shrink. In roughly 600 million years, the moon will be too far from Earth to completely cover the sun, and total solar eclipses will become impossible, replaced by only annular eclipses where a ring of sunlight remains visible around the moon's silhouette. Solar eclipses themselves follow predictable patterns thanks to the regular geometry of the Earth-Moon-Sun system, though predicting exactly where on Earth an eclipse will be visible requires careful calculation. A solar eclipse can occur only during a new moon, when the moon passes between Earth and the Sun, but not every new moon produces an eclipse because the moon's orbit around Earth is tilted about 5 degrees relative to Earth's orbit around the Sun. This tilt means the moon usually passes above or below the Sun from Earth's perspective. Eclipses happen only when a new or full moon coincides with the moon crossing the plane of Earth's orbit, points called nodes. The geometry of these orbital intersections repeats in a cycle called the Saros, lasting approximately 6,585 and 1/3 days, or about 18 years, 11 days, and 8 hours. After one Saros cycle, the Sun, Earth and Moon return to nearly the same geometric arrangement, producing a similar eclipse. However, the extra 1/3 day in the cycle means the eclipse occurs about 8 hours later in Earth's rotation, shifting the visibility path about 120 degrees westward. The narrow path of totality during a solar eclipse, typically only about 70 to 100 miles wide, results from the moon's shadow having two parts. The inner darker shadow called the umbra creates the path of totality where the sun is completely blocked, while the outer, lighter shadow called the penumbra creates a region where the sun is only partially blocked. Because the moon is relatively small, and its distance from Earth varies as it orbits, the umbra sometimes fails to reach Earth's surface at all, creating annular eclipses where the moon appears slightly smaller than the sun. The maximum duration of totality during a solar eclipse is about 7.5 minutes, achieved when the moon is at its closest point to Earth and moving most slowly across the sun's face, though most total solar eclipses are considerably shorter, typically lasting between 2 and 3 minutes. Lunar eclipses present a different spectacle, occurring when Earth passes between the sun and moon, causing Earth's shadow to fall on the lunar surface. These eclipses can happen only during a full moon and are visible from the entire nighttime half of Earth, unlike solar eclipses which are visible only from specific narrow paths. During a total lunar eclipse, the moon doesn't disappear completely, but instead often takes on a coppery red colour. This colouring results from sunlight passing through Earth's atmosphere and bending into the shadow region. Earth's atmosphere scatters blue light more effectively than red light, the same phenomenon that makes sunsets red and the sky blue. So the light reaching the moon during an eclipse has had its blue components removed, leaving primarily red wavelengths to illuminate the lunar surface. The exact colour and brightness of the eclipsed moon depends on Earth's atmospheric conditions at the time, with volcanic eruptions or unusual dust content creating darker or more colourful eclipses. The Moon's interior structure has been revealed through various means, including seismometers placed by Apollo astronauts and analysis of the Moon's gravitational field and physical properties. The Moon possesses a layered structure somewhat similar to Earth's, with a crust, mantle, and core, though the proportions differ significantly. The lunar crust ranges from about 25 miles thick on the near side to about 40 miles thick on the far side, this asymmetry representing one of the Moon's puzzling features. Below the crust lies the mantle, composed primarily of silicate rocks rich in magnesium and iron, extending down to a depth of roughly 900 miles. The deepest moonquakes detected by Apollo seismometers originated at depths of about 600 to 800 miles, likely caused by gravitational tides from Earth stressing the lunar interior. These deep moonquakes occurred repeatedly at the same locations and times during the Moon's orbit, indicating they relate to specific tidal stress patterns. The lunar core, much smaller relative to the Moon's size than Earth's core is to Earth's size, consists of a solid inner core and possibly a liquid outer core, together measuring perhaps 300 miles in radius. This small core helps explain why the Moon lacks a global magnetic field today, though measurements of lunar rocks reveal that some possessed magnetization, requiring an ancient lunar magnetic field. Scientists think the Moon may have generated a magnetic field through a dynamo process early in its history when the core was entirely molten and convecting. But as the Moon cooled and much of the core solidified, this dynamo ceased. Some localized magnetic anomalies on the lunar surface, regions where rocks show unexpectedly strong magnetization, might represent impacts that occurred while the lunar dynamo was still operating, with the shock of the impact effectively freezing the ambient magnetic field into the rocks as they cooled. The Apollo program of the 1960s and 70s represents humanity's most direct interaction with the Moon, placing 12 astronauts on the lunar surface across 6 missions between 1969 and 1972. These missions returned 842 pounds of lunar rocks and soil, samples that remain the primary source of detailed information about lunar composition and history. The rocks revealed that the Moon's maria consist of basalt similar to volcanic rocks on Earth, but with subtle compositional differences, including lower water content and different relative abundances of certain elements. The highland rocks proved to be largely an orthosite, a light-coloured rock rich in the mineral plagioclase feldspar, consistent with the hypothesis that they formed as light minerals floated to the top of a cooling magma ocean. Dating these rocks using radioactive decay systems showed that the highland rocks are extremely ancient, with formation ages of 4.4 to 4.5 billion years, nearly as old as the solar system itself, while the maria basalts are younger, ranging from about 3.8 to 3 billion years old. One surprising discovery from the Apollo samples was the near-complete absence of water in lunar rocks, or more precisely, the near-complete absence of water that was incorporated into minerals as they formed. The lunar rocks are drier than any naturally occurring rocks found on Earth, sometimes described as being drier than the driest terrestrial deserts. This extreme dryness supported the giant impact hypothesis for lunar formation, because the impact would have vaporized water and other volatile substances, allowing them to escape. However, more recent discoveries have complicated this picture slightly. Orbital spacecraft have detected signatures of water ice in permanently shadowed craters near the lunar poles, where temperatures remain cold enough that ice can persist for billions of years. Additionally, very sensitive measurements of Apollo samples have revealed traces of water in volcanic glass beads and in the interiors of some minerals, suggesting the Moon's interior might not be quite as dry as once thought, though it remains extremely dry by Earth standards. The permanently shadowed craters near the Moon's poles represent some of the coldest places in the solar system, with temperatures that may reach as low as -400 degrees Fahrenheit, or perhaps even colder. These cold traps occur because the Moon's axis of rotation is tilted only about 1.5 degrees relative to its orbital plane, compared to Earth's 23.5-degree tilt. This near-vertical orientation means that the floors of deep craters near the poles never receive direct sunlight. Any water molecules that happen to wander into these cold traps, perhaps delivered by comet impacts or produced by interactions between the solar wind and oxygen in lunar rocks, would freeze and remain frozen for geological time periods. Some researchers have speculated that these permanently shadowed regions might contain not just water ice, but also frozen deposits of other volatile substances, including carbon dioxide, ammonia and methane, creating a record of material delivered to the inner solar system over billions of years. The lunar surface experiences constant bombardment by micrometeorites, tiny particles ranging from dust grains to pebbles that strike the moon at velocities of tens of thousands of miles per hour. Without an atmosphere to burn them up, these particles strike the surface directly, creating microscopic craters and gradually pulverizing the upper layers of rock into a fine powder. This process, operating over billions of years, has created the lunar regolith, a layer of fragmented and broken rock covering the moon's surface to depths ranging from about 10 feet in the Maria to perhaps 30 feet or more in the highlands. The regolith consists not just of simple crushed rock, but includes glass spherules created when impacts melted rock, particles welded together by impact heat, and fragments excavated from depths and transported far from their origins by large impacts. Walking on the lunar surface, Apollo astronauts found the regolith behaved somewhat like snow, compressing under their boots but also clinging to their spacesuits with surprising tenacity. The constant rain of solar wind particles, primarily protons and electrons streaming from the sun, affects the lunar surface in subtle but interesting ways. These energetic particles strike the moon directly without atmospheric shielding and become implanted in the upper layers of regolith grains. Over time, solar wind hydrogen can react with oxygen in lunar minerals to create tiny amounts of water or hydroxyl groups, explaining some of the water signatures detected by spacecraft. The solar wind implantation also creates a very thin and extremely tenuous atmosphere, if it can be called an atmosphere at all, consisting of particles knocked off the surface by impacts and solar wind bombardment. This exosphere is so tenuous that particles almost never collide with each other, following ballistic trajectories more like spacecraft in orbit than like molecules in a gas. The moon's influence extends beyond physical effects, like tides, to encompass cultural and biological influences that have shaped life on Earth and human civilization. The regular cycles of lunar phases provided early humans with a natural calendar, and many cultures developed lunar or lunisolar calendars to track time and coordinate seasonal activities. The word month derives from moon, reflecting this ancient connection. Some biological organisms synchronize their reproductive cycles with lunar phases, the most famous examples being certain marine species that spawn during specific lunar phases, apparently using moonlight levels or tidal patterns as timing cues. Coral reefs around the world often show synchronized spawning events tied to lunar cycles, releasing eggs and sperm on specific nights following full moons, a strategy that increases the chances of successful fertilization while also potentially overwhelming predators with the sheer abundance of gametes in the water. Whether the moon affects human biology and behavior beyond providing light at night remains controversial, with many claimed lunar effects failing to hold up under careful statistical analysis. The popular notion that full moons influence human behavior, causing increased emergency room visits, psychiatric episodes, or births, has been extensively studied and generally not supported by data when proper statistical controls are applied. The term lunacy derives from the Latin word for moon, luna, reflecting ancient beliefs about lunar influences on the mind. But modern evidence suggests these effects were likely either coincidental or caused by confirmation bias. However, the moon certainly influences human activity indirectly by providing illumination during night hours and in pre-industrial societies without artificial lighting. Full moons would have enabled activities impossible during dark nights, potentially affecting sleep patterns and activity rhythms. Future exploration of the moon has become a focus of renewed interest from space agencies and private companies around the world. The motivations include scientific discovery, testing technologies for eventual Mars missions, and potentially utilizing lunar resources. The presence of water. Ice in polar cold traps has attracted particular attention because water can be split into hydrogen and oxygen, providing both rocket propellant and breathable air for future astronauts. The moon's low gravity, about 1/6 that of Earth, means that launching spacecraft from the lunar surface requires far less energy than launching from Earth, potentially making the moon a useful staging point for missions deeper into the solar system. Additionally, the moon's far side offers a unique environment for radio astronomy, shielded from Earth's radio noise by the bulk of the moon itself, allowing potentially unprecedented observations of faint cosmic radio signals. Several space agencies have announced plans for lunar missions in the coming decades, including NASA's Artemis program, which aims to return humans to the moon and establish a sustainable presence there. The technical challenges of maintaining a human presence on the moon include protection from radiation, since the moon lacks both a magnetic field and atmosphere to shield against solar and cosmic radiation, and dealing with the abrasive lunar dust, which caused significant problems for Apollo equipment, despite missions lasting only a few days. The temperature extremes and the long lunar day-night cycle pose additional engineering challenges for any permanent facilities, which would need to either store energy for the 14-day night or be located at special locations near the poles where elevated terrain can receive nearly continuous sunlight. The moon's geology continues to present puzzles and opportunities for research. The Maria, while broadly understood as ancient lava flows, show detailed features that reveal information about lunar volcanic processes. Some Maria contain sinuous channels called rills, winding features that sometimes extend for hundreds of miles and may represent either collapsed lava tubes or channels carved by flowing lava. The lunar surface also contains mysterious dome structures, thought to be volcanic in origin, and straight or curved features called wrinkle ridges that may represent buckling of the lava flows as they cooled and contracted, or as the weight of the lava compressed the underlying crust. Understanding these features helps planetary scientists piece together the moon's volcanic history and compare it to volcanic processes on Earth and other solar system bodies. The lunar highlands, making up about 83% of the moon's surface, preserve a record of the intense bombardment that all inner solar system bodies experienced early in their histories. This period of heavy bombardment, lasting from the solar system's formation until about 3.8 billion years ago, shaped the surfaces of the Moon, Mercury, Mars, and even Earth, though Earth's active geology has erased most direct evidence from our planet's surface. The timing and intensity of this bombardment remains somewhat uncertain, with some evidence suggesting a spike in impact rates around 3.9 billion years ago, sometimes called the Late Heavy Bombardment. Whether this represents a true increase in impact rates or simply a bias in the preservation of evidence remains debated, but studying lunar craters and their ages helps scientists understand this important phase of solar system evolution. The Moon has no plate tectonics like Earth, where large sections of crust move relative to each other, creating mountains, ocean basins, and recycling surface material into the interior. The Moon's smaller size meant it cooled more rapidly than Earth, and its interior appears to be largely solid today, lacking the vigorous convective motions in the mantle that drive Earth's plate tectonics. Without this geological recycling and without erosion from water or atmosphere, the lunar surface preserves features billions of years old with remarkable clarity. This geological stillness makes the Moon valuable as a record of solar system history, but it also means that the Moon's active geological history was relatively brief. Most of the Moon's volcanic activity occurred between about 3.8 and 3 billion years ago, with little evidence for volcanic activity in the most recent billion years, though some researchers have argued for occasional small eruptions in more recent times based on fresh-looking deposits. The Moon's gravitational field shows interesting variations that reveal information about its internal structure. Concentrations of mass beneath some of the large impact basins, called mascons for mass concentrations, create regions of slightly stronger gravity that can affect the orbits of spacecraft. These mascons probably represent the dense mantle material that welled up after the giant impacts, partially filling the basins before the lava flows arrived. The presence of mascons indicates that the lunar lithosphere, the strong outer shell of the Moon, was thick enough to support these mass concentrations, without the basins collapsing back to equilibrium, suggesting the Moon had already cooled and developed a substantial lithosphere by the time the large impacts occurred. One of the curious aspects of the Moon's orbit is its slight eccentricity, meaning the orbit is not perfectly circular but slightly elliptical. This eccentricity causes the Moon's distance from Earth to vary from about 225,000 miles at perigee, the closest point, to about 252,000 miles at apogee, the farthest point. When a full moon occurs near perigee, sometimes called a supermoon in popular media, the Moon appears about 14% larger and about 30% brighter than when full moon occurs near apogee. However, this size difference proves difficult to detect by eye without careful measurement or comparison photographs. The Moon's orbital eccentricity also varies over long time periods due to gravitational perturbations from the Sun and planets, though these variations are small and gradual. The Moon's orbit is also inclined about 5 degrees to the ecliptic, the plane of Earth's orbit around the Sun, and this inclination varies slightly over time in a cycle lasting about 18.6 years. This variation in orbital inclination affects how high the Moon appears in the sky from different latitudes on Earth and influences the patterns of tides. During the major standstill, when the Moon's orbital inclination reaches its maximum, the Moon can appear very high in the sky as seen from locations at high latitudes, while during the minor standstill, the Moon's range of positions becomes more restricted. Ancient monuments such as some stone circles in Britain appear to have been aligned with these lunar standstill positions, suggesting that prehistoric peoples tracked these cycles carefully, though the purposes of such tracking remain somewhat speculative. The Moon's surface contains numerous features named after scientists, philosophers, and other notable figures, following a tradition established in the 17th century by early telescopic observers. The lunar highlands contain craters named after Copernicus, Kepler, Tycho, and many other figures from the history of science and philosophy, while the Maria bear Latin names such as Mare Tranquillitatis, the Sea of Tranquility, where Apollo 11 landed, and Mare Imbrium, the Sea of Rains. Some features bear more whimsical names, like the crater Hadley Rill, named after John Hadley, who invented the reflecting sextant, which became the landing site for Apollo 15. The far side of the Moon, first photographed by Soviet spacecraft in 1959, contains additional name features including the Mare Moscoviense, the Moscow Sea, and craters named after space exploration pioneers. The question of whether the Moon could support life in any form has generally received a negative answer given the absence of atmosphere, liquid water, and protection from radiation. However, the discovery of more water than previously suspected, particularly the ice in permanently shadowed craters, raises interesting if highly speculative possibilities. If protected environments existed, perhaps in lava tubes or beneath the surface where ice deposits might exist, could these harbour simple microorganisms? Most scientists consider this extremely unlikely given what we know about the Moon's history and conditions, but the question illustrates how our understanding of possible habitats for life has expanded. More practically, if humans establish a permanent presence on the Moon, the question of preventing contamination becomes important both to protect any potential lunar science from terrestrial contamination and to avoid introducing Earth organisms into the lunar environment. The Apollo program left behind not just footprints and scientific instruments, but also several types of ongoing experiments that continue to provide data decades later. The most successful of these has been the laser-ranging retroreflectors, arrays of corner cube prisms that reflect laser beams directly back to their source. By timing how long laser pulses take to travel from Earth to the Moon and back, scientists can measure the Earth-Moon distance with remarkable precision, currently accurate to about a millimetre. These measurements have confirmed the gradual lunar recession, tested predictions of general relativity, and provided information about variations in Earth's rotation. The retroreflectors require no power and have no moving parts, allowing them to function indefinitely, though their reflective efficiency has decreased somewhat over the decades, possibly due to coating of lunar dust. The Moon's lack of global magnetic field today contrasts with evidence that some lunar rocks formed in the presence of a strong magnetic field billions of years ago. Understanding how and when the lunar magnetic field operated and eventually shut down provides clues about the Moon's thermal evolution and internal dynamics. The generation of magnetic fields in planetary bodies generally requires a dynamo process where flowing, electrically conducting fluid, usually liquid metal in a planet's core, converts kinetic energy into magnetic energy. For the Moon to have sustained a dynamo, its core must have been molten and convecting, which requires sufficient heat. As the Moon cooled over time, the core would have begun to solidify, potentially shutting down convection and ending the dynamo. Some researchers have proposed alternative mechanisms for the ancient lunar magnetic field, including the possibility that the giant impact that formed the Moon left the early Moon rotating much faster than today, and that this rapid rotation helped sustain a dynamo even with a smaller and cooler core than would normally be required. When astronauts first landed on the Moon, one concern was how the fine lunar dust would behave. The regolith, particles, never having been rounded by water or wind erosion, retain sharp edges and angular shapes that make them particularly abrasive. Additionally, Static electricity and the lack of moisture can cause the dust particles to cling to surfaces with surprising tenacity. Apollo astronauts reported that the dust worked its way into seals and mechanisms despite precautions, and they could smell the dust when it entered the lunar module, describing it as similar to gunpowder or spent fireworks. This smell probably resulted from chemical reactions when the dust, which had been altered by solar wind bombardment and vacuum conditions, suddenly encountered oxygen and moisture in the cabin atmosphere. Understanding and mitigating the effects of lunar dust represents one of the engineering challenges for future lunar missions, as prolonged exposure to the abrasive, clingy dust could damage equipment and potentially pose health hazards to astronauts. The moon's surface temperature varies not just between day and night, but also with depth below the surface. While the surface experiences extreme temperature swings, measurements from Apollo experiments showed that at depths of only a few feet, the temperature becomes stable at about -35 degrees Fahrenheit, representing an average of the surface temperature variations. This temperature stability with depth occurs because the regolith acts as an insulating layer, with the upper portion responding to daily temperature changes while deeper material maintains an equilibrium temperature. This property might prove useful for future lunar habitats, which could potentially maintain more stable temperatures by being partially buried in regolith, providing both thermal stability and some radiation shielding. The phenomenon of earthshine, where Earth's reflected sunlight illuminates the moon's night side, creates the beautiful sight of the dark portion of the crescent moon glowing faintly, sometimes called the old moon in the new moon's arms in poetry. This earthshine is bright enough that if you were standing on the moon's night side looking at Earth, our planet would provide much more light than the full moon provides on Earth, both because Earth is larger and because Earth's atmosphere and clouds make it more reflective. An observer on the moon would see Earth go through phases opposite to the lunar phases seen from Earth, with a full Earth visible from the moon during the new moon phase and a new Earth during the full moon. Additionally, Earth would appear to hang nearly motionless in the lunar sky, slowly rotating on its axis but not rising or setting for an observer on the lunar near side, while Earth would never be visible at all from the lunar far side. The moon stabilizes Earth's axial tilt through its gravitational influence, preventing the large variations in obliquity that would otherwise occur over millions of years due to gravitational perturbations from other planets. Without the moon, Earth's obliquity might vary chaotically between 0 and 85 degrees, creating extreme climate variations that would make the planet much less hospitable for life. The moon's presence keeps Earth's obliquity confined to a relatively narrow range around 23.5 degrees, varying by only about a degree or two over tens of thousands of years. This stability has likely been important for the development of complex life on Earth, providing relatively stable climate zones and preventing the catastrophic climate shifts that large obliquity variations would cause. This represents one of the subtle but profound ways the moon has influenced Earth's evolution and habitability. Looking at the moon through a telescope reveals a wealth of detail impossible to see with the naked eye. The curved line separating the illuminated and dark portions of the moon, called the terminator, offers the best views of surface features because the low angle of sunlight near the terminator creates long shadows that highlight topographic variations. Craters, mountains and valleys that might appear flat and washed out in high, overhead sun stand out in sharp relief near the terminator. The moon's features show best not during the full moon, despite maximum brightness, but during the quarter phases when the terminator bisects the visible face, and shadows reveal three-dimensional structure. Observers with telescopes can see the central peaks inside some large craters, mountainous terrain in the highlands, the smooth plains of the Maria, and the bright ray systems extending from young craters. The moon has inspired countless works of art, literature and music throughout human history, serving as a symbol of romance, mystery and aspiration. From ancient myths explaining the moon's phases and features to science fiction stories imagining lunar inhabitants or bases, the moon occupies a unique place in human culture. The achievement of landing humans on the moon in 1969 represented not just a technical accomplishment, but a moment when humanity first set foot on another celestial body, expanding our physical presence beyond Earth. The famous photograph of Earth rising over the lunar horizon, taken by Apollo 8 astronauts in December 1968, provided a new perspective on our home planet as a small, beautiful, fragile world hanging in the void, an image that helped inspire environmental awareness and a sense of our common humanity. The phases of the moon result from the changing angles between the Sun, Earth and Moon as the moon orbits Earth. During the new moon, the moon lies between Earth and the Sun, with its illuminated side facing away from Earth, making it invisible except during solar eclipses. As the moon continues its orbit, a thin crescent becomes visible, growing thicker each night as more of the illuminated face becomes visible from Earth. At the first quarter, half of the moon's face appears illuminated, though the term quarter refers to the moon's position in its orbit rather than the visible fraction. The waxing gibbous moon shows more than half illuminated, until the full moon occurs when Earth lies between the Sun and Moon, and we see the entire illuminated face. The cycle then reverses through waning gibbous, third quarter, and waning crescent before returning to new moon. This entire cycle takes 29.5 days, slightly longer than the moon's orbital period of 27.3 days because Earth's motion around the Sun means the moon must travel slightly more than one complete orbit to return to the same phase. The moon's influence on Earth's rotation, gradually slowing it through tidal friction, means that Earth's day has been lengthening throughout geological history. When the moon first formed, Earth's day may have been only 4 to 6 hours long, compared to today's 24 hours. Evidence for Earth's changing rotation rate comes from multiple sources, including growth patterns in ancient corals and other organisms that recorded daily and annual cycles in their structures. By counting daily growth bands within yearly patterns in fossil corals hundreds of millions of years old, paleontologists have determined that Earth's day has indeed grown longer over time, consistent with the predictions from tidal friction theory. This gradual slowing continues today, adding about 1.7 milliseconds to the day length per century, a change that accumulates enough over many centuries that it becomes necessary to occasionally add leap seconds to our atomic time standards to keep them synchronized with Earth's actual rotation. The moon's surface features include not just craters and maria, but also mysterious swirl-like patterns visible in some locations, appearing as bright, winding streaks on the surface. These lunar swirls, found in areas such as Reina Gamma and near the far-side crater Mare Marginis, don't obviously correspond to topographic features, but instead appear to be albedo markings, where surface material has different reflective properties. The swirls correlate with local magnetic anomalies, regions where crustal rocks possess stronger than average magnetization. One hypothesis suggests that these magnetic fields, though weak by Earth standards, provide slight protection from solar wind bombardment, preventing or slowing the normal darkening of the soil that occurs over time, thus preserving brighter, fresher-looking material. Alternative explanations involving comet impacts or other processes have also been proposed, but the magnetic shielding hypothesis currently appears most consistent with observations. The Moon's interior, though much less active than Earth's, may not be completely dead geologically. Seismometers placed by Apollo astronauts detected thousands of seismic events during their operating period, ranging from impacts of meteorites and spacecraft to deep moonquakes and thermal quakes, caused by the sudden temperature changes at sunrise. The deep moonquakes, occurring at depths of 600 to 800 miles, appear to result from tidal stresses caused by Earth's gravity flexing the Moon slightly as it orbits. These moonquakes are much weaker than typical earthquakes, but occur in clusters at specific locations and times in the lunar month, creating a predictable pattern tied to the Moon's orbital position. Thermal moonquakes, caused by the expansion and contraction of surface rocks as they heat in sunlight and cool in shadow, mostly occur near sunrise when surface rocks experience the most rapid temperature changes. Recent analysis of Apollo seismic data using modern techniques has revealed additional information about the lunar interior, including evidence for a partially molten layer at the base of the mantle and confirmation of a small metallic core. The details of the core structure remain somewhat uncertain, with estimates of the solid inner core radius ranging from about 150 to 250 miles, and the liquid outer core perhaps extending to a radius of about 200 to 300 miles. These small sizes, compared to Earth's core, which extends to about half of Earth's radius, help explain why the Moon lacks a current magnetic field and provide constraints on models of lunar formation and thermal evolution. Volcanic glasses found in lunar samples provide evidence for fire fountaining, where lava erupted explosively from the lunar interior, spraying droplets that cooled and solidified into tiny glass beads. These pyroclastic deposits sometimes appear as dark halos around small craters or as darker patches on the Maria, representing volcanic material spread across the surface by explosive eruptions rather than flowing as lava. The composition of these glasses reveals information about the Moon's interior chemistry, and the presence of the glasses indicates that at least some lunar magmas contained enough dissolved gases to drive explosive eruptions, contrary to the expectation that the Moon's interior would be completely dry and unable to produce such eruptions. The gases involved were probably not water vapour, but instead carbon monoxide or sulfur compounds. The Moon affects life on Earth in subtle ways beyond the obvious tides. The lunar illumination cycle influences the behaviour of many nocturnal animals, with some species more active during bright moonlit nights and others preferring darker periods. Predator-prey relationships can shift with lunar phase, as moonlight makes it easier for predators to hunt, but also makes it easier for prey to detect approaching threats. Some researchers have found correlations between lunar cycles and ecological processes such as leaf litter decomposition rates or soil respiration, though the mechanisms for such effects, if real, remain unclear. The Moon may also affect atmospheric tides, creating subtle periodic variations in atmospheric pressure and winds, though these effects are much smaller than oceanic tides and difficult to measure against the background of weather variations. Throughout human history, different cultures have created myths and stories to explain the Moon's features, phases, and movements. Many cultures saw shapes or figures in the pattern of Maria and Highlands on the Moon's near side. Western tradition speaks of the man in the Moon, seeing the dark Maria as forming facial features, while other cultures identified different patterns. Some saw a rabbit or hare in the Moon, particularly in East Asian and Central American traditions, while others saw a woman, a toad, or various other figures. These interpretations demonstrate how humans naturally seek patterns and meaning in the objects around us, finding familiar forms even in the random arrangement of lunar geological features. The Moon's small size relative to Earth, only about 1/4 of Earth's diameter and 1/80th of Earth's mass, places it among the larger moons in the solar system relative to its planet. Only Charon, Pluto's moon, is larger relative to its primary body. This unusually large moon-to-planet ratio represents part of what makes the Moon's giant impact origin hypothesis compelling, as normal planet formation processes tend to produce relatively small moons. The energy involved in the giant impact that formed the Moon was sufficient to melt and partially vaporize both Earth and the impactor, creating the most violent event in Earth's history after the planet's initial formation. The fact that Earth survived this catastrophe and eventually cooled to become a habitable world demonstrates the resilience of planetary bodies and the ultimate constructive outcomes that can emerge from apparently destructive events. Looking toward the future, the Moon will continue its gradual recession from Earth, though this process will eventually halt as the Earth-Moon system evolves toward a final state where both bodies are tidally locked to each other, with the same face of each constantly facing the other. In this configuration, Earth's rotation period would match the Moon's orbital period, which by that time would be much longer than today, perhaps equivalent to about 50 to 60 current days. However, this final state lies billions of years in the future, and other factors will intervene before it arrives. The Sun will eventually begin to expand as it evolves off the main sequence, and within about 5 billion years the Sun's expansion into a red giant will likely engulf both Earth and the Moon, ending their long relationship in a very different way than their tidal evolution would suggest. For now, though, and for countless generations to come, the Moon will continue to grace our night sky, waxing and waning in its eternal cycle, pulling on our oceans, stabilizing our planet's tilt, and providing a constant reminder of the larger cosmos of which we are a part. The Moon represents both a neighbour we have visited and a frontier for future exploration, both a subject of scientific study and an object of beauty and inspiration. Understanding the Moon through science deepens rather than diminishes its wonder, revealing the intricate processes and vast timescales that shape our corner of the universe. As we drift towards sleep, we can reflect on the fact that the same Moon that lights the night sky tonight has shone down on Earth for more than 4 billion years, witnessing the rise of the oceans, the emergence of life, and the eventual appearance of beings capable of looking up and wondering about its nature. The Moon abides, patient and constant, a silver companion in the darkness, a gentle presence marking the passage of time while inviting contemplation of the deep history written in its ancient cratered face. The next story is about to begin. Please relax and enjoy.